AGI-24 conference. Hopefully everybody's been enjoying the conference, learning, sharing, talking with others and having great conversations about AGI and reading AGI papers and so on. A few important notes. There are three emergency exits, one here up in the front and two in the back. And there's not a fire drill, so if there is any alarms, treat it as real. We do want to thank all of our sponsors, SingularityNET, True AGI, the University of Washington, our publishers of the preceding Springer Nature, and the BICA conference, which is co-located here virtually. And our media partners, Twin Protocol, the Vancouver Startup Week, the BCCA 6th International Conference on Blockchain Computing and Applications, and Machine Learning Street Talk. This afternoon, unfortunately, Rachel St. Clair will be unable to join us today. At that time, around 4:35, give or take, we invite you to the other room here in room, I think it's 145, but it's just next door down the hall. There are a bunch of demos, there's poster sessions, and so take the opportunity at coffee breaks, at lunch, but especially at that 4:35 time to learn about some of the other cutting edge papers and presentations and demos. Don't forget to join us this evening beginning at 7 p.m. for the conference reception and the Desdemona Robots Dream Band performance, and that's going to be at the Burke Museum. Is that on which street? 40? Does anyone? It's on the map. It's not far from here. So, with that, our first session is going to begin this morning with Dr. Francois Cholet. He's a well-known AI researcher has developed the Keras framework. He worked on the TensorFlow framework before that as well, and wrote the book Python for deep learning, or deep learning with Python, which I used in my own classrooms. He's also creator of the ARC-AGI dataset to measure progress towards AI systems that can solve novel tasks on their own. Co-founder of the ARC Prize, $1 million prize to solve ARC-AGI and open source progress towards AGI. And I want to put this into the context of James Oswell's talk yesterday in the contributed paper session. He started off by asking, what is artificial general intelligence? But wait, first we need to understand what is general intelligence. And then he also went further and saying, well, first we need to understand intelligence. And Francois today, this morning, is going to discuss AGI, define it, measure it, and build it. And Francois, welcome.
All right, thank you for the very kind introduction. Okay, the mic should be on. Okay, thank you, Matthew, for the very kind introduction. Before we start building AGI, we need to ask ourselves the hard questions. What is intelligence? How can we measure it, benchmark progress? And what are the directions that we should follow to build it? So I just want to give you my take on these questions. And I'm going to start by taking you back to peak AGI hype, which was early last year. Do you remember what February 2023 felt like? ChatGPT had been released just a couple months prior. GPT-4 just came out. Bing Chat just came out. It was the Google killer. Anyone remember Bing Chat? And we were told that ChatGPT would make us 100x more productive, 1,000x more productive, that it would outright replace us. The existential risk of AI was becoming front page news. And AGI was just around the corner. It was no longer 10 years away, not even 5 years away. It was just a couple years away. You could start the countdown in months. And that was 1.5 years ago. And clearly back then, AI was coming for your job right away. It could do anything you could, but faster and cheaper. And how did we know this? Well, it could pass exams. And these exams are the way that we tell whether other humans are fit to perform a certain job. If AI passes the bar exam, then it can be a lawyer. If it can solve programming puzzles, then it can be a software engineer and so on. So many people were saying that all lawyers, all software engineers, all doctors and so on were going to be out of a job, maybe even within the next year, which would have been today. In fact, most desk jobs were going to disappear, and we faced mass unemployment. So it's very funny to think about it, because today the employment rate in the US is actually higher than it was at the time. So was that really true? You know, was it really what the benchmarks were telling us back then? So if you go back to the real world, you know, away from the headlines, away from the February 2023 hype, it seems that LLMs might be a little bit short of general AI. I'm sure most of you in this room would agree with that. They suffer from some problems. And these limitations are inherent to curve fitting. They're inherent to the paradigm that we are using to build these models. So they're not easy to patch. And in fact, there's been basically no progress on these limitations since day one. And day one was not last year. It was actually when we started using these transformer-based large language models, so over 5 years ago. So over 5 years ago, and we've not really made any progress on these problems because the models we are using are still the same. They're parametric curves fitted to a data set via gradient descent, and they're still using the same transformer architecture. So I'm going to cover these limitations. I'm not actually going to cover hallucinations because all of you are probably very familiar with it. But let's take a look at the other ones. So to start with, an interesting issue with LLMs is that because they're autoregressive models, they will always output something that seems likely to follow your question without necessarily looking at the contents of your question. So for instance, for a few months after the original release of ChatGPT, if you asked, what's heavier, 10 kilos of steel or 1 kilo of feathers, it would answer, they weigh the same. And it would answer that because the trick question, what's heavier, 1 kilo of steel or 1 kilo of feathers, is found all over the internet. And the answer is, of course, that they weigh the same. And so the model would just pattern match the question without actually looking at the numbers, without parsing the actual question you're asking. And same if you provide a variation of the Monty Hall problem, which is the screenshot right here. The LLM has memorized perfectly the canonical answer to the actual Monty Hall problem. So if you ask an absurd variation, it's just going to go right through it and output the answer to the original problem. So to be clear, these two specific problems, they've already been patched via RLHF, but they've been patched by special casing them. And it's very, very easy to find new problems that still fit this failure mode. So you may say, well, these examples are from last year, so surely today we are doing much better. And in fact, no, we are not. The issues have not changed since day one. We've not made any progress towards addressing them. They still plague the latest state-of-the-art models, like Claude 3.5, for instance. This is a paper from just a few days ago, from last month, that actually investigates some of these examples in state-of-the-art models, including Claude 3.5. So a closely related issue is the extreme sensitivity of LLMs to phrasing. If you change the names or places, variable names in a text paragraph, it can break LLM performance. Or if you change numbers in a formula. There's an interesting paper that investigates this, so you can check it out. It's called Embers of Autoregression. And people who are very optimistic, they would say that this brittleness is actually a great thing because it means that your models are more performant than you know. You just need to query in the right way and you will see better performance. You just need prompt engineering. And the counterpart to that statement is that for any LLM, for any query that seems to work, there is an equivalent rephrasing of the query that a human would readily understand that will break, right? And to what extent do LLMs actually understand something if you can break their understanding with very simple renamings and rephrasings? It looks a lot more like superficial pattern matching than robust understanding. We lost the clicker. Can you go next slide? Thank you. And besides that, there's a lot of talk about LLM's ability to perform in-context learning, to adapt to new problems on the fly. And what seems to actually happen is that LLMs are capable of fetching memorized programs, like problem-solving templates, and map them to the current task. And if they don't have a memorized program ready, if they're faced with something slightly unfamiliar, even if it's something very simple, they will not be able to analyze it from first principles the way a human could. So one example, Caesar ciphers. LLMs, state-of-the-art LLMs can solve a Caesar cipher, which is very impressive, right? But as it turns out, they can only solve it for very specific values of the key size. The specific values like 3 and 5 that you find commonly in online examples. If you show it an example of a Caesar cipher with a key size like 13, for instance, it will fail. So it has no actual understanding of the algorithm for solving the cipher. It has only memorized it for very specific values of the key size, right? So my hypothesis is that LLM performance depends purely on task familiarity and not at all on task complexity. There's not really any complexity ceiling to what you can get LLMs to solve, to memorize, as long as you give them the opportunity to memorize the solution or the problem-solving template, the program, right, that you have to run to get the answer. Instead, LLM performance depends entirely on task familiarity. And so even very simple problems, if they are unfamiliar, will be out of reach. Okay, the clicker is back. And lastly, LLMs suffer from a generalization issue with the programs that they did in fact memorize. So some examples include the fact that LLMs have trouble with number multiplication, as you probably know, with list sorting and so on, even though they've seen millions of examples of these problems. So they typically have to be aided by external symbolic systems in order to handle these things. There's an interesting paper that investigates how LLMs handle composition. So it's titled Limits of Transformers of Compositionality. And the main finding is that LLMs do not actually handle composition at all. What they're doing instead is linearized subgraph matching. There's another paper that's also very intriguing. It's the reversal curse. So the authors found that if you train an LLM with content like A is B, it cannot actually infer the reverse, B is A. So that's really breakdown of generalization on a deep level. And that's actually pretty surprising. Like even I'm typically pretty skeptical of LLMs, so I was pretty surprised with this result. So one thing to keep in mind about these failure cases is that specific queries will tend to get fixed relatively quickly because the models are being constantly fine-tuned on new data collected from human contractors based on past query history. And so many of the examples that I show in my slides are probably already working with some of the state-of-the-art LLMs because they failed in the past, and so they've been manually addressed since. But that's a very brittle way of making progress because you're only addressing one query at a time. And even for a query that you patched, if you rephrase it or if you change names and variables, it's going to start failing again. So it's a constant game of whack-a-mole, and it's very, very heavily reliant on human labor. Today, there's probably between 10 and 30,000 humans that work full-time on creating annotated data to train LLMs. So, on balance, it seems a little bit contradictory. Like on one hand, LLMs are beating every human benchmark that you throw at them. And on the other hand, they're not really demonstrating a robust understanding of the things they're doing. So to solve this paradox, you have to understand that skill and benchmarks are not the primary lens through which you should look at these systems. So let's zoom out by a lot. There have been historically two currents of thought to define the goals of AI. First, there's the Minsky-style view, which echoes the current big tech view that AGI would be a system that can perform most economically valuable tasks. So Minsky said AI is the science of making machines capable of performing tasks that would require intelligence if done by humans. So it's very task-centric. You care about whether the AI does well on a fixed set of tasks. And then there's the McCarthy view. So he didn't exactly say what I'm quoting here, but he was a big proponent of these ideas, that generality in AI is not task-specific performance scaled to many tasks. It's actually about getting machines to handle problems they have not been prepared for. And that difference echoes the Locke view of intelligence versus the Darwin view of intelligence. So intelligence as a general-purpose learning mechanism versus intelligence as a collection of task-specific skills imparted to you by evolution. And my view is more like the Locke and McCarthy view. I see that intelligence is a process, and skill, task-specific skill, is the output of that process. This is a really important point. If there's just one point you take away from this talk, it should be this. Skill is not intelligence, and displaying skill at any number of tasks does not show intelligence. It's always possible to be skillful at any given task without requiring any intelligence. And this is like the difference between having a road network versus having a road building company. If you have a road network, then you can go from A to B for a very specific set of A's and B's that are defined in advance. But if you have a road building company, then you can start connecting arbitrary A's and B's on the fly as your needs evolve. So attributing intelligence to a crystallized behavioral program is a category error. You are confusing the output of the process with the process itself. Intelligence is the ability to deal with new situations, the ability to blaze fresh trails and build new roads. It's not the road. So don't confuse the road and the process that created it. And all the issues that we are facing today with LLMs, they are a direct result of this misguided conceptualization of intelligence. The way we define and measure intelligence is not a technical detail that you can leave to externally provided benchmarks. It reflects our understanding of cognition. So it reflects the questions that you're asking. And through that, it also kind of limits the answers that you could be getting. It's really the way that you measure progress. It's the feedback signal that you use to get closer to your goals. If you have a bad feedback signal, you're not going to make progress towards actual generality. So here are some key concepts that you have to take into account if you want to define and measure intelligence. The first thing to keep in mind is the distinction between static skill and fluid intelligence. So between having access to a large collection of static programs to solve known problems, like what LLM would do, versus being able to synthesize brand new programs on the fly to solve a problem you've never seen before. So it's not a binary, right? Either you have fluidity or you don't. It's more like a spectrum, but there's higher intelligence on the right side of the spectrum. And the second concept is operational area. There's a big difference between being skilled only in situations that are very close to what you're familiar with versus being skilled in any situation within a broad scope. So for instance, if you know how to add numbers, then you should be able to add any two numbers, not just specific numbers that you've seen before or numbers close to them. If you know how to drive, then you should be able to drive in any city. You should even be able to learn to drive in the US and then move to London and drive in London, where you're driving on the other side of the road. If you know how to drive, but only in very specific geo-fenced areas, that's less intelligent. So again, there's a spectrum here. It's not a binary, but there's higher intelligence on the higher generalization side of the spectrum. And lastly, the last concept is information efficiency. How much information, how much data was required for your system to acquire a new skill program? If you're more information efficient, you are more intelligent. And so all these three concepts, these three quantities, they're linked by the concept of generalization. And generalization is really the central question in AI, not skill. Forget about skill, forget about benchmarks. And that's really the reason why using human exams to evaluate AI models is a terrible idea, because exams were not designed with generalization in mind. Or rather, they were designed with generalization assumptions that are appropriate for human beings, but are not appropriate for machines. Most exams assume that humans haven't read the exam questions and the answers beforehand. They assume that the questions you're going to be asking are going to be at least somewhat unfamiliar to the test taker, unless it's a pure memorization exam, in which case it would make sense that LLMs could ace it, since they've memorized the entire internet. So to get to the next level of capabilities, we've seen that we want AI to have the ability to adapt, to generalize to new situations that it has not been prepared for. And to get there, we need a better way to measure this ability, because it's by measuring it that we'll be able to make progress. We need a feedback signal. So in order to get there, we need a clear understanding of what generalization means. Generalization is the relationship between the information you have, like the priors that you're born with and the experience that you've acquired over the course of your lifetime, and your operational area over the space of potential future situations that you might encounter as an agent. And they are going to feature uncertainty, they're going to feature novelty, they're not going to be like the past. And generalization is basically the efficiency with which you operationalize past information in order to deal with the future. So you can interpret it as a conversion ratio. If you enjoy math, you can in fact use algorithmic information theory to try to characterize and quantify precisely this ratio. So I have a paper about it. If that's interesting to you, you can check it out. One of the things I talk about in the paper is that to measure generalization power, to measure intelligence, you should control for priors and experience, since intelligence is a conversion ratio. You need to know what you're dividing by. And if you're interested specifically in comparing AI to human intelligence, then you should standardize on a shared set of cognitive priors, which should be, of course, human cognitive priors, what we call core knowledge. So as an attempt to fulfill these requirements for a good benchmark of intelligence, I've put together a data set. It's called the Abstraction and Reasoning Corpus for Artificial General Intelligence, or ARC-AGI for short. And you can think of it as a kind of IQ test. So it's kind of intelligence test that can be taken by humans. It's actually very easy for humans, or AI agents. And you can think of it as a program synthesis data set as well. So a key idea is that in ARC-AGI, every task that you see, every task you get is novel. It's different from any other task in the data set. It's also different from anything you may find online, for instance. So you cannot prepare in advance for ARC. You cannot just solve ARC by memorizing the solutions in advance. That just doesn't work. And ARC tries to control for experience because you're doing few-shot program learning. You're seeing 2 or 3 examples of a thing, and then you must infer from that the program that links the input to the output. And we're also controlling for priors in the sense that ARC-AGI is grounded purely in core knowledge priors. So it's not going to be using any sort of acquired knowledge like the English language, for instance. It's only built on top of 4 core knowledge systems. There's objectness, there's basic geometry and topology, and there's numbers, and there's agentness. So we first ran a Kaggle competition on this data set in early 2020 that produced several very interesting solutions, all based on program synthesis. And right now, the state of the art is about 40% of tests are solved. And that's very much baby steps. And that's a data set that's from before the age of LLMs, but actually it has become even more relevant in the age of LLMs because most benchmarks based on human exams and so on, they've already saturated in the age of LLMs, but not ARC-AGI. And that's because ARC-AGI is designed to be resistant to memorization, and all the other benchmarks can be hacked by memory alone. So in June this year, we've launched a much more ambitious competition around ARC-AGI. We call it the ARC Prize. So together with Mike Knoop, the co-founder of Zapier, we're offering over $1 million in prizes to get researchers to solve ARC-AGI and open source the solution. The competition has 2 tracks. There's a private track that takes place on Kaggle. It's the largest Kaggle competition at the moment. You get evaluated on 100 hidden tasks, and your solution must be self-contained. So it must be able to run on a GPU VM within 12 hours with good CPU as well. There's a big prize to get over 85%. And then there are prizes for the top scores as well. And there's even a best paper prize, 45K. So even if you don't have a top result, but you have good ideas, just write a paper, submit it, you can win some money. And there's also a public track, which we added because people kept asking, okay, but how do the state-of-the-art LLMs like GPT-4, Claude, and so on, how do they do on the dataset? So we launched this sort of like semi-private eval where the tasks are not public, but they're also not quite private because they're being queried by this remote API. And surprisingly, the state-of-the-art on this track is pretty much the same as on the private track. That's actually quite interesting. So what's LLM performance on ARC-AGI exactly? It's not very good. The state-of-the-art LLMs are doing, most of them are doing between 5% and 9%. And then there's one that's doing better. It's Claude 3.5. Claude 3.5 is a big jump. It's at 21%. And meanwhile, basic program search should be able to get you at least 50%. So how do we know this? 50% is what you get if you ensemble all of the submissions that were made in a 2020 competition, which were all brute force program search. So basically, if you scale up brute force program search to more compute, you should get at least 50%. And meanwhile, humans do like easily over 90%. The private test set was verified by 2 people, and each of them scored 97 to 98, right? And together, they can solve 100%. So, 5 to 21% is not great, but it's also not 0. So it implies that LLMs have non-zero intelligence according to the benchmark, and that's intriguing. But one thing you have to keep in mind is that the benchmark is far from perfect. There's a chance that you could achieve this score by purely memorizing patterns and reciting them. It's possible. So we have to investigate where this comes from. Because if it comes from a kernel of reasoning, then you could scale up the approach to become more general over time and eventually get to general AI. But if that performance actually comes from memorization, then you'll never reach generality. You will always have to keep applying these one-time human-guided pointwise fixes to acquire new skills. It's going to be this perpetual game of whack-a-mole, and it's not going to scale to generality. So to better understand what LLMs are doing, we have to talk about abstraction. Abstraction and generalization are closely tied because abstraction is the engine through which you produce generalization. So let's take a look at abstraction in general, and then we look at abstraction in LLMs. To understand abstraction, you have to start by looking around, zoom out, look at the universe. An interesting observation about the universe is that it's made of many different things, that are all similar. They're all analogous to each other. Like one human is similar to other humans because they have a shared origin. Electromagnetism is analogous to hydrodynamics, is also analogous to gravity and so on. So everything is similar to everything else. We are surrounded by isomorphisms. I call this the kaleidoscope hypothesis. So you know what a kaleidoscope is. It's a tube with a few bits of colored glass that are repeated and amplified by a set of mirrors. And that creates this remarkable richness of complex patterns out of just a few kernels of information. And the universe is like that. And in this context, intelligence is the ability to mine the experience that you have to identify bits that are reusable. And you extract these bits, and you call them abstractions. And they take the form of programs, patterns, representations, and then you're going to recombine these bits together to make sense of novel situations. So intelligence is sensitivity to abstract analogies. And in fact, that's pretty much all there is to it. If you have a high sensitivity to analogies, then you will extract powerful abstractions from little experience, and you will be able to use these abstractions to make sense of a maximally large area of future experience space. And one really important thing to understand about abstraction ability is that it's not a binary thing where either you're capable of abstraction or you're not. It's actually a matter of degree. There's a spectrum from factoids to organized knowledge to abstract models that can generalize broadly and accurately to meta models that enable you to generate new models on the fly given a new situation. And the degree 0 is when you purely memorize pointwise factoids. There's no abstraction involved. It doesn't generalize at all past what you memorized. So here we are representing our factoids as functions with no argument. You're going to see why in a bit. The fact that they have no argument means that they're not abstract at all. Once you have lots of related factoids, you can organize them into something that's more like an abstract function that encodes knowledge. So here this function has a variable x, so it is abstract for x. So this type of thing, this type of organized knowledge based on pointwise factoids or interpolations between pointwise factoids, it doesn't generalize very well. You know, kind of like the way LLMs add numbers. It looks like abstraction, but it's a relatively weak form of abstraction. It may be inaccurate. It may not work on data points that are far from the data points that you've seen before. And the next degree of abstraction is to turn your organized knowledge into models that generalize strongly. A model is not an interpolation between factoids anymore. It's a concise and causal way of processing inputs to obtain the correct output. So here, a model of addition using just binary operations is going to look like this. This returns the correct result 100% of the time. It's not approximate. And it will work with any inputs whatsoever, like regardless how large they might be. So this is strong abstraction. LLMs, as we know, they still fall short of that. The next stage would be the ability to generate abstraction autonomously. That's how you're going to be able to handle novel problems, like things you've not been prepared for. And that's what intelligence is. Everything up to this point was not actually intelligence. It was just crystallized skill. And the last stage is going to be able to do so in a way that's maximally information efficient. That would be AGI. So it means you should be able to master new tasks using very little experience, very little information about the task. So not only are you going to display high skill at the task, meaning that the model you're applying can generalize strongly, but you will only have to look at a few examples, a few situations to produce that model. So that's the holy grail of AI. And if you want to situate LLMs on the spectrum of abstraction, they're somewhere between organized knowledge and generalizable models. They're clearly not quite at the model stage, as per the limitations that we have discussed. If LLMs were at the model stage, they could actually add numbers or sort lists. But they have a lot of knowledge, and that knowledge is structured in such a way that it can generalize to some distance from previously seen situations. It's not just a collection of pointwise factoids. And if you solve all the limitations of LLMs, like hallucinations and brittleness and so on, you would get to the next stage. But in order to get to actual intelligence, to on-the-fly model synthesis, there's still a massive jump. You cannot just purely scale the current approach and get there. You actually need brand new directions. And of course, AGI after that is still a pretty long way off. So how do we build abstraction in machines? Let's take a look at how abstraction works. I said that intelligence is sensitivity to analogies, but there's actually more than one way to draw analogies. There's two ways. There are two key categories of analogies from which arise two categories of abstraction. There's value-centric abstraction and there's program-centric abstraction. And they're pretty similar to each other. They mirror each other. They're both about comparing things and then merging individual instances into common abstractions by erasing certain details about the instances that don't matter. So you take a bunch of things, you compare them among each other, you erase the stuff that doesn't matter. What you're left with is an abstraction. And the key difference between the two is that the first one operates in continuous domain, and the other one operates in discrete domain. So value-centric abstraction is about comparing things via a continuous distance function, like dot product in LLM, for instance, or the L2 distance. And this is basically what powers human perception, intuition, and pattern recognition. And meanwhile, program-centric abstraction is about comparing discrete programs, which are graphs, obviously, and instead of computing a distance between graphs, you are looking for exact subgraph isomorphisms, for exact subgraph matching. So if you ever hear like a software engineer talk about abstraction, for instance, this is actually what they mean. When you're refactoring something to make it more abstract, that's what you're doing. Both of these forms of abstraction, they're really driven by analogy making. It's just different ways to make analogies. Analogy making is the engine that produces abstraction. And value analogy is grounded in geometry. You compare instances via a distance function. And program-centric analogy is grounded in topology. You're doing exact subgraph matching. And all cognition arises from an interplay between these two forms of abstraction. And you can also remember them via the left brain versus right brain analogy, or the type 1 versus type 2 thinking distinction from Kahneman. So of course, the left brain versus right brain stuff, it's actually an image. It's not how lateralization of cognitive function actually works in the brain. But it's a fun way to remember it. And transformers are actually great at type 1, at value-centric abstraction. They do everything that type 1 is effective for, like perception, intuition, pattern recognition. So in that sense, transformers represent a major breakthrough in AI. But they are not a good fit for type 2 abstraction, and that is where all the limitations we listed came from. This is why you cannot add numbers, or why you cannot infer from A is B that B is A as well, even with a transformer that's trained on all the data on the internet. So how do you go forward from here? How do you get to type 2? How do you solve problems like ARC-AGI, right? Any reasoning or planning problem? The answer is that you have to leverage discrete program search as opposed to purely manipulating continuous interpolative embedding spaces learned with gradient descent. And there's an entirely separate branch of computer science that deals with this. And in order to get to AGI, we have to merge discrete program search with deep learning. So quick intro, what's discrete program search exactly? It's basically combinatorial search over graphs of operators taken from a domain-specific language, a DSL. And there are many flavors of that idea, like genetic programming, for instance. And to better understand it, you can sort of like draw a side-by-side analogy between what machine learning does and what program synthesis does. So in machine learning, your model is a differentiable parametric function. In PS, it's a graph of operators taken from a DSL. In ML, the learning engine is gradient descent. In PS, it's combinatorial search. And in ML, you're looking at a continuous loss function, whereas in PS, you only have this binary correctness check as a feedback signal. And the big hurdle in ML is data density to learn a model. Your model is a curve, so to fit it, you need a dense sampling of the problem space. Meanwhile, PS is extremely data efficient. You can see the program using just a couple examples. But the key hurdle is combinatorial explosion. The size of the program space you have to look at to find the correct program is immense. And it increases combinatorially with DSL size or program length. So program synthesis has been very successful on ARC-AGI so far, even though these are just baby steps. And so all program synthesis solutions on ARC, they follow the same template, basically doing brute force program search. And even though that's very primitive, it still outperforms state-of-the-art LLMs with much less compute, by the way. So now we know what the limitations of LLMs are. We know what they're good at. They're good at type 1. We know what they're not good at, type 2. So where do we go next? And the answer is that we have to merge machine learning, like this sort of like type 1 thinking with the type 2 thinking provided by program synthesis. And I think that's really how intelligence works in humans. That's what human intelligence is really good at. That's what makes us special, is that we combine perception and intuition together with explicit step-by-step reasoning. We combine really both forms of abstraction. So for instance, if you're playing chess, you're using type 2 when you calculate step-by-step, like you unfold specific interesting moves. But you're not doing this for every possible move because there are lots of them. It's combinatorial explosion. You're only doing this for a handful of different options. So you use your intuition, which you build up by playing lots of games, in order to narrow down the sort of discrete search that you perform when you're calculating. So you're merging type 1 and type 2, and that's why you can actually play chess using very, very small cognitive resources compared to what a computer can do. And this blending of type 1 and type 2 is where we should take AI next. So we can combine deep learning and discrete search into a unified super approach. So how does that work? Well, the key system 2 technique is discrete search over a space of programs. And the key wall that you run into is combinatorial explosion. And meanwhile, the key system 1 technique is curve fitting and generalization via interpolation. So you embed lots of data into an interpolative manifold. This manifold can do fast but approximate judgment calls about the target space. So the big idea is to leverage those fast but approximate judgment calls to fight combinatorial explosion. So you use them as a form of intuition about the structure of the program space that you're trying to search over, that you're navigating. And you use that to make search tractable. So a simple analogy that sounds a little bit too abstract is drawing a map. You take a space of discrete objects with discrete relationships that would normally require combinatorial search, like pathfinding in the Paris metro is a good example. That's a combinatorial problem. And you embed these discrete objects and their relationships into a geometric manifold where you can compare things via a continuous distance function. And you can use that to make fast but approximate inferences about relationships, right? Like you can pretty much draw a line on this map, look at what it intersects, and this gives you a sort of like candidate path that restricts the set of discrete passes that you're going to have to look at one by one. So this enables you to keep combinatorial explosion in check. But of course, you cannot draw maps of any kind of space, right? Like program space is actually very, very nonlinear. So in order to use deep learning for a problem, you need two things. You need an interpolative problem, like it needs to follow the manifold hypothesis, and you need lots of data. If you have only 2 examples, it doesn't work. So if you look at a single ARC-AGI task, for instance, it's not interpolative, and you only have like 2 to 4 examples. So you cannot use deep learning. You cannot solve it purely by reapplying a memorized pattern either. So you cannot use an LLM. But if you take a step down, lower down the scale of abstraction, and you look at core knowledge, the core knowledge systems that ARC-AGI is built upon, each core knowledge system is interpolative in nature and could be learned from data. And of course, you can collect lots of data about them. So you could use deep learning at that level to serve as a perception layer that passes ARC world into discrete objects. And likewise, if you take a step higher up the scale of abstraction, and you look at the space of all possible ARC-AGI tasks and all possible programs that solve them, then again, you will find continuous dimensions of variation. So you can actually leverage interpolation in that space to some extent. So you can use deep learning there to produce intuition over the structure of the space of ARC tasks and the programs that solve them. So based on that, I think there are two exciting research areas to combine deep learning and program synthesis. The first one would be leveraging discrete programs that incorporate deep learning components. So for instance, use deep learning as a perception layer to parse the real world into discrete building blocks that you can feed into a program synthesis engine. You can also add symbolic add-ons to deep learning systems, which is something I've been talking about for a very long time, but it's actually starting to happen now with things like external verifiers, tool use for LLMs, and so on. And the other direction would be deep learning models used to inform discrete search and improve its efficiency. So you use deep learning as a driver, as a guide for program synthesis. So for instance, it can give you intuitive program sketches to guide your program search. And it can reduce the space of possible branching decisions that you should consider over each node and so on. So what would that look like on ARC-AGI? I'm going to spell out to you how you can crack ARC-AGI and win $1 million maybe. So there are two directions you can go. First, you can use deep learning to draw a map, in a sense, of grid state space, grid space. So in the limit, this solves program synthesis because you take your initial grid input, you embed it on your manifold, then you look at the grid output, you embed it, and then you draw a line between the 2 points on your manifold. And you look at the grids that it interpolates. And this gives you approximately the series of transformations to go from input to output, right? You still have to do local search around them, of course, because this is fast, but this is very approximate. It may not be correct. But it's a very good starting point. You are turning program synthesis into a pure interpolation problem. And the other direction you can go is program embedding. You can use deep learning to draw a map of program space this time instead of grid space. And you can use this map to generate discrete programs and make your search process more efficient. So a very cool example of how you can combine LLMs with discrete program search is this paper. Hypothesis search, inductive reasoning with language models. So it uses LLM to first generate a number of hypotheses about an ARC task in natural language. And then it uses another LLM to implement candidate programs corresponding to each hypothesis in Python. And so by doing this, they're actually getting a 2x improvement on ARC-AGI, so that's very promising. Another very crude example that's very promising is the submission from Ryan Greenblatt on the ARC-AGI leaderboard, the public leaderboard. So he's using a very sophisticated prompting pipeline based on GPT-4o, where he uses GPT-4o to generate candidate Python programs to solve ARC tasks. And then he has an external verifier. He's generating like thousands of tasks thousands of programs per task. He also has a way to refine tasks, programs that seem to be doing, close to what you want. So this scores 42% on the public leaderboard, and that's the current state of the art. So again, here's where we are. We know that LLMs fall short of AGI. They're great at system 1 thinking. They lack system 2. And meanwhile, progress towards system 2 has stalled. Progress towards AGI has stalled. The limitations that we are dealing with LLMs they're still the exact same we were dealing with 5 years ago. And we need new ideas, we need new breakthroughs. And my bet is that the next breakthrough will likely come from an outsider, while all the big labs are busy training bigger LLMs. So maybe it could even be someone in this room. Maybe you have the new ideas that I want to see. So see you on the leaderboard for ARC-AGI. Thank you. Yeah, let's do Q&A. Questions? Yeah?
Yeah, so I was kind of following the public state-of-the-art approach, which is kind of sampling programs. So if you follow the public state-of-the-art, the approach appears to be kind of using an LLM to sample really lots and lots of programs, like thousands of samples based on one prompt, tens of thousands of samples. And it seems that the performance goes up, maybe if you go from 10,000 to 20,000 program samples, maybe goes up by 2%. And it didn't seem like there was necessarily a limit to that improvement, or other than like the massive amount of compute that you throw at it.
There would be. The improvement is not linear. So ARC-AGI is not difficult. I mean, for humans, it's extremely easy. If you have infinite compute, you can in fact solve ARC-AGI with brute force program search, right? If you have data center scale compute, that's actually doable. We already know that you can get at least 50% with brute force search. And of course, brute force search performance improves as you throw more compute at it. Part of the challenge is to be able to solve it with limited compute resources, right? On the public track, we don't have hard compute limits. So for instance, Ryan's Greenblatt solution is actually using a tremendous amount of compute. It's costing, I think, about 10K to 20K to actually run it in terms of API fees. So it's enormous. It's only doing 42%. If you were to just apply large-scale brute force program search, you could spend hundreds of dollars and get the same results, right?
So you think that performance, the nature of that is simply you're just approaching in the limit brute force search over.
And by the way, I don't think, because improvement is going to be logarithmic, I don't think you're going to get to like 85, 90% like human level performance just by scaling compute. You will need more compute than is available in the universe.
Thank you.
A very simple question. Do you have a program that solves it?
Do I what?
Do you have a program that solves the challenge?
No, not to human level.
And do you have some?
Yeah. I have some things that sort of work, yeah.
Okay.
Quick question, Francois. You said you think that the next breakthrough will come from an outsider, not from the big labs. But don't big labs like Google employ outside thinkers like yourself?
Yeah, so the way I see it, we used to have a pretty good amount of intellectual diversity in AI a few years ago. But the rise of LLMs and ChatGPT and this sort of arms race between the big tech companies to build the best possible LLM, that has kind of like led to an intellectual collapse where everyone is now working on the same things. And I think this is actually making progress towards AGI slower than it would have been otherwise. And I'll tell you, all the top entrants in ARC-AGI so far, they've been outsiders. They've not been like big tech labs. They've been, random people coming up with really interesting novel ideas. Sometimes these novel ideas actually echo what some of the big labs are doing. Like for instance, AlphaProof versus the currently leading solution from Jack Cole and his team. There's actually pretty strong parallels there.
Yeah. So thanks for the talk, and I think it's a fantastic initiative, and I've been following it since 2020 when it came out. It seemed like a quite brilliant thing. I still have a certain, I guess, an uncertainty whether this sort of generalization that you're measuring, while clearly it's an important thing to look at, and it's something that current AI systems don't do, I wonder if you could have a system that did score close to 100% on this, but yet was doing it in some more limited way to how people are generalizing. Like how confident are you that, you know, a solution that does at the human level on the ARC challenge would then be able to do the other creative acts of generalization that really smart people do, like say, invent new physics theories or new forms of music or something, which admittedly, these examples are things that most humans aren't good at either, but maybe humans do these exceptional things, do these by hacks of the same mechanisms ordinary people have, right? So
Yes.
I guess, do you think there will be like an ARC-2 challenge that measures some more ambitious form of generalization, or is this going to be enough to sort of
Yes,
human
these are very, very good questions. So I don't think the first system to crack ARC-AGI is going to be an actual AGI. I think we're going to get there before we get to AGI. So you can think of ARC-AGI not as a sufficient condition for AGI, but as a necessary condition. As long as we don't solve ARC-AGI, we do not have AGI. So it's a rebuttal to all the people who say AGI is already here. Another thing, you mentioned ARC-2. There is going to be ARC-2. ARC is a work in progress. Like I came up with it in 2019. I started working on it in 2017. It's a very crude attempt. It's the first attempt. As it came out and people started trying to crack it, we learned from that. We learned from that, and we want to reinvest these learnings into version 2. And then there's going to be version 3. And as time goes by, it's going to get more sophisticated, hopefully closer to real-world problems, and also more dynamic and open-ended. Like I don't think a good AGI test in the long term can just be this sort of like static input-output pair program synthesis data set. I think it's going to go much beyond that. And I want to tackle the problem of open-endedness as well. So I would say one thing that I'm reasonably confident about is that if you solve ARC-AGI, it means that you have at least a decent answer to the question of how do we make machines that can approach problems they've not seen before and figure them out. So you're solving this specific sub-problem of AGI. And I think that's going to lead to tremendous progress. Like that's, I would say, the most important problem that's blocking us from getting to AGI today.
Yeah, thanks. That sounds fantastic.
Yeah, I think we still have time for questions.
So I'll take the chance to kind of do the last question. A lot of ideas there that really resonated with my own thoughts, so thank you very much. So, and kind of in transition to our third contributed paper session, which is on causality. I know the first paper talks a little bit about experiential learning, as when babies learn and they begin abstracting concepts just by exploring the world. And I was wondering how you see that integrating into your ideas there.
Yeah, I have two kids. They're 3-year-old and 3 months old, respectively. And I think watching kids grow up is a tremendous source of inspiration for coming up with theories of the human mind. I think it's especially true between ages 1 and 2, I would say, because that's when cognition is still sort of like simple enough that you can see it in action. Past that point, it gets so sophisticated that what you're seeing is very, very difficult to see through. And before that point, it's also sort of like, sensorimotor affordances are not fully controlled. It's not quite like interesting enough, but at that point in time, it's really fascinating. And personally, I do see things in my kids that have kind of like inspired me towards certain solutions that are applicable to art. I think humans actually It's not like a controversial statement that I do think humans are capable of performing few-shot program synthesis. The sort of process that you would need to solve ARC-AGI. But instead of applying it to this sort of like IQ-like puzzles, we are just applying it to completely everyday situations. Like we set sort of like short-term goals, like you're a baby, you're like crawling on the floor, you want to get to an object. You set that goal. Then you enter this sort of like feedback loop where you know your current state, you can imagine the state you want to get to, right? You have this sort of like latent representation of your target, and you're trying to do planning between the two. So that's few-shot program synthesis. And you're trying to execute, then you kind of like restart the loop. So I think this is very much how human cognition works on a fundamental level. Yeah.
Okay. Thank you, and thank you so much. As I said, so the next session, the third contributed paper session, is going to begin. It's going to be a talk, it's a session on causality, causal reasoning. The first talk is from Barrick Cook, and he's going to give a talk on autonomous, intelligent reinforcement inferred symbolism. Barrick?
All right. Thank you, everyone. Thank you. Okay. All right. So we'll sync up my laptop with what we're seeing on the screen. Okay. So, welcome, everyone. My name is Barrick. And today I'm going to be doing an overview of autonomous intelligent reinforcement inferred symbolism, or as I call it, IRIS for much shorter. It is a novel causality-based way to perform machine learning by inferring symbolic rules from changes in its subsymbolic inputs. And it has several key advantages over classical reinforcement learning. Hey, that works. So I come from a game development background. And when we developers write code, we use if statements. So when coding a grid world game like this, we would say something like, if the cell next to this little bot is empty and the action is left, then let's move the bot to the left. But what if an AI could independently learn these types of rules? Could we see the same intelligent behavior that we can manually code into these applications and games? And how could an AI learn those rules? If we look at what values change from one state to the next, we can find everything that an AI would need. I need this clicker to work. Maybe. Next slide. Thank you. So down at this bottom, let's see if we have a, yeah, we do. So down at the bottom, this is the model that we are trying to create. And from observing that state change, the AI can create the following: that if a space is a bot and the space next to it is empty and the action is left, then that bot space will turn into an empty space. And likewise, if the empty space is next to a bot and the action is left, then the empty space will turn into a bot. So we end up with two rules: one that changes the bot into an empty space, one that changes the empty space into a bot. And when we apply these two outcomes together, we get the bot moving left. Now, we can use these same symbolic rules to make predictions about how the subsymbolic values in a world will change when an action is performed. We can then chain these predictions together into an action state graph, which gives the agent an internal world model that it can use to make plans, much like a Markov decision process. So from the current state, we get state 1, and then state 2, and state 3, and so on. But if you notice, this doesn't look right. That's because it has not yet encountered a wall. And because a wall is a different cell value than the empty spaces that it has experienced so far, it has a lower confidence in that prediction. And we can use that lack of confidence as a guide toward novelty, where it will learn new rules. And once it's made its plan, such as go see what a wall does, it sequentially performs each action. And as it takes these actions, it is comparing its predicted state to its actual inputs. And if there's a discrepancy, well, then it abandons its plan, creates new rules from these new observations. So when it does encounter a wall, it creates new rules. Has a different outcome. It doesn't do anything. And eventually, when it encounters a battery, it sees that it collects it and that its score increases. So if we give this agent the goal of increasing its score, it will build a state graph of predictions from the current state until it finds a state where its score increases. Anybody here know pathfinding A*? Same kind of thing. Then, as soon as it finds the state where its goal increases, it simply traces the route back through the state graph and performs the sequence of actions. But let's add a new obstacle, a locked door that requires a key to open, and a new input that we'll call keys, that represents the number of keys that the agent has collected. Now there are two cell values that it hasn't seen before, and it's also unable to model a path to the battery. So interacting with these new values in its world model results in low confidence predictions. By seeking those low confidence predictions, it learns that doors are walls. And a key increases one of its inputs, just not its goal of its score. But now that it has a key, all of its predictions have lower confidences, because it doesn't yet know what effect having a key has. So it will retry everything. It'll move in open spaces, it'll press up against walls, and update its rules accordingly. And when it tries the door again, the door opens, which gives it a clear path to its goal. And from these few interactions in one episode, it has learned that if it has no keys, a door is a wall, but if it has a key, the door will open. It would take reinforcement learning hundreds or even thousands of episodes in this kind of example to do the same. And unlike reinforcement learning, rearranging the layout or adding more objects has no impact on Iris's capabilities. It will instantly know that it has to collect the keys to open the doors, as it has learned the causal relationships between these objects. And in these examples, it's just breadth-first searching through the action state graph, or the world model, for its goal. But that's very inefficient and quickly runs up against the combinatorial explosion problem. This is where the dynamically calculated goal heuristic comes in. It is a calculated value of how far away a given state is from a goal that is based on whatever rules satisfy that current goal. So if its goal is to increase its score, the heuristic finds an appropriate rule where the score increases and calculates how far the given state is away from satisfying that rule. So if we're looking at the bot, a battery needs to be next to it. That's 5 spaces away. This value of 5 is fed back to the planning algorithm to tell it how close or far away a newly predicted state is. And it is used to guide further predictions. So if a newly predicted state is further away, that value could be 6, or if it's closer, 4. There we go. This also allows us to change the goal of the AI at any time. So if we switch the goal to decreasing its score, the goal heuristic simply finds a rule that satisfies this condition and performs those same types of calculations. So these calculations can be thought of as unconnected goal substates floating around in the action state graph. So let's see what that looks like. This is an example of how a state graph is formed and used. The starting state up there is state 0 on the left. And those unconnected gold substates that I was talking about are on the right. These are where the bot has to be, pushing the wrong button, for a particular action to satisfy the goal. Now some of those are possible and some of them aren't. It doesn't care. From the initial state, it starts to make predictions about the results of its actions, like move left. This creates a new state that we'll call state 1. The edges that connect the states are labeled with the action performed, the confidence of the prediction, and the resulting goal heuristic value. In this case, the bot is about 3 spaces away. There we go. Skipped ahead of myself. It's about 3 spaces away from the closest potential goal state, so that heuristic value is 3. And here it's predicting what move up will do and storing it as state 2. But let's say that it hasn't actually encountered an arrow before. So this might be the outcome, but its confidence of that prediction is lower. Well, if for some reason it's unable to reach any of these floating goal substates, it will instead choose this low confidence prediction as its end goal, where it will learn new rules from new observations so that it can incorporate into future plans. And essentially, if it can't figure out how to achieve its primary goal, it'll be driven by curiosity to learn new things that may help it achieve its goal in the future. But for now, it continues predicting. And it builds states 3 and 4. But it doesn't continue predicting from the low confidence state, because that prediction may not be accurate. So future predictions from there could also be inaccurate, and it would end up hallucinating. So as it's making predictions, it's prioritizing generating new predictions from states with the lowest goal heuristic, as that means it is closer to its goal. Since state 4 has the lower goal heuristic, it generates state 5 and 6. But both of these have equally good heuristics. That bot is same distance away. So it continues predicting down both branches, because it doesn't know which one might be better or not. So it predicts action state left, moving left, and it notices, okay, that's getting me a little further away from the goal, so that's not good. Well, what if I move up? Well, that results in state 5, which is exactly where I am. Nothing changed. Okay, that's a dead end. And predicting from state 6 results in state 8, which matches one of these floating goal substates. So it has reached its goal, and it predicts that it will increase its score in state 9. Then, once it's found its goal state, it just traces the path backward through the state graph to the current state and performs the sequence of actions leading from the initial state to the goal. To test the generality. Okay. That was interesting. To test the generality of this concept, we've tried it in several different types of environments. MNIST, which is a standard handwritten character image recognition benchmark, been around forever. Cart bowl, which is where the agent must balance a pole on top of a moving cart in a continuous physics-based environment. And, of course, this grid world puzzle game. Now, MNIST is interesting because there's no planning. It's just pure prediction. The agent is shown an image and a blank label. It has to predict what the label will be, and then it is shown what the correct label is to compare its prediction against. The conditions of these rules are kind of wonky here for some reason with the formatting, but they are the raw pixel values of the images. Well, first let's see how reinforcement learning does. A deep learning paper from 2022 shows a test accuracy after one training episode, right down here, a little under 20%. And it takes about 50 training episodes to reach around 95%. This is Iris's first episode through the first 60,000 character training set. By the first 100 images, it was up to 58% accuracy. At the first 1,000, 77%. And it ended its first episode at 91%. Then when we show it, the 10,000 character training set, it briefly drops from 100, just shy of 90%, and caps off at 93%. On episode 2 of the training result, or the training set, we get a consistent 98%, floats right around there. across all 60,000 images. The deep learning algorithm took hundreds of episodes to reach the accuracy that Iris achieved in 2. Now, cart pull is also interesting because it's a continuous action space, which kind of poses a challenge. We had to round the inputs to constrain the size of the rule set. And Iris completed the challenge after 32 episodes with a steep increase in capability and consistent success afterwards, compared to a deep Q learning result from 2020, which took almost twice as many episodes to complete with noisier results. Testing the puzzle game against reinforcement learning is not really possible. The level changes, the sparsity of rewards, complexity of the challenges are just too much for reinforcement learning to handle. And as my co-author, Patrick Hammer, talked about in the OpenCog workshop earlier this week, reinforcement learning stumbles once you introduce a single-step sequential dependency, such as requiring a key to open a door. And it fails entirely once you introduce a 2-step sequential dependency. And some of these puzzle games levels have 20 to 30-step sequential dependencies. And also, as Patrick demonstrated, the closest analog is the mini-grid benchmark, which takes reinforcement learning millions of episodes to learn one level, if it can at all. Whereas Iris completed all 13 of these episodes, or all 13 of these levels in one episode, and in only 4,612 time steps. That is an unbelievable improvement in training efficiency. Now, as cool as all that is, we have barely scratched the surface of the potential of this kind of machine learning. And it does have some limitations. For example, it can't yet model the behavior of other things, such as movements or actions of other objects or characters in a game. However, as Patrick and I have just very recently discovered, it can adapt to them, like when Patrick showed Nace chasing his player character. It failed to predict his movement, but since it was constantly creating new plans when its predictions failed, it was still able to very effectively chase him around. And it can't yet learn time-related causal relationships, such as time-delayed events, like take an elevator, for example. You can push a button, and sometime later the door opens. To Iris, pushing the button does nothing, and the door just opens randomly. Now, if the button lights up, it can make a weak causal relationship between the door never opening when the button is unlit, but opens randomly when the button is lit, which would prompt it to push the button, but it's easy to imagine situations where such a weak causal understanding would fail. And high-resolution environments with lots of inputs and lots of outputs take a lot of compute horsepower. So there are a lot of optimizations to figure out there. Perhaps combining Iris with convolutional neural networks or other techniques to handle perception. But despite these limitations, Iris already has many advantages over existing machine learning. It's continuously learning, it learns much faster, it adapts, and it incorporates new information. Its rules can consist of integers, strings, booleans, RGB values, whatever the task requires. The planning algorithm is completely separate from the learning, so it can be anything. It can be modified or swapped out during runtime. It can even have multiple planning algorithms running in parallel. And its goal can be changed at any time, so it can perform any number of tasks and easily and instantly switch between them with no additional training. Best of all, every option or every operation is 100% transparent. It can be logged and debugged just like a human-written program. We can see exactly how it's doing something and why. We can see its motives, what predictions it's making, what rules it's using, when and how it learned those rules, anything else that we want to know. And all of this without using any form of neural network. This is good old-fashioned AI that learns. Lastly, since publishing this paper, we have expanded Iris to work in Minecraft, which is another challenging continuous environment. So I'll be setting up a demo of that in the booth in the poster room next door, so feel free to come on by and see that in action. Thank you.
So next up is Dr. Arash, I hope I get his last name correct, Sheklar. He's going to talk on causal generalization and goal-driven analogy.
Hello, can you hear me?
We hear you. You can go ahead.
All right. So thanks everyone. Thanks for having me. So let me. Okay. So my name is Arash Sheikhlar, and I'm presenting our work, our paper entitled Causal Generalization by Goal-Driven Analogy. The authors of the paper are myself and Christian Torison from the Center of Analysis and Design of Intelligent Agents at Reykjavik University and the Icelandic Institute for Intelligent Machines, Reykjavik, Iceland. So let me briefly describe what I mean by each of these terms, causality and generalization. Generalization is an agent's ability to extend the scope of its knowledge, its learned knowledge, so that it fits new situations and tasks. And it requires hypothesizing new pieces of knowledge based on existing knowledge. And causality is the information about what leads to what under what conditions. And if an agent has a causal knowledge and causal reasoning capability, it can predict the outcomes of its actions and hypothesize the reasons for taking actions and the conditions under which the actions must be taken. So the research question we want to address is, how can AI agents generalize their causal knowledge? How can they generalize the important parts of their causal knowledge? Those parts that are relevant to the goal achievement of the agent. And our hypothesis is goal-driven analogy is the key. Goal-driven analogy making allows an agent to generalize only the aspects of the knowledge that are relevant to its goal achievement. And it makes the generalization more efficient and effective. So looking at our theoretical and methodological framework, we follow Turing's suggestion of building child machines and the principles of constructivist AI. Those principles are, the first one is learning controllers based on feedback loops. So we need agents that can interact with their environments and learn through feedbacks and create models of their environment. And they need to learn and perform reasoning based on the assumption of insufficient knowledge and resources, which implies that knowledge has degrees of truth and it's falsifiable. And it needs to follow, the reasoning must be ampliative, meaning that it needs to consider deduction, abduction, induction, and analogy all together when it performs reasoning. And that reasoning needs to be done in real time based on a temporal, compositional, scalable knowledge representation. So here, let's see what we mean by causality. Our representation of causal knowledge is based on the notion of causal relational models, which are small temporal falsifiable pieces of knowledge with a left-hand side and a right-hand side, LHS, RHS, and a confidence value between 0 and 1. And the left-hand side contains preconditions and commands at time t1 that leads to a change in the state of some properties at a later time at time t2. And LHS, RHS patterns are facts. Facts are commands. Commands can have this structure that a command can take in an entity, a symbol, or an entity and a value. And there's observation facts, which have the following structure: entity, property, value, time. And there's constraints, which are transition functions, logical conditions, and ranges of values. Causal generalization problem we're going to address has three aspects. So the first one is abstraction, which has to do with replacing entities and values with variables. Induction, which is about creating causal relational models, or CRMs, by any process. But in this particular work, we are focused on goal-driven analogy as a way of creating new CRMs that uses existing models, situations, and goals in order to induce new models. And then the other aspect is knowledge pruning, which is about removing irrelevant facts and patterns from the knowledge structures and making them more general in this way. So the goal-driven analogy idea is based on this common sense rule that under similar conditions, similar actions lead to similar outcomes. And its purpose is to induce new models during the goal achievement process. And the requirements for that is that the agent has to have some initial knowledge about the tasks that it wants to solve. And that initial knowledge, let's say it's a model, it's a CRM called M with the left-hand side, right-hand side, and with the confidence value. And then the next step is the familiarity computation based on a comparison at two levels. The first level is to compare the goal state with the right-hand side of the model M. And when they match, then the second comparison is between the left-hand side and the current situation. And then we will have knowledge pruning, which has to do with removing non-matching patterns from the model M. And that leads to creation of new left-hand side, right-hand side, new LHS and new RHS, so the LHS star and RHS star. And we use, it uses the LHS star and RHS star in order to create a new model, M star, with a new confidence value. And the confidence value, the new confidence value, depends on the confidence value of the original model from which M star is derived, and the familiarity value. So the familiarity computation is based on, so confidence value of a model, as I mentioned, is a number between 0 and 1. And therefore, since familiarity determines the confidence value, then the familiarity must be between 0 and 1 as well. And therefore, we can conclude that if the right-hand side and the goal facts patterns match, then the familiarity can be computed, can be calculated in this way. We have a ratio that we have the ratio of cardinality of matching patterns over all existing patterns in the comparison, and that gives you a familiarity value. So this analogy process happens during the planning process, as I mentioned, and it leads to creating different multiple models during the planning and goal achievement process, and that itself leads to creating multiple solutions for the same task. So we have implemented this goal-driven analogy mechanism in a causality-based general purpose control architecture called ERA, which is based on the principles of constructivism and non-axiomatic amplitude reasoning. And improves induction and abduction mechanisms in error by pruning model preconditions systematically and inducing new models during the planning process. So let me briefly describe the knowledge representation and reasoning in open error, which is the implementation of the error framework. So the first component is composite states, which are sets of simultaneous related facts. Those are the preconditions of the CRMs that are introduced. And there's causal models, which have left-hand side and right-hand side. On the left-hand side, there's commands, and the right-hand side, we have new states. And there's requirement models that connect composite states and command models by instantiating them. It instantiates composite states on its left-hand side and command models on its right-hand side. And the planning components in ERA system is based on forward and backward chaining. Forward chaining happens when input facts match the left-hand side of requirement models. That it matches the composite states that leads to making a prediction on the right-hand side, and the backward chaining happens when a goal fact matches the right-hand side of a command model that leads to creation of sub-goals on the left-hand side of its relevant requirement models. And induction mechanisms in standard open error are two mechanisms: change targeted pattern extractor, CTPX, which is triggered when a state changes as a result of issuing a command that leads to the creation of a composite state and a command model and a requirement model. And there's PTPX, which is activated when the prediction of a model, a prediction of command model fails, which leads to creation of a new composite state and requirement model. And our goal-driven analogy is integrated into open error, and it works in this way. It compares the sub-goals with the situation facts. The sub-goals, as I mentioned, are instantiated composite states, and some of them do not match the situations, and those non-matching components are pruned via the goal-driven analogy, and new composite states are created. CST stars are created, and also M requirements or requirement models are created that instantiate those newly created composite states with new confidence and new confidence values that is calculated based on the familiarity calculation that I described. And it induces that composite state, that new composite state requirement model, and uses that during the planning process when it is solving the task. And this algorithm over here shows the cases that can happen during the task, during the sub-goal creation. So the analogy process happens when the sub-goals do not match the situations or the right-hand side of the causal model of command models, which leads to generation of new composite state requirement models and creating new plans. So let's see how this mechanism works by a simple example. So let's say we can place robot arm and its task, so the experiment has two phases. So there's guided experimentation phase and there's task solving phase. In the guided experimentation phase, we teach the robot agent to apply two grab commands, grab type 1, grab type 2. Grab type 1 is applying grab commands with closed fingers. And let's say it's applied on C1, a small cube, and grab type 2 is applied on C2, a large cube, with opened fingers. And the observables are the size of the object, the shape of the object, the positions of the objects, and also if the hand is holding some things or not. So in this phase, in the guided experimentation phase, it learns some composite state requirement models and command models. And now in the task solving phase, in the second phase, it needs to be able to transfer what it has learned from the guided experimentation phase for solving new tasks of grabbing and releasing 3 new items, S1, S2, and SIL. So these are new items because their shape are different. So what the goal-driven analogy has to do is to prune the non-matching property, which is the shape here, and use the familiarity property, which is the size. I mean, S1 has a large size, S2 has a small size, and cylinder has a large size. These are familiar properties that should guide the agent in order to take the right action. For example, for grabbing a sphere, for grabbing S1, it needs to apply grab type 2. And that needs to be guided by the familiarity of the object. So we have implemented this in this example in a robot simulator called WeBots, which is connected to the Aero system. It uses Aero as its controller, and it sends data to Aero, and it receives commands in real time. And let's see what happens in the experiment that we did with it. So in the guided experimentation phase, it learns some composite state command models and requirement models. And now in the task solving phase, it has to autonomously grab and release these 3 new items on the right-hand side. This is a sphere that applies the right command. For the small sphere, it applies grab type 1, which is the proper command, and for the larger sphere, it applies grab type 2, which is, again, the right hypothesis. So let's see the composite state models that it learns in the guided experimentation phase. And in the task solving phase, the non-matching pattern, which is the shape, is pruned by the analogy mechanism, and it leads to creation of a new composite state that it uses in the task solving phase, and a requirement model that instantiates that new composite state with a new confidence value, and that confidence value is calculated based on the familiarity level. The familiarity value, I mean, it's 0.75, 3 out of 4 components match and therefore it becomes 0.75. So yeah, the simulation experiment as a proof of concept shows how this mechanism works, and the effectiveness of choosing the right models to generalize during the task solving phase. And our future work has to do with expanding the analogy processes implementation by incorporating comparisons in value spaces, in numerical value spaces, I mean, and the precise formalization of the concepts in the analogy, goal-driven analogy mechanism process that they introduced. And we will use it for more complex tasks in our future work. Yeah, thanks for your attention.
Or it's not usually at the end.
Hello?
Thank you, Arash. We usually do questions at the end as kind of a panel session. So hold on, and we'll bring questions after the next talk. So the next talk is Bowen Zhu, who's going to talk on causal inference in the non-axiomatic reasoning system, or NARS. Okay.
Okay, so hello everyone. I'm glad to be here to share our paper, Causal Inference in NARS. NARS is short for non-axiomatic reasoning system, which is a long-term project. Yeah, and it's well known in this conference. So in this paper, I will not show much details of NARS, but I will focus on this special topic, this special issue, causal inference. Yeah, in my presentation. And the authors are me and Dr. Pei Wang. So first of all, I think in the research of causal inference, there are two different goals. One is to develop the mathematical tools for scientists to estimate the strength of causal relations. I think like, Judy Pro, who is a famous scientist, yeah, and he's researching causal inference. And I think this is, in my view, it's their goal. And another goal is to reveal the mechanisms of causal inference in thinking activities in like human beings or any general intelligence systems. So indeed, for sure there are a trade-off between those goals, and I think in our work we adopt the second goal. So here's the comparison with our approach, the comparison of our approach and the traditional methods. So causal inference aims to evaluate the extent of truthfulness of implications provided by human beings, and this is what the traditional methods do, and I call it causal estimation. And a key idea is intervention in causal inference. And intervention is modeled by do calculus in Pearl's theory, aiming to adjust statistical bias through pure observation, as if action were executed. And in Pearl's causal theory, it assumes that future observation will follow the same regularity as the past, so many theories can be correct based on this assumption. And while in the traditional work, causal inference assumes that there has been a causal graph, and the only work is to estimate the strengths of the in each of the edges. So, but in causal inference, they don't know how the causal graph can be extracted from some data. So they define another problem, which is called causal discovery. And according to a survey, causal discovery problem is defined as recovering the true graph from the given data set, while the causal discovery is to reveal causal information by analyzing purely observational data. So, well, in NARS, it's different. It's a different story. So, causal estimation and causal discovery are unified in the same system because we don't think they are different. They are those two functions are executed in the same system with the same logic. So in philosophy, in NARS, causation is a fat concept indeed. So, but we adopt the major meaning of causation. For example, the major meaning of causation is prediction. So in NARS, causation is prediction, but plus some other demands in different contexts. For example, in physics, causation means prediction plus reproducibility. What does that mean? So in physics, a causal law should be true in many observations, and but in history, just one event, one observation can be viewed as a, causal explanation if it's good enough. So in NARS, causation is subjective rather than objective. We do not deny that there might be some objective laws which is designed by a certain creator of this world, but when humans and AGI systems try to understand those laws, then we have to describe them in our own language, then it becomes subjective. So in any cases, we can say that the causal relations understood by human beings are subjective. And under the assumption of insufficient knowledge and resources, future experience may overturn rules learned from the past. So future may be different from the past. That is why we don't agree with Judy Pro's assumption in which future observation will follow the same regularity as the past. I think this AIKR or ACRE is more appropriate for AGI research. And in NARS, no true causal graph is assumed, which is different from the traditional causal discovery research. By contrast, causal relations are learned for adapting to the environment. So also different from traditional methods, intervention is to collect new evidence via operations. The system must really do some operations rather than pretend to do them. So this is some comparisons of the NARS approaches with the traditional ones. And in our paper, there are some more discussions on the philosophical aspects. And I do not go through them here. And if you are interested, you can read that paper. So, but here I will provide some working examples. One example is at the sensory motor level, and the other two examples are at the more abstract level, and they all follow the same logic. So, the first example is the card pull game, and we let NARS to play this game, and we found that it can learn this kind of knowledge. So it's represented as that format. Under what condition, do what, and what will happen. This can be regarded as a kind of conditional reflex, and and this sentence can also be viewed as a preliminary form of causal relation. So after learning, and we checked the memory of the system, we found that it learns those two pieces of knowledge with a certain angle of that pole. The system should move left, and it will feel good. Or with another angle, move right, it will also feel good. And it's fully interpretable in this system. And the second example is Simpson's paradox. Since this example is too complex, I think I will not go through this too much details about this. But the major conclusion is in these examples is is to discuss whether a drug is beneficial for heart attacks or not. And our main conclusion is that the drug does harm to heart attacks from one reasoning path, However, it benefits heart attacks from another reason path, and those two beliefs are contradictory, so that it's a paradox. And it's our explanation to Simpson's paradox, yeah, which is, it's a parallel example with the, that famous book, The Book of Why. And yeah, so we just want to compare our approach to their ones. And the third example is about intervention and counterfactual reasoning. So we design a scene to explain those two terms in NARS. So yeah, in this scene, suppose we have a remote control for a TV, or when pressing a button, then the TV will display something. Yeah, P means press the button, and C means controller, D means display, and the battery, B means battery, yeah, battery for the controller, and R means infrared array, which is invisible to human beings. So, yeah, and in NARS, this knowledge can be learned by temporal induction. With an operation P, pressing a button, we will get D. The TV will display something. So this can be learned by the system through temporal induction. So the question here is pressing the button the cause of D, the cause of displaying? And for sure, because this is a kind of prediction statement, and in our theory, causation is prediction. So we can say that P is a cause of D. However, if you think it over, then you'll find that there's an explanation chain. So P causes L means light, the infrared ray, the light of the, in the controller, on the controller. And then the light causes TV's displaying. So this will form a chain. Then which is the cause of D? Pressing a button or the conjunction of pressing and light? So our answer is that in most cases, P is enough. Pressing the button is enough. It's a good enough explanation. However, when pressing the button, but the TV does not open, then the latter one is a better causal explanation. So here, causation is not a logical relation. And in logic, we just have temporal rules. And here, there's no true cause of TV's display, but there are satisfactory causal explanations. Then you can think about this situation, and some infants may never generate this kind of explanation. Pressing the button causes an infrared ray R, and infrared ray R causes displaying. And because a baby just doesn't know what is an infrared ray, right? And we can see it through our eyes. And similarly, an ill-educated adult may not know that pressing the button causes electric current, and the current causes electronic transitions in infrared ray emitting diodes, and electronic transition produce infrared ray R, and so on. So if you just dive into it, you'll get a longer and longer explanation chain. So there can be an extremely long chain for explanation. Nevertheless, in daily life, satisfactory explanations are enough to be viewed as causes. So then, given this situation, this scene, we can discuss what is intervention. Intervention is nothing but operation in NARS. So by operations, the system changes the environment to construct new knowledge or to collect more evidence for existing knowledge. And some knowledge might not be easy to obtain by pure observation. So in this example, if the system just doesn't press the button, it will never know that press the button and then the light flash will cause the TV's displaying. So until it actually executing that operation. So that is why we don't think that pure observation is suitable for many cases, especially in AGI. And counterfactual. So suppose that the system learns a piece of knowledge, which is with a battery pressing the button, then the light flashes. Suppose the system knows this. Then the system observes that the lack of battery, which is represented by this. This is a kind of Narcisse sentence, and not B means the lack of battery or no battery, and this is the fact. The fact the system observes, and then so that knowledge means with this knowledge, B P causes L, and this fact not B. Then how to interpret that knowledge? So it is interpreted as this. By pressing the button, if B were true, then L would be also true. So given that fact not B. And this is a counterfactual sentence, right? So suppose the system learns another piece of knowledge by installing a battery into the controller will have that battery, then B will be true. So given these two pieces of knowledge, this and this, I just put it here. And according to some inference rules in the logic part of NARS, it will derive this. So what does that mean? That means, this sentence means by pressing the button, if the system installed the battery, the light would flash. So this is also it derives a new knowledge, counterfactual knowledge through reasoning. So here, counterfactual reasoning exactly means reasoning with a statement that is contrary to the fact. In this example, not B is the fact according to its truth value, and B and P causes L is a basis for concluding what if B. So conclusions. We try to give a definition of causal relation. For sure, causal relation is the relation between a cause and an effect. It's too trivial. And then the question is, what is a cause and what is an effect? So here, a cause is kind of explanation, namely causal explanation of an event. And causal explanation is one of the various types of explanations. While a cause is selected among multiple premises of an event according to different contexts, this context includes like physics, economics, history, and so on. And so the event as a conclusion here is also named, the event here is named effect. So we have a definition of causal relation here. However, causal relation is not a built-in logical relation, since it's quite different from, it has quite different meanings under different contexts and domains. However, the original form of causal relation is prediction, and in different contexts, so in different contexts, some demands are attached to it, and it can be represented as a acquired term in acquired relation in NARS. And we have some working examples in this paper. which covers both the sensory motor level and the abstract level. So by intervention, the system actively obtains new evidence from the environment. And so that new knowledge is acquired, which cannot be done by pure observation. And counterfactual reasoning is about reasoning on the statements that are false actually, but it derives possible consequences as if those were true. So that's all, and yeah, thank you.
You can stay here. Okay. Barrick, come on up. And so we'll have about 10 minutes for questions for any of the panelists.
I have a quick question for regarding the talk on ERA, and I'm psyched to see some new stuff from ERA, which has always been one of my favorite cognitive architectures. Now, one of the things I always liked about ERA was its focus on sort of self-organizing, almost algorithmic chemistry-like dynamics. We have all these rewrite rules, rewriting each other in a sort of self-organizing way, and then networks and structures sort of bubble up from there, right? Now, what seemed to me in this usage of ERA to do planning, it's not as much like that. It's like a very structured bit of pseudocode doing planning using the rules within ERA. So I'm sort of wondering how this structured approach to making a sort of almost top-down planning algorithm within ERA, how that gels with the sort of bottom-up self-organizing approach to ERA-based cognition. Like, do we view these more structured plans as seeding some self-organizing activity that gives rise to more fleshed out plans or something? Or how are we thinking about this?
Hello?
There we go, we hear you.
Okay. So I'm honestly, I'm not sure if I have completely understood your question. Could you please repeat your question again, if that's possible?
Yeah, and it was a somewhat vague question, so apologies if it's incomprehensible by nature rather than purely for acoustic reasons. But it feels like within the way ERA and replicode work, one could approach planning in a sort of very bottom-up way, where plans would sort of bubble up from like autocatalytic sets of rewrite rules or something, whereas what you've described seems like a more top-down approach to planning with a sort of specific planning algorithm that's, I think of as more top-down in nature. So I'm wondering how that works. Like, how do these plans trigger like self-organizing activity within the ERA network? How do these plans connect to the other dynamics happening in ERA? Do they sort of seed broader self-organized plans or something?
I see. Okay. I think I got the idea. So it's based on the same idea that we have some initial knowledge, we have some seed knowledge from which the system starts its bootstrapping. It bootstraps its learning, and an important part of learning is to plan how to achieve the goals. And what we do here is to integrate learning and planning, and it creates new models and uses that during planning in order to gain more knowledge, and this way it can cumulatively add new pieces of knowledge to the knowledge base of it. So it's based on the same idea of self-programming and cumulatively improving the knowledge and adding new pieces of knowledge to the knowledge base. If that answers your question.
Somewhat. It seems like it's driving this self-learning in a more structured way than I've seen before with ARA, which is interesting, but different from having a planning process sort of bubble up from reflective self-learning, it seems like.
Yeah, that's I think I didn't get what you said.
Let us move on then. Sometimes long distance
All right.
isn't as good as face-to-face. Thanks for the answer.
All right. Thank you. Thanks.
I have a question about Iris. After François Chollet's beautiful presentation today, it's clear to everyone who watched your presentation that this is in many ways implementing some of the strategies that François is suggesting to tackle problems via program synthesis. And you also ran into difficulties and, when you are scaling with perception, and suggested adding something like the convolutional neural networks, which also alludes to some of the suggestions that François is making, is trying to map the space and basically finding solutions that are based on rendering the domain into some continuous manifold that makes it searchable. But if you think about ConvNets, they are not the result of human beings creating such a continuous space. Instead, they are a constructive solution. People did discrete reasoning to come up with ConvNets. And the same thing is true for the transformer. The transformer is not just some interpolation of ideas that somebody at Google had, but it's a constructive thing that was also built from the ground up by some kind of program search. And so what I want to know from you is, do you think that the strategy that François is suggesting is the right one, or is this building of continuous maps itself the result of some bottom-level program search? And then regardless of whether this answer is correct or not, do you think you can discover your continents or whatever other heuristics you need via program search, or you need to think you need to throw another paradigm?
That's a good question. Well, okay, that is a very good question. I do think that the potential of the hybrid approaches of like the two different systems that Francois was discussing with the continuous spaces of that, neural networks are so very good at processing and classifying and understanding, in a combination with this type 2 type of system like Iris, the combination and the cross-communication between these two systems, I think, can fill in the gaps that are missing or otherwise are problematic for systems like Iris. For example, I've mentioned that high-resolution environments, like if you take just a camera view, a live feed of a camera, that is every single pixel has to have sets of rules about what is going to happen with that particular pixel. And as you can imagine, that gets very complicated very quickly. So there's opportunity there to utilize neural networks in ways that can handle and process those continuous spaces and convert those into abstractions that can be then utilized by a system like Iris.
Thanks, Berik. We have one question. Let me see if we can get this. We have one question from the virtual attendees for Bowen.
Okay.
How do you know that the remote has batteries and the batteries are dead, rather than aliens that were turning the TV on whenever you press the button, but decided to stop turning the TV on for you?
Yeah, so in this, this is just an example I gave, and I suppose that it learns those knowledge. And of course, there can be some other, other possible causes of the displaying, and yeah, because it's a system with the learning ability. So if given some events to it, it can do some temporal induction, then it generates some other pieces of knowledge so that it will acquire new causal knowledge. Yeah.
Thank you. And I know we have more questions, but we need to go. We need to go to coffee break. We're already a bit behind. So.
Okay. Thank you so much to all the speakers. And a reminder that all the papers can be found on the website. And also during coffee break, if people want to go and there might take a look at the demo space as well if you have time. But we should be back here in about 15 minutes for the next keynote by Jordi Rose.
10 minutes.
think we should just. Welcome back. We'll start the final keynote before lunch, who will be Dr. Jordi Rose, who founded D-Wave Quantum Systems, Kindred AI, and his current company, and he's also CEO of, is Sanctuary AI. He earned a PhD in theoretical physics. And now the interesting part of the bio. We were just kind of talking about it. He won 2 Canadian National Wrestling Championships, won the 2010 NAGA World Championships in Brazilian Jiu-Jitsu, in both the gi and non-gi categories, won the BC Provincial A Beach Volleyball Championship with Jason Hall in 2003, was a past holder of British Columbia powerlifting records in deadlift, bench press, and total for the 105 kilogram masters division. And this is what I find the most interesting of all. For a short time, held the Guinness Book of World Records, world record for the most yogurt eaten in 1 minute.
Yes.
With that resume, Dr. Rose is sure to entertain.
Thanks. Yeah, that yogurt thing is the thing I'm most proud of. This is going to be a little bit different than the rest of the presentations that you're going to hear at the conference. I did that on purpose. I've done quite a few things that are kind of peripheral to AGI, I suppose. But before I started that, I was in the quantum computing field for a long time. I worked on the technical side of trying to build one. And that's a remarkable journey that you can ask me about at some point. What I do right now, which is not at all what we're going to talk about, is I build machines. Well, I don't build them. I'm the CEO of a company that builds machines like this. They're humanoid robots, and the AI control systems that run in them. Did I just stop the video by accident? Probably. Yeah, there are things that look like this. So the intent is to try to make machines that understand the world the same way we do and can act on it in the way that you'd expect a person to in order to do work. But we're not going to talk about that. What we're going to talk about instead is my beloved field of quantum computing delivering zero value to the world. It's, I haven't been in this field for 15 years. And when I left, I'm like, okay, you know, I did my part and passed the baton, and at some point, this is going to be a thing, and I'm going to cheer, and I'm going to say, yes, my child grew up, and it's now a productive member of society, and it, gosh darn, hasn't happened. The entire field, regardless of which particular approach you may be a fan of, is a giant failure. I don't know how more clearly to put it. There's been a lot of money that's gone into this stuff. The number of useful applications that have been developed that are clearly you want to use one of these machines to do is zero. And the people in the field, I find this so irritating, always talk about the future. So a sign of a toxic field is something that never delivers value, and every single article you ever read about it is, you know, a step on the path to. No, it's not. You either have done something interesting or you haven't. And this field, unfortunately, and you know, mea culpa, I was part of this, has not delivered anything of value. So, you know, I can listen all day long to people saying about, well, you know, in 10 years. No. Stop talking about 10 years away. It's stupid. Like, sometimes talking about things that are 10 years away is fine, but not after you've poured $50 billion into something and you've had 30 years to do it already. So basically what I'm going to do here is try to do 3 things. So the first is I'm going to give you some terminology to kind of set the stage for how people think about quantum computing in its use, not the actual physics of the device, but how you'd actually use it. Then I'm going to introduce the core idea that I'm going to share with you. And then I'm going to show you an example. So the thesis of what I'm going to try to do here is to try to demonstrate a useful application on a quantum computer. And if I can do that, or if anyone can do it, it will be the first. So this is a rather dramatic kind of moonshot kind of thing, I suppose. And this is not my day job. I just do this on like weekends and evenings. But the reason why I think this particular one, I've got it to the stage I have, is even back when I was doing this, I was obsessed with this idea. So I was like, this is a great idea. We should do this thing. And I was like, no, we're not going to do that thing. So now I've kind of like reached a point in my career where I can do whatever hell I want. So this is what I do on weekends and evenings. Okay, first of all, there's a term called supremacy. And basically what this means is that I take a computation, well-defined thing, a function evaluation or something, for which there's a claim that a quantum computer can do it better than any conventional computer ever could. Like not just today, but ever. So there's a split in the capabilities where the things quantum computers are really, really good at have reached a point where you just can't catch them anymore, like ever. So there are only a handful of claims that people have made to have achieved this, and all of them are under question. So there isn't a single claim anywhere that a quantum computer has done anything better than you could do classically that isn't under threat of being overturned. But the two ones that are probably the most well-known and the most have potential that they may actually be this use two different kinds of quantum computers. The first is the gate model, which is in some sense kind of the de facto standard for how you think about these things. And Google published a paper a few years ago where they used a problem called random circuit sampling. So this is exactly what it sounds like. You create a random circuit and you sample from it. So not very useful, probably, but it's a thing, and they claim that they could do this better than you could do it when you simulate it. The other one is the D-Wave stuff. They've also had a claim of quantum supremacy recently on a very different kind of problem that might actually be more useful potentially, and I'm going to talk a little bit about it. But none of these are certified correct. And any others that aren't this are also in that category. So the thing I want to point out here is that even a quantum computer, when it's run at its absolute maximum, when you don't care at all about what the problem is, just simulate yourself. So we were talking about this at dinner last night. Trees simulate themselves really well, right? So does everything in the universe. It's obeying laws of physics, which it is simulating. This is just a fact of everything. Quantum computers simulate themselves really well. These things are like that. They're the edge of the hardware capability that you can't do better than at all. Like it is the most squeezed juice out of the hardware that you will ever get. So this is why I call it a capability envelope for the hardware. These claims are at the limit of what you can do, regardless of any considerations of utility or whatever. And even that is not guaranteed to be the case today. But there are claims. So the second thing that I find much more interesting personally is whether you can take whatever the system is doing and use it for something that you care about. You probably don't care about random circuit sampling unless you're a giant weirdo that cares about that stuff. There are some people like that. But it doesn't have any uses as far as I can tell, at least in the conventional sense of the term. I like this definition of useful, like do something useful with your life. It sounds like a disdainful command. I don't know, I found that was funny. It's like something your grandma would say to you. So this quantum utility or advantage is a software and creativity challenge. So if the hardware is good enough to do something better than you can do conventionally, then it's up to us as a community of people who are creatives and can write software to figure out how to use it. So it's no longer a hardware challenge so much as a creativity challenge. Given this hardware, it does a thing, how are we going to use it? So this is a much more accessible problem than the first one, which requires actually building hardware and stuff. So the thing I'm going to talk about is a game. And I'm not sure if games are useful. I mean, it depends on how you characterize that word, I suppose. But I would argue they are for multiple reasons. They're everywhere. They go back in history thousands and thousands of years. It's in us as people to play games. And they're actually big business, too. So if you just consider, like, how much money could you make making a game, it's quite a lot. Like World of Warcraft, I think, has grossed almost $10 billion since it was released. And chess sets sell, $2 billion worth every country in the world every year. So games are also big business. But the thing that makes them most interesting to people like us is the fact that games are an ideal testbed for AI algorithms for a variety of reasons. And they do quite well. So even in games like chess, where they don't have a gigantic edge, they're still better than the best human players. And they have been for a long time. 10 odd years, a little bit more. So the few game terminologies, just so we're on the same page about what we're talking about. I'm going to be talking about a certain kind of game, which is the sort of game that chess or Go is, that has these properties. So some of them are more important than others, but these games are what are called fully observed, which means you know everything there is to know. It's a pocket universe that contains the game and its rules, and that's all you need to know in order to play. They're zero sum, so there's a winner, a loser, or a draw. They're deterministic, and in this field, that means something specific. It means that if you are in a state and you take an action, you always end up in the same state the state action state combination is deterministic. That doesn't mean there can't be randomness. Like, for example, in Monopoly, if you throw the dice, there's a random component, but it doesn't change this fact that when you start from a state and I roll a 7, I always end up in the same board state after I go 7 moves. Some of these, of course, don't have all these properties. Like, for example, poker is not fully observed. When you play, you don't know what your opponent is holding in their hand, and that's obviously a very important part of the game. In fact, it's central. And the last thing is we want to be able to have a model of the game, which kind of comes along for free mostly with these things in most of the games we play, but I just want to make it explicit. And all that means is that you can play games in a hallucinatory way. So there's enough known about the determinism of the game that you can actually trace games through all the way from the beginning to the end. Okay, so let's say we're going to build a game-playing AI for chess or Go or anything like this. The way that you typically do it, and there's very few exceptions to this, is that you play a lot of games. So this algorithm that I'm showing here is an example of one of the core fundamental building blocks of modern AI game-playing algorithms, Monte Carlo tree search. So you don't have to worry about too much about the details of this, but it's a stepwise procedure that you repeat over and over again that in the end of the day traces through a game state path down to the terminal state, that is the end of the game. We play chess and we get to the end. And then we evaluate who won, or if it was a draw. And then we backpropagate that up to affect certain numbers of these states that then condition which actions the system thinks are better to take from others from a certain state in order to win. So the goal is to win. So we can trace back down through the game. We play a game, me and you. We play against each other. We determine who won. Then we take all the moves that we made and make it more likely that you would choose one of the moves that led to your win condition than the ones that I chose that didn't. So this Monte Carlo tree search is an example of a building block that's in virtually all of these. The only exception I can think of where you don't actually evaluate the terminal state is if I just give you a bunch of games that have win-loss labels on them, and you use supervised learning to try to learn them. The problem with this, of course, is that all these games have these massive, monstrous search spaces. So even chess, which is reasonably small, is still so big that that number doesn't even exist in the physical universe, basically. Like if you took protons and you lined them up from the beginning to the end of the visible universe, that number is about the same as the number of board positions in chess, and chess is not a very big game. Go, for example, is monstrously larger, and what I'm going to show you soon is even larger than that. Okay, so this is kind of, in a sense, the punchline of the first part of this, and the heart of the idea. So if we're going to play a game, and I want to make it hard for you to build a game-playing AI, like including your own brain. We'll put that in the same category. I want to make it hard to play. What one thing that can you do for all of these games that are just going to completely stop any AI playing algorithm from learning? It's very simple. Make it hard to know who won. So if you can make this particular step computationally difficult, every single game-playing AI set of this sort has the same problem, is that it needs to play a lot of games in order to learn the rules of how to win. If it's computationally difficult to compute who won, you're stuck. I don't care how smart your AlphaZero algorithm or its derivative is, you gotta know who won, because that's the root of the learning of how to play games well. You need to be able to calculate reward. And if you can't, then you're stuck. So just as an aside, all reinforcement learning-based algorithms and all value-based algorithms, anything where you assign goodness to actions, this applies to. So if I make it difficult for an agent to compute reward somehow, then all this reinforcement learning stuff grinds to a halt, because it's the core of the thing. We always take for granted that calculating reward is easy, but it doesn't have to be, especially in a game where I make up the rules here. I can tell you what the game is. It's up to me. You can choose not to play it because it might be boring and stupid, but I can make up any game I want, and if I want to make this a condition of my game, you know, who's to stop me? So this is the end of part one of this presentation. The new kind of game is just like chess or Go or checkers or tic-tac-toe, except it's hard to figure out who won at the end of the game. And that particular hardness is exactly in the zone where the quantum computing people claim supremacy. So think of them as the bad guys. They're over there somewhere in that other room. And they're like, this problem, we're going to smoke you. I don't care what you do. My quantum computer is just going to annihilate anything you do. You can use every piece of silicon on the entire planet and run it for 1 billion years, and you will never be able to beat our quantum computer. Okay, that's the claim that they're making. Okay, let's make it the thing that computes the result of the game. Now, if you're right, and you use your quantum computer and some fancy AI stuff to evaluate the terminal states, your game-playing AI is going to obliterate anything that you can build with a conventional computer. So when we play this game, your agent will win every single time. Not because we aren't smart, but because the laws of physics somewhat preclude us from being able to build competent agents for this problem. So this is this is part of the reason why I haven't been able to let this problem go, is I don't really understand what this means. Because if you have, let's say in the abstract, you have a decision-making agent that wanders around in the same environment as you, and there's something that it can do better than you, in principle, that you can never catch up to. What does that look like? Well, this is what this is claiming, is that it's possible to build agents in the physical universe that do something better than you ever could, full stop. And not only you, but any machine that you could build that wasn't of this sort. So I think this is a very interesting idea. So now I'm going to go to the second part of this, which is introducing a specific game that has these properties. It isn't special in any way. I mean, you take anything where quantum supremacy is claimed, you make it the terminal state function evaluation, and then you figure out how to create a game around it. So this was basically the first thing I thought of. There are lots of things like this. So in this game, you start with a graph, so collection of vertices and edges, and it doesn't matter what it is. Any graph this will work on. And you and I will play 2 players for the first, but this actually generalizes to n players. We're going to take turns coloring the edges of this graph. So every edge is one of these lines, and we're going to choose one of 3 colors. You can color it gray, green, or purple. And what this means is that, and I'll show you an example, but just to give you a flavor. These are, actually, let me leave that for a second. We'll just say there's 3 colors that you can color. And the other thing is, once a game, you have to choose one of these vertices to be yours. It's you own it. And every player has to choose one vertex. And there's just one kind of weird condition is that if there's only one unselected edge, you have to choose a vertex just so that you don't get it stuck at the end. So I've shown 4 graphs here. The first 3 I've done extensive experiments on, and the last one is the target. So this one is ultimately where I want this game to sit. This graph is the hardware graph of the D-Wave chip that claims quantum supremacy on this problem. So it's hard to see, but there are these little dots. Those are vertices in the graph, and these blue things are the edges. So it's just like that, except it's super dense and it's hard to see what's going on because the numbers are very big. And you can see that the state space of this thing is astronomically large. So the number of terminal states scales like 3 to the number of edges. So you don't have to make a very big graph before the number of possible terminal states just explodes into some stupid number. Even the tiny ones, it grows pretty quick, even though you can still enumerate the ones on graph 3 if you have a lot of patience. Okay, so here's an example of how you play this game on this tiny, stupid toy graph. So you start off with just the graph itself, and then red goes first. So red has to choose either one of the edges to color or choose a vertex. So he chooses this edge to color gray. And then player 2 goes, and they're going to choose this one and color that purple. And then player 1 has to go now, and now there's only one unselected edge, so they have to select a vertex, so they select this one. And then the other guy has to do the same, so they select that one, and then the final guy selects the last edges and turns it green. So this whole process is how all of these games, this category of games work. We just alternate making choices. And this last thing is this thing called a terminal state, and there's some terminology here. We need something to determine who won the game. We need a rule to decide whether red or blue is the winner for this particular configuration. I'd call that adjudicating the terminal state. So we have to have technology rules that tell us for that thing who won. So I'm going to just basically do a small detour here into quantum computing stuff, not too deep, just to give you an idea of how these two things are connected. So a qubit is a 2-state system. When you measure it, you measure one of the 2 states, just like a regular bit. It's either 0, 1, up, down, +1, -1, whatever. And physically, the kinds of qubits that I'm used to are actually loops of metal that subtend persistent currents. So these are superconducting loops. The currents that flow in them are what are called persistent currents. They have quantized values. And in low energy configuration, you can make this device so that the currents flow counterclockwise and clockwise corresponding to the 2 bit states. And you can put those things in what's called a superposition. It's a quantum property of the system. This has been being done for 30 odd years. This technology is very well established. It's fairly easy to do this, and many, many, many people do this now. The other piece of thing we need to know is that when you have more than one qubit, you want them to influence each other. So in the D-Wave type design, there's another device, which I haven't shown, but it's also another loop, where you can think of the direction here as creating a magnetic field that threads the coupler and changes its parameters that then influences through the same induction coupling the other ones. So they're magnetically coupled. And you can tune the couplers to favor the alignment of these 2 qubits. So if one's down, the other one's most likely down, and so on. So that's called ferromagnetic coupling. So the green favors alike alignments. Purple is anti-ferromagnetic, so it favors anti-alike, so up, down, down, up. And if you turn it gray, that means there's no coupling at all, which means that all 4 potential bit states, all combinations of up and down, are all equally likely. So in the design of this type of quantum computer, this is the knob that you've got to play with. You can figure out what the couplings are between these 2 things. And in this case, going back to the game design, the color of the line is ferromagnetic, anti-ferromagnetic, or 0 coupling. So the D-Wave chips are made up of lots of these little loops. Every yellow guy is a loop like a qubit, and every line is also a metal loop. So the chip is just a bunch of metal loops configured in such a way that there isn't a lot of crosstalk and all the noise goes away and stuff. And there's lots of different types of graphs that you can think about. And the one that I care about most is this one on the edge, because that's the one that where the claim was made. Okay, so I'm just going to now walk you through some physics that's now going to connect the game to the hardware, the quantum computer. So the first thing is we want to know who won the game given this terminal state. Okay, so where do we start? Well, the first thing is we've made a map between these things in qubits and these things in couplers. And the couplers, remember, the purple favors anti-alignment and the green favors alignment. So if we look at the table of all of the possible states that these 3 bits can have, from up, up, up to down, 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 and we just count the energy, which is that thing up there. So ferromagnetic means you put a -1 in front of the product of the spin, so these are now like +1, -1 variables. So that guy's +1 and that guy's +1. You multiply it by -1, you get -1, you get a negative energy. So this first term favors those guys being the same. The second term, the 0, means we don't care about the relative strength of that. And the last one, the +1, means we want these 2 things to be opposite. So if I just compute that with these things being plus or -1 variables, here's the answer. And lower energies are favored. So this thing is called a Boltzmann distribution, which just basically says what is the probability of being in states that have these energies at a given temperature. And if I put the temperature to 0, it just means only the lowest energies ever enter, because as t goes to 0, only the lowest ones have any weight. I get this answer. So it's pretty simple. Half of the time I'm in this guy, and half of the time I'm in that other guy. So what does that look like? It looks like this. So this particular configuration has 2 states that you'll see, as long as you're only seeing ground states, with up, up, down. So you can see all of the constraints are met. That's the same, that's different. And this one also, that's the same, that's different. So these 2 states are both half likely. There's symmetry. It doesn't, there's nothing to prefer one or the other. We're almost there. So the last thing that we have to set up is a thing called a correlation matrix. So it's defined up at the top, and all this means is we're going to sum over the product of the 2 states. So if I want to know the correlation between, say, 0 and 1, what I do is I ask for the probability that they're both up plus the probability that they're both down, and if there are other probabilities, I enter them, and I get a number. So it's basically saying, conceptually, how correlated are the 2 things? So 0 and 1 are obviously fully correlated, right? Because if I measure 0, I'm always going to get the same answer as 1. So that's why it's +1. Whereas 0 and 2 are anti-correlated. These guys are always different. So that's why it's -1. This is actually the heart of the hard problem to solve. So skipping ahead a bit, this is going to be the quantum supremacy claim that D-Wave makes. They claim that this particular thing, they can do better than anyone else. So now we're going to turn it into a score for a game. And the way we're going to do that is introduce 2 things. The first is something called influence. So influence is the sum over the correlations for a particular vertex. So if I'm vertex 0, I can compute the correlation with 1 and the correlation with 2. And the influence is just adding those 2 numbers together. And the same for all the others. So this thing at the top just says, take all of the correlations for whatever vertex I care about, add them all up. That's the influence of my vertex. And you can think of it conceptually as being, how much does my vertex influence the rest of the vertices? So if I'm up, how many of them are up? If I'm down, how many of them are down? Do they follow me or not? So in one limit, imagine you had a giant ferromagnetic block where everything was coupled to everything else ferromagnetically. So if everything's up, everything's down, nothing else happens. Each vertex has immense influence because everybody is always agreeing with you, regardless of which state you're in. So that's the first thing. The second thing now, easy next step, is the score of the game is the influence of my vertex minus the influence of your vertex. So the question I'm asking is, who has more influence? And whoever has more influence wins. So this is a simple thing to do. We've already calculated all these things. And we then can now evaluate the terminal state. And in this particular case, this is a draw because the influence of 0 and the influence of 1 are the same. But if 1 had chosen this vertex, for example, blue would have lost. Because this thing is anti-correlated to the rest. If it has a decision, it wants to eat, it wants to go to steak restaurant, everybody says, no, we're going to fish. If I say, no, I want fish restaurant, everybody says steak. Everybody always disagrees with you if you pick this vertex. So that's a losing position. And that's the substance of how you evaluate the terminal states in this particular game. Now, connecting back to the hardware thing, the exotic, very obtuse, difficult to understand problem that only 5 condensed matter theorists in the world care about is quantum phase transitions in magnets. So this is how the company proposed to describe what they were doing. And the way it works is you start with all of these qubits, which you can think of them as little magnets with north pole up, north pole down. And you start in a state where that first term in this thing called a Hamiltonian, which is basically a description of the energies of the system, dominates, which means conceptually all of the qubits are in superpositions of up and down. So the starting position for any D-wave anneal is every single qubit is independent of all of the others. They're not coupled at all. And every single one is in an equal superposition of the two things. And remember, I told you that people do this all the time. This is an easy thing to do. If you have isolated qubits that don't talk to each other, it's very easy to do this. So that initial state is very easy to prepare. And a magnet person would call this a paramagnet. Because if I go in and I measure the system then, all of the system just randomly adopts ones and zeros. They just randomly form patterns. So there's no structure to the result when you sample. Now, the process that's used is called quantum annealing, where you turn that thing off and you turn on another term, which gives you these ferromagnetic and antiferromagnetic couplers. And we're going to ignore that term, which is the individual bias on the qubits. You can also polarize them one way or the other. We're going to ignore that. We're only going to focus on the second thing. So the way that computation works, you start with this full random state, and then you turn off the term that causes those superpositions while you're turning on this other term that defines the problem you care about. And these two things cross. So there's one of them dominates and then the other one dominates as the anneal proceeds. And the interesting thing about this is that if you do it in a regime which is not too fast and not too slow, you enter into a very, very hard to simulate result. So if you do this thing called a quantum quench, when you do this thing quite quickly, what ends up happening is it's very difficult to predict the distribution of the states that you sample from. It's not Boltzmann. So that Boltzmann thing with the e to the minus, that's not what it is. It's something else, and it's weird, and nobody knows what it is. And the only way to access it is experimentally because we don't have the theoretical tools to compute it from scratch. It requires solving the full Schrodinger equation for like thousands of variables, which is impossible. And even the best approximation techniques don't work very well. So when you quench the thing and you ask, what are the probabilities of measuring each of these states after the quench? For small systems, it's a little bit like a t equals 0 Boltzmann, but not exactly. There's a little bit of a difference. And for large systems, it looks nothing like you'd expect. And that's the thing that causes the problems, is that you can't figure out what the probability distribution over the states is going to be after you do this quantum quench in the system. So that's what they claim. And if the claim holds, that thing is really hard to calculate because remember, we're calculating spin-spin correlation functions. So you have to be able to sample, sample, sample. And for every sample, now we're measuring who's correlated to who. And if you can't calculate the distribution, you can't calculate the samples, which means you can't actually do that calculation effectively. So that's what they claim. And if that's true, then this thing is hard to calculate, which means you can't calculate who wins this game. It's a thing that you can do with a quantum computer and no other way. So if that's true, then this is a way to build an AI using essentially exactly the same strategies that we do today. So the one that I implemented was AlphaZero, which is a beautiful algorithm. By the way, if you have any coding chops at all, I highly recommend you do this from scratch because this thing teaches you an awful lot about an interesting way to use search and neural nets together. It's not that hard. Like, I'm not a good programmer or anything, and I managed to do this in a couple weeks just by myself, so it's highly recommended. So if you implement that algorithm, and the only change you make is you implement the rules of the game, which is pretty straightforward, and then you require that the terminal state be that thing I just showed you. You've got something that mixes the best of modern game-playing AI with the use of a quantum computer to evaluate the terminal state. So the quantum computer isn't doing anything weird. It's not like some, this weird stuff that people usually do. It's very simple. It's just a black box It's calculating a number. It's evaluating the score. It tells you the answer. That's all it's being used for. All the rest of it just uses all this Monte Carlo tree searching, neural nets, and the rest. And my claim is that if everything I told you is true, which it might not be, but if it is, this agent that I've built can't be beaten by any classical agent. So you will never, in principle, because of the rules of physics, be able to beat this thing that I just trained. It doesn't matter what you do. It doesn't matter what you do classically. It doesn't matter if you play by yourself. You will just never win at all. It's just so strange. It's a very interesting and weird thing. Now, there's a loophole that I've tried to exploit because I didn't want to do something really stupid and then talk about it, which I may have done anyway. But this is a potential loophole that I wanted to close. And I'm not sure I have yet, but the claim of quantum supremacy for the underlying problem is not exactly the same as the claim I'm making. Because the function that I'm calling is like not the actual hardware output, but a processed version. There isn't a lot of processing, but there's a little bit. And I wanted to see if you could spoof the output. So what this means is I come up with some classical adjudicator that always gives me the same answer as the hardware for the answer, that the evaluation of the game. And the most sophisticated way I could think of doing this is using a technique called simulated thermal annealing, which is related in some ways to the way the hardware works, except it's not a quantum thing. It's just annealing temperature in a Boltzmann distribution. And the reason why that might work is that even though the Boltzmann statistics are not correct, when you anneal fast enough, when you quench, the result you get is not the equilibrium distribution, it's something else. So when you quench temperature, it's the same. And it could be the case that if you tune the parameters of the quench, you might be able to replicate what the quantum computer is doing. So I wanted to see if that was true. So I did the following. I did like a pretty cool, like just a regular kind of simulated annealing deal. And then I started fiddling with the parameters of the algorithm. And the way that I did this is every single terminal state in the graph, so essentially asking if I can enumerate them, which means it's a pretty small graph. I sampled both from the D-Wave quantum computer and from the simulated annealing. I evaluated the score that both of those were giving. And then what I did, and this is a little bit sort of weird and tedious, but it's actually quite an important point. If the two scores disagreed, that's important. What I did is I asked, if I were to make them agree by changing the definition of a draw to the score is under a certain number, not 0, but like under some number epsilon, how big does epsilon have to be in order for them to agree? So for example, if the quantum computer says red wins, and the simulated annealing says it's a draw, I can change the result of this by changing the definition of what a draw is to make it so that the red would be considered a draw, by changing it from draw condition is the score is 0 to the draw condition is less than, say, 0.1 or something like that. So the question was, how big is this number? And then the thing I think is the right way to do this is the bigger epsilon is, the harder it is to spoof. And when it gets past a certain point, which is set by some extraction of statistics and noise from these sorts of sampling things, you can never spoof. So what this means is if it gets too big, if you set that condition to be a draw, the spoof is just not going to work. And so what I was looking for is this epsilon for these things. And so in my kind of end of the day sorts of things, what I found was that for the tiny graphs, I can spoof the quantum computer 100% of the time. But the larger ones is not clear. So this is a potential loophole that needs to be closed in this idea. But there is some hope that you can't spoof this machine. And I was hoping to actually present some results on this, but I don't think they're ready yet. But I've been sort of trying to do this with bigger graphs. Okay, so here's some, I'm going to end with some results here. So I implemented 5 agents for this type of game. You can play yourself. Random, which is just random. Monte Carlo tree search, just raw tree search. Game tree enumeration, which gives you an optimal policy. That's only possible if you can enumerate all the states. And this AlphaZero thing. And the way that I adjudicated the terminal states is I used an exact solver. So this crunch through the evolution of the Schrodinger equation. And also this tuned simulated annealing. And for the 10 vertex graph, the Schrodinger equation solver it takes too long to evaluate. So I just used the tuned simulated annealing agent. So here's the upshot. So for these tiny little graphs, you can find optimal play conditions where if you play either side, you can always play to a draw. So that's not unexpected. There aren't a lot of positions here. So both the optimal policy and the alpha zero thing never lose. This is evidence that the alpha zero policy is learning the optimal policy, although it's not a proof. On this bigger graph, I trained alpha zero for about 4 days on my home setup and got to a condition again where it draws against itself all the time. So this is, again, evidence that you can find an optimal policy for this size of game. And by the way, this isn't, again, very surprising. One of the tricks you can use here is exploit symmetries. And I didn't think about this before I picked the graph. I just picked it because it looked cool. But this graph has a lot of symmetries which you can exploit when you do something like this. Because like one game position is the same if you rotate it. And so there aren't actually as many terminal states as I'd originally hoped. But you can get to a draw condition. Now what I ultimately want to be able to do is draw a chart like this. So this was the AlphaGo, the alpha zero and AlphaGo zero training graph. So for chess or for Go, you can evaluate this ELO score, which is essentially how well do you do against your competitors. For this new game, it's a little bit challenging because there are no other players for the game to compete against except like random, which is kind of stupid. But I'm trying to figure out how to do this now, and hopefully I'm going to be able to show some kind of a graph here where the playing capacity of the system increases dramatically over time. Okay, so last thing I want to talk about is the things that need to happen next with this idea. So the first thing is, can you spoof it? Which means, is the quantum computer actually useful or not? And I'm agnostic about this. It either is or it isn't. But one thing I'd point out is that the runtime on the D-Wave chip is on the order of nanoseconds per sample for the big graph. So those of you who've worked with like large graphs, a nanosecond per sample on a graph like this, you cannot beat with any conventional thing just because you're competing against the inherent parallelism of an analog solution. So the thing is very, very fast. So even if you could spoof the result, if it took you, say, 3 minutes to do something that takes a nanosecond, you're done. Because you have to call this thing like 1 billion times in order to train an AI. So what I'm going to do is I'm going to start picking increasing size subgraphs of this thing, train these AlphaZero agents with and without the quantum computer adjudicator. And then if I can convince myself that the quantum computing run AlphaZero just is annihilating everything else I do, including the spoofed AlphaZero with the simulated annealing backend, I'm going to run a tournament and I'm going to give a prize. And this is my own money, so I'm only going to do this if I'm absolutely sure that no one can beat this, or at least I get as sure as I can. Thanks.
Thank you, Jordy. That was just fascinating. Questions? We have one over here, Haley.
Great presentation. First of all, it's a small world. I think you were my son's wrestling coach in Vancouver. And secondly, I actually had used D-Wave's quantum annealer to make a virtual agent in social VR and a world recommendation engine. So I've had some of these use cases. I used the energy minimization kind of thing with the Boltzmann thing.
Yep.
So happy to show YouTube of that to you and anyone else. So there's stuff similar, some overlap going on. And
yeah, it's great that people are working on it. The thing about that sort of thing is that the thing I'm after here is a little bit different. I know that you can use these things to do interesting things. What I'm looking for is that quantum advantage thing. Is it the only thing that can do the thing? Because most of these things you can compete with, other stuff. That's fine. But what I care about is something that you just can't do in principle using conventional stuff, and that hasn't been shown yet.
Fair enough. Thank you.
Thanks for an interesting talk. I appreciate it. I am friends with Bob Cooka, so you know Bob.
Yep.
All right. So Bob and I have been kicking around this idea of actually building a quantum consensus mechanism. And I wonder, and the reason that's interesting for a number of reasons is because A, consensus is a very hard problem. B, it's not a general compute problem, right? We're not trying to build a general purpose computing. And C, quantum is really good at these kinds of correlations of state.
Yeah.
And finally, if we do what we think we can do, then consensus takes 0 time. And so that would seem to be something that classical consensus algorithms can't do. So I'm curious what your take on that is.
Well, nothing takes 0 time. You find that out when you do robotics. There is always a cost of mapping what the hardware is doing effectively, this like bleeding edge, to anything that isn't exactly itself simulating itself. So my view is that if you pick something that isn't it simulating itself as the first thing that you use it for, you're paying a penalty. And if the hardware isn't even clearly good enough at that, it's not a good idea. So this is my own personal view. It's mostly because I'm not invested in this field anymore. I actually literally don't care about any of these things except in like intellectual curiosity. So I think that my view is you do the thing that the thing does best. That's the problem black box you've got to work with. You can't cause any mapping cost. You have to use it in its raw form until the technology matures, if the technology matures well enough to be able to be so powerful that you can eat the cost of doing the problem mapping into it. So this thing I'm showing you here is a little bit like a consensus thing, in that you want more consensus for your vertex than the others. So there might be something there, but I'm always wary of these sorts of things because of the hidden costs of the map. Like, for example, the hardware graph. So the graph that I'm showing you here has to be embedded into the hardware unless you have the freedom to just choose the hardware graph. And the embedding is generally n² cost. So you only get square root of the number of variables, and even then you lose capability because you have to chain the qubits together in order to make that work. And the chaining process has defects in it, so there's a cost you have to pay to do anything that isn't the raw hardware.
Yeah, thanks for that great talk. I learned a lot, but I didn't understand one thing, which is the actually useful part. Like if you could get this thing to play the game,
yeah.
Didn't you just show that you've transformed supremacy from one domain into another kind of weird domain? But I didn't get who it's useful to, who would be like, yay, I have this game playing machine.
Yeah, I mean, it's a good question, and that's why I flashed that thing about the definition of usefulness, because I think usefulness is maybe in the eye of the beholder, but I kind of asked the same question about the AlphaZero algorithm. Like, okay, I can play Go better than any person. Is that actually useful? I think the answer is no, but it doesn't mean that it isn't potentially tangentially useful, because the algorithm, combining neural nets and search, could be useful in a whole bunch of other ways. So I think my definition of usefulness is maybe a little bit more broad than most people. I think for me, useful means I'm interested in it. So I think that if you can build a situation where you have a 2-player zero-sum game where one of the agents always wins because of some fundamental character of the physical universe, that's got to be useful. So even if the initial use case is just a stupid game where you color edges, graphs are everywhere. We were talking about morphic resonance and patterns and stuff last night, and I think that part of the reason why certain patterns reoccur is they're a function of the way that our world is constructed and the way we understand it. And we understand things as objects and connections between objects. It's a fundamental way that our brains work. So these graphs are objects and connections between objects, and the gameplay is on that structure. So, use your imagination. Like, graphs could represent a lot of things, and if you can do problem solving on graphs that are connected to games, who knows where it will go. I think most like creative innovations happen at the edges, where some weirdo like me who has nothing better to do starts pulling at a thread, and 9 times out of 10 or 999 times out of 1,000 it doesn't lead anywhere, but every once in a while it does. So this one I don't have any dog in the game. I want it to work. You want it to work. I don't really care. It's more just an intellectual curiosity thing for me at this point. So I concede the point. Maybe building a game playing AI is not useful, but it's interesting, I think. So maybe that's one level down.
Yeah, I started thinking about one way in which this could maybe be useful, which would be fun. It would depend on the scale at which you could do it. But there was a paper 4 years ago or something at one of Joseph Urban's AI for theorem proving conferences, which was learning theorem proving through self-play. And they were trying to use AlphaZero algorithm for theorem proving, where you have 2 players, one of whom is suggesting theorems, and the other is trying to prove the theorem. Right? And if they can prove the theorem, they win. If they can't prove it, then the conjecture wins. Right? And this was an attempt to get automated theorem proving to work without a corpus, right? So it's sort of like a GAN philosophy or something, but it's not a GAN, right? It's just a proposer and a prover. But that's literally using AlphaZero to try to do theorem proving. Now it was just a fun paper. I haven't seen that take off big time, and you could think about ways to combine that with more corpus-driven theorem proving as well, right? Where you could start the theorem constructor and the theorem prover guys with some knowledge if you wanted, rather than starting them from nothing. But just throwing out there that you can try to view mathematics as a 2-player game of this sort, which is evidently a more useful game than Go. I'm not sure what would the practicalities be.
Yeah, the important point that Ben, is sort of related to what Ben said, I don't know if you guys know how AlphaZero works, but it works entirely using self-play. So there's no human knowledge injected in about the quality of gameplay, which is really fascinating. Like the thing, and there are variants of it where the system actually learns the rules of the game as well, this mu0 thing. So you can use these things in very, very generic situations where you don't have any a priori knowledge at all except some basic facts about what you want the domain of the thing to be. So that's a good point, is that this is what I mean, is like playing against someone else is such a general thing. Again, it goes to this creativity and software challenge. Like assuming you've got a piece of gear that does something, how do you use it? So that's where the creativity and weird ideas end up being the ones that end up being the breakthroughs.
Thanks. So just to react to what Ben was saying, like we have been programming AlphaZero style theorem provers for like 6-8 years now, and it's doing something, but it's sort of a one player game quite often. And what Ben was saying is that with some conjecture you could turn it into a two-player game. I would say one area where I do not totally understand your game, but one area where it sort of feels slightly similar to what some of our people are doing is Ramsey graphs. Like when you basically there is this class of strange graphs where you are aiming for some bounds on the size of cliques and anti-cliques.
Yeah.
And this is
Ramsey numbers, Ramsey graphs.
Yeah, and this feels a bit similar, like with these colorings that you are doing, and like we are now actually doing some sort of AlphaZero style stuff, like a bit similar to what I was showing yesterday with OEIs for finding bounds on interesting Ramsey graphs, and I'm sort of wondering whether this could be used for that, but it's very unclear to me at this point.
Yeah, why not? I mean, I think it does take a little bit of luck that the thing you're interested in works in this context. But, you know, Ramsey numbers and things like them are very natural for this type of hardware. Independent set is a very easy problem to map into this thing. You know, cliques are just the dual independent set. So there's something there. Although I think like evaluating Ramsey numbers is probably even less useful than playing a game, I think, maybe.
It's a matter of aesthetics.
Yeah, I suppose it's an aesthetic question, but yeah, no, I think all this graph theory stuff is an interesting point, right? So usually when you do optimization on graphs, you use all the stuff that people have come up with for finding low energy states. But why couldn't you use some kind of adversarial training, like an AlphaZero style thing, to solve graph theory problems? So just like Ben said, you know, you have a guy who's doing one thing and a guy who's doing another thing, and somehow they learn from each other and they escalate the knowledge they have about the thing, and then at some point reach some level of play that solves the problem. I'm totally bullshitting here, but it could be the case that something like that could be true.
I had one quick sort of comment on, like I'm totally happy with AlphaZero Monte Carlo tree search, and I think it's a very good algorithmic approach. But I have one quick comment to your slide saying that it outperformed like the best chess engine. This is what DeepMind says, but like in Go, I'm totally sold. In chess, people are sort of contradicting it, and for example, the best chess playing engine today isn't even using deep learning. Like they are using much faster neural networks in that. So like, don't totally buy into like all this DeepMind hype. Like they do it really well.
Yeah, I mean, that's fair. I mean, I'm not an expert in this sort of thing. I think that it's fair to say, though, that it plays quite well. I think who plays the best in chess is kind of a little weird thing, because even the best things lose still. Like those ELO numbers are not that different. So yeah, it still does pretty well. And being able to learn a game without any guidance at all just is very interesting, like this bootstrapping method. Because like when we were trying to do really hard problems, there's this idea of you put a bunch of prior structure on the problem, then you start from there. But what if you didn't have to do that? So there's a whole bunch of ways that search combined with policy and value networks can be applied across all sorts of different things. I'm surprised that people haven't done more integration of search algorithms into large language model type things, because you'd imagine that that would be a natural thing to try. Maybe people are doing it. I'm not really up to date on what's going on in that field, but yeah, search is pretty powerful.
Thanks very much, Jordy. We have one more question online, but I'll ask you offline. I think it's time to go for lunch. So everybody online was very appreciative, and perhaps we could all show Jordy some appreciation as well.
Thank you.
And we can meet, the lunch is out in the foyer, the area outside, and we'll meet back here in an hour and get started with David Spivak. welcome back, AGI-24. We're going to get going here in just a moment. Let a couple more people trickle in for this amazing keynote that's about to get started. I want to...
Round up more people into the room. I think I got everyone. Not quite everyone. Trying to use my role as the conference chair to intimidate people coming into the room. Well, I'm the AGI chairman. All right, I'm the former conference chair then. Yeah. All right, welcome back from lunch, everyone. Hopefully it was a good time to catch up and discuss AGI in the morning's talk. So it's my great pleasure to introduce our next speaker, David Spivak, and we've talked about David talking at the AGI conferences for a few years now, I think, and now finally schedules and geolocations lined up, and we have a keynote from David. I've been following his work for a number of years. I mean, we both began in the mathematics field. I degenerated somewhat into the AI field, and he's stuck with that, with mathematics more closely. The PhD in math from Berkeley, starting with algebraic topology, and then turning more and more into a category theorist. A decade at MIT, and then recently co-founded the Topos Institute, which is an independent nonprofit research institute pursuing a whole bunch of different topics swirling around category theory, other sorts of advanced mathematics and their applications in different areas. I'd recommend a variety of his books on different topics. I mean, his book on category theory for the sciences, I've recommended to a lot of people who just needed a basic introduction on what category theory is. And his book on polynomial functors, which is written together with Nelson Yu, who keynoted at the AGI conference here a couple of years ago, is the definitive text on that topic. And more and more books and papers I'm not going to summarize now, but I think that the role of category theory, topology, various topos theory, these forms of math in AGI is something that's still being worked out. My intuition personally is that there's a lot to be found in this intersection, and so it's great to bring people from these portions of the math community together with AGI researchers to sort of work out what mutual cross-pollination that there may be. So take it away, David.
Great, thank you. Yeah, thanks, Ben. It's great to be here. I've had a lot of great conversations with people. So today I'm going to talk about, I was in fact, at a Buddhist monastery one time, and they just had this, before eating, they had this quote, all my relations. And that was the entire, instead of like some big long prayer, it was just all my relations. And I didn't know what I loved about that phrase, but somehow I thought, like, in math, a relation is just any two things. There's friendship is a relation, mother is a relation, part of is a relation. So I was thinking, like, wow, this is not just my ancestors, not just my friends, not just me, my relationship to my body or to the floor, like to the ceiling, relationship to my habits. This is all my relations, to books and to what science is, and to engineering, what is the difference, and all the relations that I make, all of them, including emotions and what's true and false and what's math, and all the relations at all. And then I looked at the center word of my, and I said, like, what is the my? Oh, the my is the center of gravity of all these relations. And so if you think about all of your relations, every relation you have, what holds them all together, that's you. But why would they say this before a meal? So that's like all your relations to everything in the world, and before the meal you say that,
because somehow you're about to eat something, right? And so what I thought was somehow they're trying to call into your mind all your relations because they're trying to say, like, don't forget, everyone, like you count on them, they count on you. What is this thing we're building together? They had no prescription of this is what you should do with all your relations, or this is why you should care about all your relations. They just said, all my relations. That's the whole quote. So I thought that was very, very beautiful. So what I want to talk in this talk, the way it's going to go is I'm going to start with philosophy and move into math. And my motivation is personal. As a kid, I just thought, like, well, obviously the goal of life is to have a good life, so what does that mean? And I didn't know what any of those pieces meant, but in some sense, I think I am deeply insecure. I didn't understand, like, why you're supposed to learn to stand instead of just playing with your toys. I thought that was like, oh, really? I need to do that? How did you know that I was supposed to learn to stand? I didn't know kind of how to figure out which was the right thing to do. And so when I finally found math, as like a 4 or 5-year-old, I was like, wow, that thing just works. It just keeps working, and I can count on it. So I think what I love about math is that I care about the philosophy of how to have a good life or what life is and stuff like that. But math is solid enough that, like, you can ground the philosophical claims in the math. So that's kind of why I'm using it. So I want to engage you. I'm here because I want help tracking something. I'm going to ask a bunch of questions in this talk, and then I'm going to kind of answer them, but they're not going to be the right answer, right? In some sense, they're the provisional answer, and I'm actually here because I want engagement and to understand, like, some of these difficult questions. So I think the thing I want to track, the thing I think is we're a little bit underdeveloped as a world is what care is. I think, the reason I was talking about all my relations, and I guess when I was preparing this talk, I thought I was going to ask you to consider all your relations, was to invoke what's at stake and what we're here for. Not just like, oh no, the doom of, like, it's all at stake, but, you know, the triumph or the beauty of, like, all the stuff that we have. So, right. In other words, I think whether you're excited about AGI or you're worried about AGI, in both, those are rooted in care. If you didn't care, you wouldn't be excited, or you wouldn't be doomy. So I think we need this open-ended investigation into this notion of care, and that's what this talk is about. I like short phrases that, like, pack a lot of punch. So the one I came up with that I thought was, I'll tell you about, is care tends to actualize potential. And all the words here are important to me. So when you hear care words, especially in this talk, I want you to know that I'm being deliberate with care words. So a care word is matters. What matters? Hey, what actually matters? Useful. All models are wrong, but some are useful. Well, you can't have useful if you don't care, right? If you didn't have a care, or something's important, or I'm worried about something, this is a problem. It's a real problem, so you care. It couldn't be a problem if you didn't care. If you say, I have values, you're saying, I care about this. So those are all care words. Robert Pirsig in Zen and the Art of Motorcycle Maintenance, he was trying to understand what makes a quality essay. And he's like, you should teach quality. It's like, yeah, but what forms quality? So he taught them all these tricks. But he found after the whole, I'm spoiling it here, but basically the point was that he noticed that when people internally did something they called care, it showed up externally as quality. And Heidegger said that the being of Dasein, in other words, the being of us, is disclosed as care. So he, in his investigation of himself, thought that the way that his very being was disclosed was shown to him was as care. So I think care is a very central concept. Another word here is potential. So potential and actual are kind of Aristotelian words. So potential is the possibility, what could become, what's potent, what's really got the potence, what's the real stuff there. This baby, it's got so much potential, what could it be? Or this genius kid from Guatemala, or, you know, from India. This person, they're so special, they're nice and they're smart, like what could they be in this world? This algorithm, I feel like it has so much potential, right? So potential, when you say, this experience that we have right now has so much potential. What's in this room? What's the potential of this room? What could be if only blah, 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 right? What could be if only we could just get everyone to
That's potential. So I think so potential is that, and then actualizing is what's here, what is actually acted out in the world. So people say actions speak louder than words, right? Self-actualization is the pinnacle of the Maslow's hierarchy. So being all you can be, reaching your potential, that's actualizing. And then the last word is tends. One way to read this is what tends to actualize potential? Caring about stuff tends to do it. Like if you actually care, that'll probably help. But another word based in tend is like tending to a garden. So what does care do to actualize potential? Let's say you wanted to actualize some potential for this baby or whatever. You care for them, you tend to them, you pay attention to them, you concern yourself with them, you attend them. So these attending, attention, these are all the same words. So how does care actualize potential? It tends. It cultivates the garden. So when you care, you just kind of sit with it, you attend it, you pay attention, and then potential gets actualized. So the problem I've cared about for the last 15, 20 years or so started when I read a book called The Moment of Complexity. And he said that, the author said that in 1993 or whatever, the world's brain kind of came online with the internet, and we all wired up. And he said that this is going to be a massive thing, and that more and more was going to be different. This book presaged fake news. I knew fake news was coming since 2007 reading his book. And he said that anomalies would become the norm, which is a kind of paradoxical contradiction. So I wanted to help, and I saw an opportunity because my math PhD, as Ben said, relied heavily on category theory, which organizes perspectives. Like different perspectives can each have their own world, and then translations between perspectives is what it's all about. And so I thought, well, if we've got this new brain where all these people are online now and they're connecting, and communication is becoming more and more important, organizing all that complexity is what we need. And so I thought category theory could help. And so the question that I've been working on is how can category theory help humanity make a better collective sense, get better collective sense? I'm reminded a lot of Czar's poster out there about collective collaboration and care are all we need. But so collective sense making. So people have been talking about Mike Levin a lot. He's very interesting biologist, and he says that all intelligence is collective intelligence. And I think in the same way, all sense making is collective sense making. The idea is that here we are collectively making sense of something together, what AGI should or could or will be. But also, and we're learning from each other. So we're kind of like, as you have this conversation over lunch, you start to understand how to have that conversation in a way that you're going to get a collective sense of what the discussion is. But also in your brain, there's all these little cells, and they're all making sense together. Each one has like, oh, I think I know when to fire. And then together, they make a collective sense. So if you have a sense of something, it's because it's a collective sense of your neurons. But humanity is kind of making collective sense. And so intelligence and our sense of things arise from coordinated activity. So so to use Mark C. Taylor, that previous guy's book, if he says that tweets and texts and TikToks, he didn't know about those, but are like neurons in the global brain firing, is the world thinking? And I'm not going to answer. I don't know if the world's thinking. I don't know if Yosha would say the world's thinking. But we do have videos and blogs explaining the situation in real time, each person giving their account of what's going on. And we could call this cultural processing. And I think that the point is that cultural processing is improving and getting faster. And people could say, it's not improving. There's flat earthers everywhere. But I think those are kind of bubbles through the system. Those are people who deeply distrust the science network, which I think is kind of okay, reasonable because of all the fraud that's happened. And they're not sure who to trust. So it's kind of bubbling up through the system. Like, so is the earth flat or not? And the way they work together, the way they make fun of each other, the way they congratulate each other on progress, et cetera, is cultural processing that they're going to have to negotiate whether the earth is flat or not. And I think that cultural processing is improving and getting faster, but I think that this is causing intense instabilities that seem to counter the improvements. And that I think we're going through a kind of phase transition, and we're going through some kind of metamorphosis, so it might start getting even more intense. And that we need something to help us take care of ourselves, because we don't know which way is up. We don't know what the good is exactly. I don't think there's a global notion of the good that people all agree on. And we don't know how to get right with ourselves. At least I don't. Sometimes I do things I'm not sure if it's right. And so to survive and flourish, we need to tend to this transition that we're going through. We need to tend to it carefully. So the question is, where can we turn to help us organize and balance this collective sense? Where should we turn if we're going to balance the collective sense of what to do about this transition? And one answer is that at least math helps organize our thinking. And so we can ask, can it be of use in helping us balance and organize the collective sense of what's going on? So maybe it's all stored in our heads. Maybe you have all these different things communicating, and each one makes an ontology of the world. I think that the most important thing for me is communication, whether it's like a deep love for somebody or a friendship or a collaboration. Communication is what makes that work. And when I'm most upset, it's because communication is failing. If I don't believe the climate scientists, it's because communication is failing. And so communication is super important. And everyone has, we can imagine everyone has a database in their head. Every cell has a database in it. Is that true? No, it's not true. There's no database in my head, but you could imagine it that way. And then you could have this schematic layout of how everything fits together, and tons of examples. You say, oh, I get it. Every dog has an owner, and a owner is a person, and a person has an address, and the dog lives at the address that his owner lives at, or something. And then you could put a table full of all the information of all the dogs you've ever heard of and all the people you've ever heard of, and contain databases, and you could pretend that that's what's going on. But that's probably not what's really going on, but still you could kind of get going with that mathematically and say, what we need to do is get everyone's database to talk to each other, not to be the same, but to be able to communicate to each other. And that's something that I was working on several years ago. You can make math out of that, and that's a thing you can do, especially with category theory. But you could say, no, it's not databases in your head. That's ridiculous. It's all dynamics. It's all dynamical systems. Everything is just a little machine with inputs and outputs. And your cells are machines with inputs and outputs. You're a machine with an input-output. A chair, its inputs are maybe all the ways you can put forces on it, and its outputs are all the orientations it can be in or something. And everything is just a dynamical systems interacting with other dynamical systems. And like you can have these little dynamical systems in these little boxes interacting somehow, forming bigger boxes and populations of neurons and brain regions, V1 talking to V2, and brains, and I'm talking to you, and just zoom in and in and in. Maybe that's what's going on. And so you can consider the math of interacting dynamical systems and say, is sense making just some algorithm that each of these little systems is running? If we're all, what was it, animism? If everything's just kind of imbued with some soul that's like running its matter, what's the rule for how they combine and talk to each other? And maybe even what's flowing through the wires, like when Ben says, and here's David, then who's talking changes and who you're listening to. So the wiring diagram itself, instead of just being fixed and soldered into silicon or into whatever, is changing based on what's being said. Like, okay, that's it, let's stop talking and move away from each other. So that sort of thing you could put in there, and again, there's math for that. But I think that there's still something really important missing in all this, and that's what the remainder of the talk is about. So in the remainder of the talk, I'll talk about motivation for sense making, and then actual math with potential to help. I don't know if it will. And then where I think we need to go. So, right, so abstracting computers. So in the 1930s, a computer was a person, right? There were these people called computers. It was like a profession. It was often a woman, often women, but all genders. And they performed calculations meticulously, right? They would try to follow the plot of a trajectory or a missile or a body in space. And they needed to make very few errors and do kind of Euler's method or some kind of figuring something out like thousands of times and like not make mistakes and do it fast. And so Turing took this and he said, I know what this is. The mechanical essence of this, and he called it an automatic machine, is that there's some instructions for when you read a symbol, where do you carry the one? There you have a limitless supply of paper, and he made these rules called a Turing machine. And that's what a computer has become. And so now when we say computer, we mean the automatic machine. But it misses a key element. And what made the women or the people do such a good job? And it's that they cared. They could not have done quality work, at least according to Persig, but also according to me, if they didn't care. So whether it was they cared about the paycheck for their family, or they cared about the mission, the making of the atomic bomb, we need to do this before the Germans, or they thought the math was just super interesting, the quantum mechanics, whether it's the men doing, or people doing the atomic bomb Manhattan Project, or people doing that we called computers. There is interest, there is mission, there is something that made them care, and if they hadn't cared, they would not have been able to do it. And in Turing's extraction of this, he did not capture that aspect, right? He missed that part. And he skipped it in the same way that Claude Shannon skipped meaning. When he defined information, he's like, oh, by the way, I don't mean meaning. When I say information, I'm not talking about that. And in some sense, that makes the math easier to write down, but it makes it harder to, you're missing something, I think, important. And so we still don't really know what meaning is, and we still don't really know what care is. But I think that they're very important. So I think what we've done since then is we've scaled up this uncaring mechanism, automatic machine, by 10 times, then 10 times, then 10 times, then 10 times, then 10 times, 10 times, 10 times, 20 times of those. But it's still the living who care, right? It's still you who type into ChatGPT what you care about, and it answers it. You're the one who OpenAI plugs in the server. It's us who cares to make those machines. And this essential piece, this interest, oh, you just pop in a goal. Just pop in a goal into the machine. Well, where'd the goal come from, right? There's something about goals that it's not quite so easy as just, it could just be any goal, right? Something about our goals, I think that's what matters most. And I'm allowed to say that because I think matter is a care word, right? So if matter is a care word, then care is what matters most. So how does it work? Let me go into sense first. So, and before that, even the power law for physics, just so you believe me that maybe care is important in another way. So power is current times voltage, and I think of intelligence as the current. How much stuff is flowing per unit time? Like how much raw computing power can you put on this problem? That's kind of the intelligence. But then the care is more like the voltage. It's the potential difference. Like what could I get? What's the pressure difference? What could I get if I actualize this potential? That's your care. And so the power of something, if you want to hire someone, they don't care at all, but they're really smart. They might not really do a great job. Or they care a bunch, but they're not very smart or something. It's not going to work. So somehow, intelligence without care would just be this dormant swamp with no direction to it. And care without intelligence would be like a high mountain, but there's no water. You can't run a water wheel. So I think care tends to actualize potential. And the way you do it when you attend to the baby or you attend to the algorithm or whatever is you start making sense of it. So this sense, I don't mean raw perception when I say sense. When I say sense, I mean something more like spidey sense. So a sense of danger, a sense of belonging, a sense of opportunity, a sense of humor, a sense of direction. Those things, you can't have a sense of direction by just the pure raw data. It's you have a sense of it. You're like, I feel like we're supposed to go that way, right? And you're tracking the right variables. You remembered the right things. You're still having the conversation, but because you have a good sense of humor or a good sense of direction, you know which way to turn and when, and you have the right timing because you're paying attention to the right variables. And then you can navigate it with ease. So as soon as you get the right way of looking at the AI architecture, then something comes into focus, and now you can navigate with ease in a way that you couldn't before. So consider this snapshot of two math students. I'm trying to give you a sense of my use of the word sense. And both of these math students, A and B, both want to succeed. But student A, what they're doing is they're carefully copying down what the teacher's writing on the board, formatting and all, commas in the right place, everything's perfect, same line breaks. Student B is doing the opposite. They're clearly frustrated. They're like, what? No, but this makes no sense. You said X, Y, Z, and that's A, B, C, and then what? They're trying, but that's a 6, and that's a 4. So how did you? And that frustration, but what are they doing? They actually, at some point they go, oh, wait, is it because of this? And then something something kind of seems to drop. They relax. They've accounted for everything. Things are fitting into place, and they say, oh, that makes sense. And now, because they make sense, they are now catching the teacher's typos. They're now doing well on the test. They don't even have to pay that much attention. They're doing their own thing. They're distracting the right variables. They know what to do. The other student, because they saw somebody make sense of it, they haven't made sense of it, they might completely stop caring and become distant. So it makes a very big difference whether you make sense, whether you turn all this crazy crap that's going on these slides, you actually make sense of it. It's just a completely different experience. So it takes work to make sense, but it produces sense. And one conjecture would be that, in fact, all of our sense of sight, sense of danger, sense of belonging or whatever, all of these things, they take work, but we start to get a sense. And those senses are really important for any kind of navigation, and which is what you need when you care about something. If you want to give the baby what they need or the algorithm what it needs, you need that sense. So when we want to track what we care about, when we want to track the baby's progress or what they need, when we're tracking criminals or tracking bears, right, we care about finding them. But in other words, tracking trains, putting a train on rails, right? Traction of the tires, right? The word track has a lot of good variance to it. So tracking someone's logic, if someone's are you tracking what I'm saying? Are you not tracking? Not getting distracted. If you get distracted, can you get back on track? So it's being able to follow something, right? So follow the bouncing ball, to stay with it as it moves, right? And so this ability to track something is, if you don't have a sense of it, you're not going to be able to track, did my character move left or did my character move right? So we want to make sense so that we can track what we care about. In order to track something, we need to make sense of how it operates. And so to care effectively for something requires, to care effectively for the baby requires we have a sense of it. And so what is this sense making? I think it might come down to accounting. So that what's going on is, and I think somebody the other day, maybe it was Ben or somebody or Yosha was saying this also, that somehow sense making comes down to accounting. When student B was trying to figure out what they were doing, they were trying to figure out how to account for X, Y, Z on the board. Like, how does this make sense with that? How do these add up? And we're seeking an abstraction that we can overlay on the current situation such that when we find it, things kind of sit in their proper place and it all kind of makes sense. And that's why we settle into it. So I think that sense making might be finding systematic ways of accounting for experience. So abstracting is kind of tracking the structural essence of something. We care about a particular case of a more general thing. So abstraction, people often think of as a one-way process, I think, but it's a two-way process. So when we use an abstraction, what's going on is we've got a particular situation that this particular garden is full of weeds, but then we extract, like Turing extracted this abstraction of the computer, right? We extract from it, the garden is full of weeds. Now we have the garden is full of weeds on a concept level. I can hand that to Bob the gardener, I can hand that to you, and say the garden is full of weeds. I don't have to show you my particular garden anymore. I've abstracted the essence of it. And now, just somebody who knows how to deal with gardens can say, oh, use a trowel. And then I can take that back and apply it to my particular experience and say, oh, I'll use the trowel that's right here on this weed that's exactly here. So it's not, if someone says that this table is a rectangle, and I know that one thing I can do with rectangles is turn them, then I know I can turn the table. So in the same way, if Turing says that this thing is a computer, and then anything you can do with a computer, you can bring it back and work it on silicon. You can work it on anything that abstracts into computer. You can pull back anything you can do with a computer, the abstraction, to the concrete scenario. So it's not this one-way street. And so the reason I'm telling you this about my notion of abstraction is two reasons. One is that I want to motivate category theory as a way of, as an abstraction language. It's perhaps the most abstract math. And second, this category of polynomial functors that Ben mentioned, actually, it's a part of category theory, but the way that polynomial functors work is this two-way process of going towards an abstraction, making a choice there, and then coming back. So, so that's the purpose of talking about abstraction. The goal was, again, to make better collective sense, of our world. But I think this mathematics is a systematic way of accounting for things. That's why we're moving into mathematics as we go down through this talk, because it's a systematic way of accounting for something we care about. And then hopefully we can take what we learn from the mathematics that I talk about here and bring it back to what we care about later. Okay, so, right. So to actualize our own potential, we need to be clearer about all our relations. Yeah, to actualize our own potential, I think we need to be clear about all our relations so that we can understand how to actualize what we have here in front of us. So category theory is roughly relational math. It's not quantitative, it's about relations. So it's about different structures and how they relate. Mathematical definitions in general, like what is a vector space or a group or a topological space, these are interlocking structures. You have a set and you have an operation and it's got these properties. And so category theory is tracking the layers of structure and their connections. It tracks it for you so you don't have to remember it all. It's holding it, it keeps it on rails for you. And that makes, by paying attention to structure, it makes analogies, which are similarities of structure, different content, same structure, that's what an analogy is, into a formal object. So it was invented in the 40s to account for something they were calling naturality. Mathematicians were considering certain things, like the double dual of a vector space, to be a naturally isomorphic to the vector space, whereas the single dual was not naturally isomorphic, but they didn't know what natural meant. They kept saying, this is naturally isomorphic to that, without knowing what natural meant. And so the inventors of category theory, Eilenberg and MacLean, set up the theory they needed to define natural transformations. They defined something called categories, and they defined something called functors, and from there they could say, now I can tell you what natural means. And Alexander Grothendieck used category theory to prove important conjectures. It wasn't just abstract nonsense. It actually could prove things that couldn't have been proven without it in number theory, which gave it the pizzazz to like be carried forward. And in the meantime, since then, it's largely become the language of pure math. But it's also increasingly applied outside of math, which is something when I tell people that, they sometimes laugh because it's so abstract. How could it possibly have applications? And yet that is what has applications. If something was completely concrete, it would only be itself and never be applicable. So it's the abstract that is, the abstract is the reusable. It's the structural essence. So despite the learning curve, I think interest in category theory has been consistently growing. So next up, I'll give you a taste. It's going to get more technical because I thought maybe that was important, especially to introduce the next upcoming paper session. So I'm going to talk a little bit about polynomial functors in particular, actually. And then I'll try to come back out and apply this idea of abstraction and math, and the particular math I'm talking about, to this question of what we care about in collective sense making. So in math, there are a few miracles. One is that the complex numbers, I don't know if anyone has seen this miracle, probably a lot of you have. You adjoin the square root of -1. You say, I know square root of -1 doesn't make any sense. Don't worry about sense for a second. Let me just add this thing to the real numbers. And also 2 times the square root of -1 and 3 times the square root of -1 and square root of -1 plus 5 and stuff. Let's add that in. And now what happens is the miracle happens. Not only does every polynomial factor completely, but if a function from the complex numbers to itself has a derivative, it can never be pointy. It always has infinitely many derivatives. No one put that in. You get more out than you put in. And sometimes, I kind of think that's where intuition comes from. It's like you're thinking about something, and then all of a sudden you have a thought, and it starts to work. It starts to give you more than you put in. And so you know something's working. And complex numbers have been a miracle and used all throughout electrical engineering, and I can't say that about polynomial functors. They are pretty new, and they have not changed the world like the complex numbers are. But from my perspective, they do have that same flavor of miracle. It seems to be at the core of a great deal of computer science, despite a very simple definition. I'm not going to talk about them in detail, but I'll give the idea. And the idea, when I try to think like, okay, what is the essential thing that polynomial functors are talking about? For some, it turns out what they seem to want to talk about is what I call interfaces and delegation. That people talk about embodiment of an AI or something. I think I heard that term. The interface that something lives in, the interface of a neuron, the input-output, and then this notion of delegation, which is less of an important idea, but we know it from business speak, that you delegate to your mech suit. You delegate the decision of what the submarine is going to do to the bridge or whatever of the submarine. So this delegation of letting something else control something else, letting A control B, is what polynomial functors, for some reason, that's what they're good at. So, so basically, the reason I want to talk about polynomial functors is that they're the simplest framework I've found where you can talk about agents and interactions and dynamics and use this to try to understand ourselves, which is what's inside and how do we relate. How does everything inside of us relate to everything else? How much does it relate? So I think Poly is a good language to ask very basic questions. So I'm going to talk about, instead of agents, I just want to talk about the interfaces of agents for a second, because a lot's going to happen to connect, basically connections between interfaces is going to be where the action is. So the interface of an agent is what you can give it and what you can receive from it. So the interface for an agent like James Bond, Agent 007, or a travel agent, what does it mean? Like, what is it that we're talking about at all? Well, we give it a task. We say, go get that guy or whatever, get me a ticket, and it returns an outcome. Here's your ticket. And so different agents have different sets of tasks they can do. Each task for an agent has a set of possible outcomes. So if you have a task that you can do called flip coin, then there'd be two possible outcomes. So I'm defining some terminology here, task and outcome, okay? So the task pick number or task tell joke has infinitely many outcomes. So the interface for an agent, or what is a polynomial functor? It's a set of tasks, a set T. Task has no meaning, it's just for your intuition. It's a set T, and for each element of T, for each task, there's a set of possible outcomes. The set of possible outcomes for the task, flip coin, is heads, tails. Maybe you could have something where every task just has the same set of outcomes, but one task is get me a heads, and the other one's get me a tails, but you still, you asked for a heads, I got you a tails, sorry. So I have a task, but there's some outcomes that could happen. 007 doesn't get the bad guy or whatever. That is a possible outcome. So you define, when you define an interface, what are the tasks, and for each task, what are the outcomes? And delegation is the name I gave to the maps of polynomial functors. I'm giving it to you, this name delegation, to try to give you intuition about something that's otherwise abstract. So suppose you have two agent interfaces. And then to say that agent 1 delegates to agent 2, what I mean is that for each task in T1, specify a task in T2. And then for every outcome of T2 of that task, knowing which task I actually gave it, give me an outcome for task T1. So I know as the boss what I really need done. I ask Bob to help me get it done. I say, here's your task. They give me an answer. I use my information about why I gave Bob that task, together with Bob's outcome, to decide my own outcome. Okay, so, but that's, if you remember, that's exactly what I said about abstraction also. So you start with this concrete experience of like some people doing computations. You extract a concept from it, and then, given an action you could do with that concept, you can bring that back to your actual set of people or whatever. So you can apply it back to the experience. So abstraction, in some sense, delegates from an experiential or concrete thing. It delegates this problem of, I have too many weeds in my garden, to the abstract thing of, quote, I have too many things in my garden, lets you solve the problem there, and then pull the answer back to your specific case and weed exactly there in your garden. And so the way that you write it in math form is like this sigma t over t, y to the ot, blah, blah, blah. And this thing is actually a functor. So I told you that Eilenberg and MacLean invented category theory. They invented categories, like the category of sets. They invented functors, like this functor here. And then delegation is exactly what they defined a natural transformation to be. This thing I said, delegation, is just my name for when I unpack the definition of natural transformation for these functors, it's this delegation story. So I took what they figured out about what's important for math, and I applied it in this case, and I called it delegation. This back and forth mapping of taking my task, delegating it, taking their response, and then taking that as my outcome. So there's an algebra of interfaces, polynomial functors. You can add them, you can multiply them, you can tensor them, you can compose them, you can internal hum them. There's all these things. So if I've a set of tasks P with outcomes and a set of tasks Q with outcomes, I can add them so that you can pick a task from either one, right? If there is a set of possible things an agent can do, another set of possible things an agent can do, I can just join those together. That's P plus Q. P times Q is, okay, I give this new interface, I give it a task from P and a task from Q. It just has to pick an outcome for either one. P tensor Q, like when you just unroll what it means, P tensor Q means pick a task from each, I need a response from each, et cetera, et cetera. There's all these different algebras of interfaces that you can make. There's an algebra of interfaces, and these are associative and unital, and they distribute across each other and all sorts of interesting things. So there's like an algebra of these interfaces. But the point is that we can combine agent interfaces in all these controlled and lawful ways, and once we do that, we can start forming machines. I don't know if people have heard of Moore machines and Mealy machines, but these are like machines that take streams of inputs and give streams of outputs. Now we're getting into something more like a neuron or something. Not a real neuron, because maybe they're more complex than just streams, but maybe on the dendrites of the neuron, if you keep track of exactly where the action potentials are hitting those dendrites, you can say it's taking a stream of those vectors or whatever and producing a stream of spikes or something. So you can start to move this into a more and more kind of useful abstraction here. And all of this stuff can be said nicely in polynomial functors. In a Moore machine, you take an input A and a current state, just an element of some set S, and you update your state, and you read out an output. In a Mealy machine, the current input is allowed to affect the current output directly. That's the only difference. Each one, a Mealy and a Moore machine, are two different abstractions for machines that transform streams of A's into streams of B's. But you can think of both of them in terms of these delegations. So a natural transformation from SY to the S to BY to the A is a Moore machine, and a natural transformation from SY to the S to the internal HOM of AY, BY is a Mealy machine. And some stuff that I'm not going to explain, but it's in the book that Ben mentioned, and it's not super easy if you're not used to it. Of course, nothing when you're not used to it is super easy, but it's not very hard compared to like how hard math gets, because my brain is not smart enough to get the really hard stuff. So I'm just looking for something easy enough that I can get my hands on it. Anyway, so this slide is just about how Moore and Mealy machines, things that kind of take inputs and give outputs, are very well represented by polynomial functors. Yeah. And then from here, you can start to arrange machines. So you could have like, an adder circuit and a multiplier circuit and a logic gate and a neuron, and you put them together and you wire them up, and bam, you get this weird thing that does who knows what. And you could even have that interaction pattern be dynamic, so that what's flowing on the wires from P1 to P2, say, if Bob says, hey, can we bring Mary into this conversation, then all of a sudden, like a wire from Mary, a new channel kind of opens up. And so you can make the wiring diagram change as data flows through the wires. And that's also very easy to do in polynomial functors. It happens in deep learning, for example, that like as you get inputs and outputs, like the loss function, you can change the weights of the neural network. So that sort of pattern works very well in polynomial functor land. So you can formulate the gradient descent algorithm in these terms. And you can also define hierarchical agents that call another agent. So one agent delegates a task to a bunch of sub-agents. Those sub-agents follow some flowchart that we make up, and they say like, hey, you two, can you come together? Each one, you solve this problem, you solve that problem. If the answer is equal, kind of do this. If it's different, do that. And you give some flowchart of how they're going to behave. If you think about like some big problem, any problem in the world, there might be someone who has a flowchart for it, like human trafficking or something. It says, is this the case? Yes, no, right? And then you follow these flowcharts, and it tells you what to do. Arbitrary flowchart logic is the sort of thing we've seen in a bunch of talks. And it's the sort of thing that you can also say very nicely in polynomial functors. So, and not just when I say specify nicely or easily, what I mean is that the polynomial functor formalism, if you got that implemented, is fairly low. I think the whole thing would be fairly low Kolmogorov complexity. Like the programs would be very short, and they'd feel very compact. But what's the point? So now we've kind of gone in, so I'm kind of doing a fractal here, right? So what is this whole story? Well, we've kind of moved into an abstraction. We said polynomial functors is some abstraction for something, but this wasn't what the talk was about. The talk was supposed to be about sense making and care and things like that. So I want to now bring it back out. So we want to bring it back out to our experience, and yeah, someone needs to build it, and that has not really been done, except, well, a lot of it has, because artificial neural networks is an example of this, but it wasn't an example that used this to construct it. Like, they had artificial neural networks before they were thinking about them in terms of polynomial functors. But it would be an abstraction that could carry that. But I think my point is I want to learn about myself in this sort of sense. So are we agents in the sense I was talking about? Are we just a fixed interface? Or should we say that, like, when I have this thing in my hand, that as an agent, I actually am now a larger agent, that my interface has changed because I have this? Like, what is this meeting? Is this meeting one of those rewiring diagrams that changes based on what flows, or is it different because there's something different about it? So I want to ask these kind of philosophical questions and see how much of it we can encode in the polynomial functor formalism. And for that, I need a lot of input from people who have ideas about how we should model meetings of, like, agents coming together and talking and making sense of things. So when you eat something and you consume this machine, this, like, protein that is able to now make things happen in your body, you're eating machines, right? It's kind of like hiring at a company. Like, how do you model that in an AI, that it can eat a machine and have that machine become part of it? Or heal some problem, be resilient to some problem you've never seen before. And then where do care and intention come from? How in this whole field of, like, machines interacting with machines, where's the care part? So my idea would be that the polynomial functor formalism, which I don't expect you to believe, but you can kind of, like, at least know that according to me, it's a very simple and elegant framework where you can do, which has been studied for like 50 years, where you can do do things along these lines, but it makes your actual desire to understand, it makes it like, it sits there as a language ready for you to write a story. And if you can write a story in that language, you can code a computer to do it. And if you can't write the story, then my point would be that I think we might be able to write nice stories in this. And then as we do that, we're creating new math, and that math might help us make sense of living. So what I want to try to do now is pretend, I wish Turing had been able to, or had wanted to, take care into account. So he found this mimetically fit, very short description of what a machine is, the mechanism of computers. But I think it's more important in the sense that care is the only thing that's important to understand how that care part works. So I want to pretend that I wish I was able to do what Turing did and get the care part into the math. Like, what is really going on with that? And so I want to give a kind of story about how we got here and where we're going, and do it in a way that's plausibly mathematizable. Although it's just, this is fiction, this is not polynomial functors, this is a wish, okay. So I think actualizing potential, which is what I said care was about, is already part of physics. So a lightning bolt, you've got this potential difference. It's like, oh man, that'd be so great it'd be so great if we could just actualize this. Or a hurricane, you've got the hot water and the cold atmosphere, and somehow it's hard for the heat to rise.
Good afternoon, everyone. Can you hear me?
And so the hurricane actualizes that potential by making an eye. By rotating the air, it makes an eye, and it slurps the hot air straight up. And so they actualize this potential difference. They somehow, the world seems to be able to notice that there is this potential that could be actualized, and then to create something amazing like like some kind of convection, Rayleigh-Bénard convection, to like somehow solve this problem in an ingenious way. And so instead of RNA first story of origins of life, there's a metabolism first story of origins of life that I heard from Eric Smith. And he says that life is the simplest chemistry lab that can perform a certain chemistry work, which is to take some high energy outputs of a deep sea vent and turn it to a low energy state. Life was the simplest chemistry lab that can accomplish that, like a hurricane. It's just that somehow that tendency, that ability to actualize potential was encapsulated into things that could go off and do it elsewhere. And that ability to form these capsids was for him, for Eric Smith, and what I think is a more plausible story of the origins of life, which is this just tendency, this ability to encapsulate this actualization of potential. So somehow it seems to me that when you're at the place where potential is actualized, if you were there in the room when OpenAI did the thing or whatever, DeepMind did the thing, or if you were in the room when if you were there when you invented the thing, the idea, whatever it was, somehow you're like changed by it. And I don't understand this. So what goes on when you're there and you actualize potential, and when you give that kid what they need or whatever, you're changed by it, right? In some way you didn't expect. And that change, that swirl in your mind or whatever happens, kind of stores information in you somehow. I don't understand how it works. But then this potential actualization skill begets more potential actualization skill. And that is this care, this tending capacity, the ability to encapsulate tending itself, that we can tend to something, becomes held. So in the story, evolution has been guided by care the whole way through. It's never been, if care was just like tending to actualize potential, then since the beginning we could say, oh, there's always been care. And that these random mutations we see in Darwinian evolution are just what outsiders would see when they watch the search process for what's going on. You know, if someone watching this room, but everything was scrambled, you'd say, like, I don't know what's going on. They seem to be searching for something. But we know by mate selection or sociality or invention that somehow it's a guided search process. It's not random mutation. And so in this point of view, the distribution of care throughout the Earth would have been the thing that's been in development for 4 billion years. The fact that Putin is in Russia right now is actually all of the care that exists on Earth has actually put that person there. And in that sense, maybe like it kind of changes how you see things. Like everything we do, everything you care about, the only time anything gets actualized is when you care. And so this care, what is it? What is that? That's the question. So carers, from neurons to humans and beyond, we collaborate, we work together to actualize potential. We sit in a room, we form companies, we get together, we have dinners because we want to actualize potential. You wouldn't care to have that dinner with the person if you didn't think there was something there that could be actualized. And when you do, when it gets actualized, if the conversation's actually good, you're kind of changed by it, and the care moves through you, and so that's kind of the whole thing I'm trying to propose here. This ability to care. The thing you'd hate most, I think, for a kid is if like they just they were completely unable to care about anything. Like you'd feel like you hadn't passed down what you needed to pass down. And by giving us pain and pleasure and stuff like that, nature has passed to us the ability to care. And that's what's being passed down. That's this animism that's being passed down. So what holds care? I think I want to know that question. So now I'm kind of wrapping up here. I think we're playing with our own lives. I really like Scott David, is that his name? Robert David? Scott David's point of view of AI is like gain of function research to the nth degree. So we're doing that and we're playing with our lives. So we should watch that. I think that the math and computer science we create is going to carry us through this phase transition. And we're going to process and make sense of the world much more powerfully. But this can cause these bizarre hiccups of miscommunication and fake news. And I think that the more elegant our abstractions are, the more they're beautiful. I think, this is a guess, that the fewer hiccups we're going to have. And so the most important thing, if that has any meaning at all, it is what we care about. That's the most important thing, what we care about. And so tending to that well it may not be easy, but it's our job. I remember as a kid, when I played soccer, I just wanted to kick the ball as hard as I could and not get it to my teammate. And I think sometimes when we form intelligence, we're just seeing how far we can kick the ball instead of making sure that it's part of a good future that we want to be a part of. So I think it's just, my point here is that I want to ask, what are the dynamics of care? Is care really my care and your care? Is it individualized, or does it pass between us? Like, can I actually get you to care about something? Can you get me to care about something? And can care itself actually be lost? If it's some kind of physical thing about physics wanting potential to be actualized, I mean, information they say can't be lost. Can care be lost? Sometimes it feels like I just can't care. It's just too much. I'm too weary. I can't handle it. Can it really be abandoned or not? I don't know the answer. Can it be created? Can care be manufactured? Could we get care into an LLM, or could we not get care into an LLM? I don't know. So far, the LLM has to be told what its goals are. And the person who tells it its goals, that's the one who cares. So I'm worried that we're not properly tracking our care. I think money is, all I can think of that lets us track our care is basically money. It's like, what do you care about? What are you willing to pay for? But it's just so poor as a tracker of care. It's supposed to be, in God we trust is on every piece of money, or at least for a long time. It's like the state, something with power tells you that this is something you can care about. But I don't think it's working. I think if we're going to have a good future, we need to remember care. We need to track it better than we are now. And so I imagine a fabric, kind of like Indra's net, if you've heard of this. So a fabric with threads knotted together billions of times, and that we're kind of these knots. So the thread, we're all this same thread somehow in this weird picture, but we're composed of thread, but we're thread that's knotted up. And that knot is somehow holding something important. And belonging together, what shapes the fabric, what belongs with what. We belong together in this room because we're all caring about the same thing. So now I'm imagining that in this thing, things can strike the fabric, right? Some meteor hits, or some weird event happens, and there's some lead ball that like strikes the fabric. And so we pull on each other, like, I need you, I need you. And so I pull on somebody. And when we make sense, we kind of distribute the load of whatever comes our way. The better we make sense of things, the more when something comes our way, we can distribute the load out to where it's supposed to go. When your system gets some kind of exception or some kind of fault, how fast can you diagnose where it's supposed to go and save the day, right? So that's the better sense you have of something, the better your code is, the more it makes sense to you, the more when something strange happens, you're able to figure out how to distribute the load of this weird new event and make it work out. So I think we're knitting the fabric as we speak. We're kind of tying the knots and tangling ourselves with each other in all these meetings we have. And that evolution and learning changed the consistency of our fabric, but now we're going through some kind of phase transition and radically changing. And we've put a lot of thought into intelligence. Everyone's talking about intelligence, but I think care is at least equally important. So our motivations guide the future texture of the fabric we're creating. Our motivations, now's the moment where we actually get to hone our motivations. In 5 years, do we still get to hone motivations? I don't know. But right now is certainly a time we get to hone, what do we actually care about again? And I think that that's the most important thing we can put into it. So thanks.
Thank you very much. That was amazing and awesome. I love being at an event where a category theorist talks about care and intention. It makes a conference worth listening to, worth attending, I think.
Thanks, Haley.
Thank you. Do we have a couple quick questions? We're trying to catch up a little on schedule, but I think we've got a roving mic back. Oh, we've got a question here. Yosha.
Thank you. I think it's an important question to put attention to, but I'm not sure if the question is all that difficult. Informally, I think that meaning, when we think about it, the meaning of information is its relationship to changes in other information. Slightly more narrowly, it's basically a reference to a function that changes the representation of a system that it uses for controlling its interaction with an environment. And if then you look at caring, I think that caring is the relationship that an agent has to its purposes. And purposes are the models of the needs that this agent makes. And needs are basically representations of the systemic demands of such a system. And I think we can understand all these things. It's not that hard. But what might be the really interesting question is, how can we build a system that is basically starting to build its own structure based on these models, on basically modeling its own demands to sustain itself in an entropic universe, and then it's building control systems based out of these demands that at some point lead to representations of purposes, and then to what we would call care, which is this relationship that the agent itself establishes to its purposes. Or please talk back to me if you don't think that's a good way to capture these terms.
Yeah, so you said care basically goes down to the demands. But demands to me is the same as care. What demands to exist? So we already have everything kind of existing. Saturn exists, doesn't seem to care. So the demand to exist, when you kind of bring everything down to this question, what demands to exist? Well, I demand to exist, but I'm not sure that a sandwich demands to exist in the same way.
When I
So-
stop caring, I stop to demand to exist. But
Right.
I'm continuing to exist until something, entropy basically takes me apart or somebody else does.
Right.
And so Saturn exists by itself. It doesn't need to care, as far as we understand.
Exactly.
Right? But if you're an agent that is only able to
But then-
persist because
yeah.
it models the future, then it needs to make a model of these demands.
Yeah, so you make agent something that's primitive, and I think care is more primitive. I think care is tending to actualize potential, to find something, to see, oh, if I have a siphon, if I just put some suction on it, I can drain this whole lake. I could drain, if I just put a little effort into it, I could get a lot out. So this actualizing of potential seems to me something that, whereas agent seems kind of like a human-made thing that almost nothing else I can't really see in physics that well, I think actualizing potential is something I can see all the way from like wanting someone to succeed and the moral, like realizing that a slave could be more, they have more potential than they're being used for. In the same way that I see morality, I also see physics as having this idea of actualizing potential. So for me,
I
it
think
seems
you
a
let
primitive.
the term make too much work. If you look at a hurricane that is sucking in air, it might be actualizing its potential, but it's pretty much a stretch to say that it cares. To care, you need to build certain kinds of representations. And as far as we know, the hurricane doesn't need to represent anything to function. So I think that an agent, a control system for future states, is a relatively simple primitive.
I think we need to, yeah.
Well, thank you for the interesting talk and presentation of care in terms of actualizing potential. I'm curious in terms of tracking care and delegation, is there some way of modeling or tracking when certain agents are like effectively caring for other agents or not? Like how can we tell if an AGI is caring for humans or not?
Yeah, I don't know how to tell if someone's caring for me or not. In some sense, I kind of feel cared for, but it's intuition. Maybe they're abusing me in some way. I don't know. So this is not supposed to be. It's supposed to be. I don't know how to tell if something cares for something else or not. Yeah.
So I have a couple brief points and then a possibly thorny question. So in seeing your presentation of the technical aspects of what you're doing, it occurred to me that your polynomial functor model could be an interesting semantic model for what we're calling the AI DSL in SingularityNET. Basically, we have a population of online AI agents. Each of them describes its properties, its inputs and outputs and requirements and so on in a certain formal description language. And that seems fairly close to the way that you're describing things. So it could be interesting to explore how you use polynomial functors to sort of formalize the semantics of this AI agent description language that we have. So that
definitely sounds like the right, yeah.
Yeah,
right
that's
level.
one observation. And another observation, I think when we talk about care, so there is a lot of depth there, and taking it in some sense as a primitive makes sense to me. I mean, consciousness and compassion may be sort of immanent in everything in some way. On the other hand, if we look from a human psychology perspective, there's often cited as being two aspects of how humans sort of deal with the empathy and compassion with others. And one is sort of a very primitive level, feel a similarity or commonality with the other entity, and we feel more of that with those who are more similar to us. We find it easier to empathize with other people than with pigs, either with pigs and with rocks. And this somehow feels like there's some morphism story there. But the other aspect is reasoning based, right? Where there's sort of a theory of mind, and we can reason, well, even if this entity doesn't look like me, it looks like some three-eyed, seven-tentacled alien. Logically, I can see, even though it's ugly, green, and slimy, it probably has feelings and suffering just like me, and I should empathize with it, even though I don't have that resonance based on similarity, right? So it seems like some of the aspects of how we manifest care in practice could be modeled some of these category theoretic tools, but it seems like you haven't tried to go to that sort of level of cognitive modeling. I'm curious if you intend to or think it's interesting.
I intend to. I have tried to, and I've failed to, but I want help. I just want to say care is as important as intelligence. But I think I just wanted to note that in what you said, it seems to me that communication with something, where when I resonate with it, when I'm able to tell it what I'm saying, and it says something back that's like, oh, it got me, that's a very important part of being able to empathize with something or want to participate with it.
Yeah, that lets you feel a sort of inner similarity, even if there's not an
exactly.
obvious
And so when you talked about empathy with the alien, you also, I guess it's time to stop pretty soon, but you also mentioned that it was similar to you as in some sense in its internals, and so that similarity was still somehow important, even to empathize with the alien.
So I think I have one more question, which I don't expect to get a concise answer to, but the stuff on Moore and Mealy machines is interesting. Now, in our actual work trying to build AGI systems, we're dealing with like the zipper abstract machine, which is a much more complex sort of abstract machine where the output doesn't depend just on the state, but on some continuations and so on. So I just wonder, is there a polynomial functor story corresponding to these more complex abstract machines like we're actually using in AGI work?
I don't know the term zipper. I don't know that term of that.
Okay.
But I would like to hear more about it.
Yeah. Well, Greg can tell you even more than me about it, or Adam, but it seems an interesting direction. I think, David Wood, did you?
We did. We actually need to move. I apologize. We do have 2 more questions. David Wooden over here. I apologize. We're going to need to miss. I do encourage you both to get on the YouTube and David as well, and you can ask questions, answer questions. There's the virtual attendees that can see it as well. We're trying to move in so that everybody gets a coffee break and we sort of end on time for the reception tonight.
Thank you.
Thank you again. I do hope, I know it was a slip of the tongue, but I do hope we find the care particle, the carons, and make that real. So thank you very much. We've got our 4th contributed paper session. We've got 2 virtual presenters and 1 live presenter. So again, we'll have 15 minutes per 15 minutes per presenter, and then a question session at the end. We'll try and keep everything super tight, get a coffee break, and then come back for Alex Arorbia's talk, which I'm looking forward to, and then an official poster session next door before the reception tonight at the Burke Museum. So our first paper today will be Vincent Abbott with category theory for artificial general intelligence, following on David's category theory talk, and see what Vincent has to say for us today. So thank you very much, Vincent. We don't hear you yet, Vincent, if you can hear us. We lost Vincent.
Hello. Good afternoon, everyone.
Hello. We can hear you if you can hear us.
I think we're ready to go. So, today I'll be covering a survey paper I submitted along with my co-authors, Tom Zhu and Yoshihiro Maruyama, to the AGI conference. We'll cover category theory and its ability to generalize and better understand all stages of the artificial intelligence pipeline, and hence, show that it offers a natural approach to true artificial general intelligence. So, why category theory for AGI? Category theory is the mathematics of composition, just like group theory is the mathematics of symmetry, and calculus is the mathematics of small changes. It focuses on composed structures and the relationship between them. A categorical description, therefore, provides connections between a structure and related ones. For example, a database relates to a vector representation, which relates to a forward algorithm, which relates to a backpropagated form. This backpropagated form, then, relates to code which we can learn and infer from a database. So, what is a category? A category is a compositional structure. Anything with objects, anchors, and morphisms, composable connections, forms a category. Here, we have X, Y, Z as objects, and F and G as morphisms. Therefore, we have F by G as a morphism. This covers a broad range of mathematical structures: sets, random kernels, logical proofs, graphs, linear spaces, diagrams, and code all form categories. Between categories, we have functors. These map from one to another, preserving composition and hence structure. This can relate a mathematical expression to corresponding code, transfer one data type to another, turn an algorithm into a learnable version of itself, or evaluate a diagram. Category theory offers consistency between different perspectives. We believe this is essential to artificial general intelligence. This is a survey presentation for a survey paper. We will cover 3 topics. First, data representation. We can convert from a composable database into a learnable linear representation. Design and analysis. We can use intuitive categorical diagrams to formally define machine learning models suitable for a data structure. And finally, we'll cover learning algorithms. We can convert from a forward algorithm into its learnable backwards form using category theory. Taken together, we see that category theory offers a general pipeline for representing, learning, and optimizing our approach to artificial intelligence. So, let's consider a database where we have words and relationships between them. This forms a category. But how do we learn these relationships? We need a vector representation. We can get this from a functor, of course. Each word gets assigned a vector space, meaning morphisms are linear maps between them. Morphisms which act on a range of words then become linear maps between direct sums, matrices. This is how we use a functor to turn our database into a graph. And then we can collapse our dimensions to give a fuzzy, low-dimensional, learnable representation. This indicates to us that vector representations used by most algorithms are, indeed, able to model complex relationships in a database. But how do we decide upon which algorithm to use? This pivots us to a critical question in deep learning research. Designing algorithms is an engineering task. We see what works and iterate upon it. If we want to streamline this process, we need a formal approach to communicate, systematize, and categorize machine learning models. Category theory offers this in the form of diagrams. They serve as both blueprints and equations. These are all implemented through functors. Vertical sections of diagrams get mapped to functions in set, or can get mapped to code. Therefore, the compositional structure of an algorithm is reflected in the diagram, and its relationship to either mathematical expressions or code can be clearly found. Architecture design has been critical to the machine learning revolution over the last decade. Architectures can significantly impact performance, ease of training, and the ability to tackle certain classes of data. However, typical presentations such as these are difficult to pass, and it's hard to see how they relate to implementation or the mathematical dynamics of architectures. These diagrams fail because they do not have a clear relationship to other perspectives on the composed structures they represent. So, how do we represent architectures? Category theory has a rich diagrammatic heritage, primarily with monoidal string diagrams. Diagrams form a category, and the evaluation of a diagram into a mathematical expression is a functor. In neural string diagrams, presented previously at this conference, my co-authors Yoshihiro Maruyama and Tom Zhu used monoidal string diagrams to describe machine learning models. These diagrams provide a formalism for otherwise problematic representations of models. However, monoidal string diagrams are not entirely appropriate for deep learning architectures. They cannot simultaneously capture the details of independent data and the axes of tensors. Seeing how operations act on specific axes and which axes are manipulated by linear operations is crucial to understanding architectures and turning them into optimized code. Neural circuit diagrams, my work, build on neural string diagrams by using a novel approach to monoidal string diagrams. Dashed lines are placed between independent expressions, allowing wirings to represent axes. This can clearly communicate the specific actions taken by machine learning models, far better than ad hoc or even monoidal string diagram approaches. Neural circuit diagrams tile together building blocks, each of which represent an operation, a morphism. These can be combined with dashed lines to represent independent data, or lines can be added above or below an expression to add an axis over which they are lifted. This lets us clearly and accurately represent entire architectures. For instance, the traditional presentation of the ResNet misses key details. It is shown here, making implementation from the diagram alone impossible. In fact, the latest version of PyTorch includes an old version of ResNet. With neural circuit diagrams, the ResNet can be presented in all its detail, with the exact operations applied to specific axes clearly represented. Once we've got a vector representation of our data and some algorithm to process it, how do we learn and optimize the algorithm? The answer is, of course, backpropagation, where we employ the derivative chain rule in an effective manner to find the derivative of the loss function with respect to each parameter. The chain rule is compositional. It is a functor. Here, we see that the derivative of a chain, x, followed by f, followed by g, is the derivative of x times the local derivative of f times the local derivative of g. The chain rule maps a forward expression to an expression that calculates locations going forward and accumulates how things change. We can apply this as a functor. Here we have our original expression, and here we have a diagram, which is the backpropagated form. This means that there is a functor from algorithms, which we have mathematically defined using diagrams, to their backpropagated form. Category theory, therefore, can be seen as providing the conditions and procedure for training an algorithm once the goal has been defined. Furthermore, category theory can be used to convert a stateless functional expression into a stateful expression with hidden parameters. In this case, backpropagation converts our expression into a map from initial to updated parameters. So, taken together, category theory is a general, universal approach to the entire machine learning pipeline. It operates by preserving structure between different perspectives. It can convert data structures into their vector representation and maps from diagrams to explicit mathematical expressions and underlying code. It relates forward algorithms to their learnable backpropagated form. Category theory, therefore, is a natural choice for developing a truly general approach to artificial intelligence, with the entire pipeline covered by different aspects of category theory, and the connections between them clearly elucidated. So these are the references used for this presentation. So we've covered using category theory to go over the entire pipeline of machine learning, showing how each is connected to the next. Category theory provides mathematical connections between these different aspects, showing how they are connected. It can therefore be used for a truly general approach, with every step being related to the next and algorithms being generated along the way. Diagrams, such as those we've shown before, are mathematical expressions. These mathematical expressions are related to a backpropagated form. Category theory serves as a holistic mathematics of all of the stages of deep learning. So, in this work, I've briefly covered some things with the intention of not going into too much technical detail, but I'm open to any questions if people are curious about any of these specific sections, especially the diagramming work.
Thank you very much, Vincent. Thank you. We'll have questions again at the end in a session. Right now, we'd like to invite King-Yin Yan, AGI from the perspectives of categorical logic and algebraic geometry. King, please take it away.
Hi.
Hello.
Can you hear me? Okay.
Yes, I can.
Can I share my screen? I need to.
Yes, go ahead.
Where is the share screen?
It should be available to you now.
I can't share screen. Where is the share screen?
It should be at the bottom of Zoom. It should be at the bottom of Zoom.
No, where is the share screen button?
Oh, all good. If you're in Zoom, maybe try Alt plus S.
Alternate
S.
S. Where is the share screen button?
If you're in Zoom, maybe try Alt plus S.
No, I press alternate S, but there's nothing.
Oh, all good then.
I'm
if you want
using
to
Linux. Does that matter?
Maybe. You may not have permission. If there's anything you want to show, I might be able to show it.
But I need to draw on my screen, so...
Okay. See if at the bottom of Zoom. Oh,
yeah.
Just got a chat message. If you go at the bottom of Zoom, there should be a... Do you see if there's a more button or a share button?
Yeah, it's not in the bottom, but yeah, I see but there's no share screen. There's whiteboards and team chat and stuff.
Is Mike Bennett around? Let's see
But
if
no
we can
share screen.
put Mike up here while we wait.
If you go at the bottom of Zoom, there should be a... Do you see if there's a more button? The more button.
While we work this out, let's go
there,
for a
maybe.
quick coffee break. So everybody, 10 minute, we'll come back and watch King and Michael Timothy Bennett do his second paper, and then we'll finish with Alex Rorbia and the poster presentation next door. So we'll meet back here at 20 after 3.
Can you use this whiteboard?
Yeah, okay.
I think we'll break. We'll get everything straightened out. It's
which is related to the category.
Do you have Zoom here?
Yeah. And in particular, I use the categorical logic perspective.
Hi, King. Stop it, please. Can you restart? And I'll let you know. I'll let you know when you can restart.
Or just meeting. So he got off the meeting. How can he get back in?
Sorry. So if it's in progress,
this one, right?
can you get in?
Yeah, I'm clicking.
Okay, can I? Sorry. Apologies.
Just how is it? Okay. Start.
Yeah. Okay, you can start.
Hello. My research is mainly concerned with categorical logic and how to use this perspective to accelerate the learning of AGI. So in this talk, I will talk about three things. The first is about the no free lunch theorem, and it's the basic argument that I use to accelerate the learning of AGI. And then the second topic, I will talk about categorical logic, in particular, the notion of vibrations. And in the third part, I'll talk about something that's new in this after I submitted my paper, which is more on algebraic logic. So, this is the basic argument. So we look at the space of all AGI solutions, and I found that we can use some symmetry of the search space to reduce the hypothesis space. So we can search in a smaller space, and that means the learning will be faster. And we have the search space here, which is of the form of the shape of the hypercube. And when we think about gradient descent, we usually look at landscapes like this. And but I argue that in high dimensions, that these ups and downs are not so important, but the most important thing is the number of dimensions. So for example, here you can see the gradient descent going down. This can go on for a long time, and the cost of the training can be measured by gradient descent. This is the formula for gradient descent, and from this we can see that we can use the Euclidean distance to measure how far we are going to train the neural network. So basically, the size of this hypothesis space as measured in the Euclidean area is an indication of how much we are going to spend, how much money we need to spend to train an AGI. And also the search space, we have a structure bias. So we impose a structure on this search space, and then the blue area is a special structure that we impose, and then after the imposition, we still need to use gradient descent to fill in knowledge into the AI. So the parameter space represents both knowledge and structure. So, for example, we can have some dumb structures, such as these animals, which may not be very intelligent, and they occupy many points in the hypothesis space. So we want to find some special structures that are particularly intelligent, right? And even within such a structure, we can have many behaviors or knowledge that are misguided or dumb, and we need to optimize by searching the right knowledge. So so this is my argument that if we know the AGI will have a certain logical structure, does it make sense for us to only search in those structures? But we are ignorant about the distribution of AI in this whole hypothesis space. And so I'm not 100% sure about how sound is this idea. So maybe some of you may help me to make this argument more rigorous. And so I have an example of an artificial example where we have the permutation symmetry. And in this example, we can work out the mathematics completely. So if we know that we are searching for a symmetric function, then we only need to look inside this fundamental domain. We have the search space, and the symmetry divides the search space into fundamental domains, and we only need to learn the data in one fundamental domain, and that would be sufficient. And this would be a reduction in the size of the space that we need to search, and that will give us the acceleration we want. So this example is worked out, and so then I will talk about the second part, which is we use the structure of logic to restrict the search space. And this is some categorical logic, which is the use of category theory to describe mathematical logic. And it's based on the principle of the Curry-Howard isomorphism. Maybe I don't have time to explain it too much, right? And some people may have already known this. Joachim Lamberg proposed this trinity between category theory, logic, and type theory. And we can see that logic is related to type theory by the Curry-Howard isomorphism. And this relation is also very obvious. So this trinity is quite canonical. And but I want to point out that in the logic part, we also have algebraic logic. It should be in here. the reason is that every logic, we need a formalism to express this logic. And if we allow for universal algebra, then the logic can be expressed in any algebraic way. So algebraic logic actually belongs in this node. So here we have the logic, and we have A implied B, and then in an algebraic form, for example, this is in the Boolean ring format, and we have this formula, algebraic formula, and then by Curry-Howard isomorphism, we go up to the type theoretic description, but this is not exactly the algebraic. This is not exactly compatible with the algebraic form. So we actually need to go back and then go up. So it's like a pullback situation. So we actually have a pullback kind of yeah. But what I want to say is that you can't just go from algebraic logic just up to the Curry-Howard. It doesn't work that way. So in the categorical logic, we have the structure of logic described by category theory, and one of the structure is A and B is equal to B and A, right? This is the commutative property of propositions, and this symmetry can be found in the transformer, which is one of the a motivation for thinking that the transformer has some kind of logic structure, and but this is already used in the transformer. This is well known, and but the second well-known symmetry in structure in logic is this vibration structure, which is when we have a predicate, for example, PAB or some relation RAB. So this is a predicate structure, and this structure is described in category theory as a vibration. So it looks like this. So, for example, the RAB would be something like AB, and then R is sitting above this as a vibration. And I was thinking that this vibration will give us a kind of symmetry similar to the permutation symmetry I mentioned earlier. So I thought that if we have a fundamental domain of this symmetry, then we can reduce the hypothesis space. However, I found out that this is not true, because the vibration is just isomorphic to A times A times A. So we actually don't have any reduction in the hypothesis space size. And that is kind of an anticlimax in this direction. And it took me a long time to realize this, and I still am not 100% sure, but that's my conclusion so far. So that means in categorical logic, I cannot find another useful symmetry for accelerating the AI. It is kind of like we have structures of these types which are spaces. And then we have the Cartesian products of these spaces, but they are just empty spaces without much structure. So it is kind of disappointing that I cannot use this to accelerate the learning. So that comes to the third part of my talk, which is the algebraic side of that trinity. Remember that I talked about this trinity, and that's the algebraic side here. And so it gives rise to some interesting mathematics because the algebra is new because we have a neural network, and we must use the neural network because it is the fastest learning method we have currently. So so let me explain the setup. This is the general setup of an LLM, which is an autoencoder. We try to reconstruct the world data by using some kind of information bottleneck. And that there is some abstract representations will emerge in this middle part of this bow tie shaped structure. And so from the logical point of view, we are trying to emulate this autoencoder using logic. And so it would also be a neural network. And so I argue that, for example, this is a deep neural network, and we can replace the activation functions with polynomials, and then it would, the whole thing, because the composition of polynomials would still be polynomials, so it would be a very complex polynomial system of polynomials. And I guess Ben Goertzel, many years ago, he has also talked, expressed the same idea. He says that AGI is like solving a huge system of polynomials. That is the learning process of the AGI. And so my idea is to push the Curry-Howard analogy so that we can understand these algebraic polynomials as logic. And so, for example, this is one polynomial neural network. And it is just a very simple example, just a starting point for me to, I'm about to finish, but so this is just a starting point. And I want to say is that I'm not 100% sure that this is working, because the neural network is just doing some kind of classification of the state into in this picture, it is just doing some I mean, it's using some layers of neural network to classify the world data. And I'm not sure if the looking at these layers as logic is completely justified. Yeah, so that's my, I mean, this is my latest idea so far. And I apologize that I did not prepare this talk because I have some real life matters. So I didn't have much time to prepare this. Okay.
Thank you very much, King. And of course, for everyone who wants to dig in deeper, read all the way to the conclusions, the papers, all the accepted papers for the conference are on the website under the accepted papers tab. There are also a number of videos submitted by papers and the posters as well. In particular, Michael Timothy Benefit's videos are excellent, and I would completely recommend them. So as our next speaker, Mike, please come up. And your second paper is, computational. I just put it down.
That's it.
I got the first word right. Computational dualism and objective superintelligence, which I want to hear about objective superintelligence. So. Thank you.
Thanks. All right, so this is building on the same formalism as yesterday, and this is all part of the same ongoing thesis. And yesterday I mentioned an upper bound on embodied intelligence. So yesterday's paper was on complexity versus weak constraints, and here it's this objective upper bound, but also another concept that I call computational dualism. Now, I'm going to argue the idea of software intelligence is flawed. You might remember from yesterday that we had this complexity-based measure of intelligence, Legg-Hutter intelligence, and it's measured with respect to a fixed UTM. And that ARC-AGI is the most intelligent agent according to Occam's razor if it uses the same UTM, right? So they got matching notions of complexity. Then according to Occam's razor, ARC-AGI is optimal, but you never know if you're going to get the right interpreter, right? So this undermines all the previous optimality claims for ARC-AGI and resulted in the paper yesterday. But I would argue that ARC-AGI also reveals a sort of a deeper flaw in the idea of software intelligence. And that is that what software does depends on how you interpret it, the hardware that interprets it. And you can think of it like this nested structure of a software mind interacting with the world through an interpreter. And it's sort of like almost a disembodied notion of a spirit, a bit like sort of a disembodied version of what Joshua was talking about with animism yesterday. I really liked that talk, by the way. But take it to its extreme, this kind of characterizes software as immortal, and people have talked about this. Hinton has spoken a lot about, immortal versus mortal computations, and it's a really catchy way of framing it. And, as the next keynote is about this very topic. In fact, Alex Orobia and Friston have formalized mortal computation. And I really like this direction because I think that immortal computations don't exist. The reality is that software is the state of hardware. And the distinction between hardware and software is kind of reminiscent of some ideas from 16th century philosophy, namely Cartesian dualism, which was the idea that Descartes thought that you had two substances, mental and physical, and that the mental affected the physical through the pineal gland, which acted like an interpreter, and then the physical affected the mental the same way. And now, there were problems with this that people identified pretty quickly. And today, philosophers talk about things like embedded, extended, inactive, embodied cognition. But when we talk about software intelligence,
if AI is the sort of engineering branch of philosophy of mind, then we're still talking about dualism in a way. And I'll call this computational dualism because it kind of mimics this mental and physical substance idea by talking about software interacting with the environment through hardware, which is actually a bit like the pineal gland. Now, I'm not saying this is just, straight up another instance of the mind-body problem. This is a slightly provocative name. But, and software and hardware are very useful categories when we talk about applications and actually building real-world products, but it has thwarted our ability to model upper bounds on intelligence. If we want to make claims regarding objective behavior, not the subjective interpretation by a UTM or something like that, we must avoid computational dualism. We need to formalize hardware and software together. And that is how this whole project started. So if the interpreter is the problem, then we need to get rid of it. We need to formalize the environment and mind as a single thing. And I mentioned that philosophy has, moved on from dualism. They now talk about, the mind as a process within the environment, as an interaction between organism and the surrounding world, as cognition is something that is enacted rather than simply passively sort of thought off in some ether. And this idea, this inactive cognition, is often seen as at odds with a computational description of the world because computation usually talks about interpreters. And, it's a great point. If we have, an organism as an interpreter, we have to talk about, well, where does the organism end? Where is the boundary between the organism and its surrounding environment? What's part of the interpreter, what's not? Why is one interpreter chosen and not another? To get around that kind of problem, we need to move the interpreter outside the environment. We just say, the interpreter is the laws of physics. And what we're dealing with here is a mind and environment together. This is an attempt to unify computation and enactivism by bringing in something called pan-computationalism, the idea that everything is computation. Now that can be, depending on how it's interpreted, a controversial idea. Here I'm just referring to a very basic notion of computation as things like cause and effect, as information processing. So a very weak notion of pan-computationalism. And so then, just to give an overall summary of this paper, we start with the question of how do we formalize objective rather than subjective behavior. As yesterday, we're building upon that same formalism, but here the emphasis is really on the body as an abstraction layer that implements a formal language. Now, yesterday I talked about a sort of a post-structuralist take on the environment as every fact is the set of states in which it holds. So this is saying that a body is implementing a language in the same way that I was talking about an aspect of the environment yesterday. And then goal-directed behavior is a task written in that formal language, which is to say we don't talk about goals separate from our body by default. We talk about them as embodied goals. Now, I'm also going to talk about them as separate, but that'll come in a bit. Because then we characterize intelligence as adaptability or sample efficiency and generalization. This whole project started as an attempt to solve Chalette's ARC dataset, then formalize that aforementioned disembodied goal. So now we can find the ideal embodiment to approach a particular problem or task, and then prove an upper bound on intelligent behavior characterized in this manner. So you could think of it as finding the ideal body for a purpose. Now, like ARC-AGI, this is impossible to build. You'd have to search an infinite space of bodies, but it's useful because we can then reason about objective rather than subjective upper limits on behavior. And it has potentially very different implications with regards to things like safety. And it gives us a clear target to iterate towards by identifying the ideal body. Now, you don't have to worry about the math for the sake of this presentation. I'm just showing you that it's here. And I'm showing you these diagrams that I showed you yesterday with the correct labels here. Now, you might recall that a program is a set of states. Truth of a declarative program is determined with respect to states. So this is how, if we want to talk about a body as a language, as an aspect of the environment, we can talk about the body as this set of statements that can be made by taking sets of declarative programs. And then we can say that, well, when a body is in a particular state, as in I have my arm up here, this would be like a statement, X, in a formal language. And that constrains what else the body can do to this extension of X, right? You could think of X as an input or a beginning position, and the extension as the possible responses to that, the outputs. And so that lets us formalize tasks and talk about things like Chalet's ARC dataset. Now, if we're thinking about statements as inputs and outputs and constraints, then input is like a constraint on the possible outputs. We can use a second statement as a policy and constrain the outputs to just correct outputs by some arbitrary notion, like one of the ARC problems. Now, this kind of harkens back to some notions of embodied AI from people like Heidegger and Dreyfus. And there's this great quote from Rodney Brooks, which says, "The best model of the world is the world itself." And the reason I bring this up is because really what I'm just doing is constraining the possible outputs. I'm not making any comment about possible world models or anything like that. And the reason I want to frame sort of goal-directed behavior and inputs and outputs this way is so I can talk about embodied generalization. So you could think of a hammer as a policy, and a hammer can generalize to different tasks. It could be a weapon, it could be a paperweight. This is just an intuitive example. And then we can talk about learning as being given a small task, a small set of examples, and generalizing to a much bigger task. And you could think of an organism's history as different tasks. Now, you recall these past results from yesterday's presentation. The weakest constraints expressed by the weakest policy is the optimal choice, but that weakness depends on the embodiment we choose. And we want to know which body is best if we want to identify a superintelligence. So we can measure the utility of choosing weaker policies for a given task and a particular embodiment by taking the difference between the weakness of the weakest and the strongest policy. That is to say, if I give you a task like press a red button, being more intelligent is not going to make you much better at it. You're just going to be pressing the red button. But if I give you a task to play a game of chess, there is a lot of potential for you to adapt and improve. And that's what this expresses, is your potential utility of intelligence here. And then to find out what the best possible embodiment is for a particular task, we need to be able to switch embodiments. So we need to be able to represent the same task in different, using different bodies. So I've got this notion of an uninstantiated task, which takes which is a function from possible embodiments, that is a set of declarative programs, to tasks in that using that set of declarative programs. So it takes a body, returns a task. And this allows us to take the same task and compare it across different bodies. And when we do that, we can identify the one that maximizes this utility of intelligence. And that's what I then show as the upper bound, that if we are allowed to just use any body, that is any abstraction layer, then the upper bound is the body that maximizes that utility of intelligence. Or it's the most intelligent body for a particular purpose expressed by the uninstantiated task. Now, downside of that is, as I mentioned, it's incomputable because you'd have to search infinitely many bodies, but it does let us talk about things like superintelligence and what an upper bound would look like. And it kind of suggests that AGI might be a little bit safer than some of the rhetoric might indicate, that if you have to search through an infinite set of bodies, this is probably going to slow you down. There's no shortcut, really. But it gives us a target to iterate towards, a target to aim for, that if we want to solve something like the ARC dataset, this is how we find a set of primitives to work with that convey, as Chalet put it, a strong inductive bias. And I think, I know yesterday when Joshua was talking about the animism thing, he was talking about computational functionalism as sort of a prerequisite. I think that, but I think ideas like his cyber animism would work really well with this. I think we would just need to, well, essentially formalize how different states of hardware interact to talk about, these animist spirits that he was getting at. Yeah, oh, and since people requested more eyeballs. This is pretty much the end of this part of the talk. I do have a poster as well that's related, which is about the hard problem of consciousness and abstraction, again, based on the same formalism. And it relates also to my papers last year and the year before. I've been formalizing some of Michael Levin's ideas with multi-scale competency architectures, trying to integrate that with the work of Alex here and on the model computation stuff. And I have been going to philosophy conferences and talking about things like causal learning and specifically a neuroscientific notion called reafference, which is where this would tie in with the consciousness stuff. So here is a preview of that poster. That's everything.
Thank you very much. Go ahead and leave it on. We'll do a couple questions real quick.
Oh, okay.
Well timed. Excellent. Very much appreciated. So we have a little bit of time for a couple questions for Michael or our two online presenters. And is there any questions to take?
Yep.
There's a mic over here coming through. I've got one from virtual. Let me ask this quickly. Is this effectively using, I believe this is, I assume this is for you, using the physical laws we find ourselves subjected to as the reference machine, UTM, to get to an objective way of measuring complexity, intelligence, etc.?
You could definitely think of it like that. I mean, it's in formal terms, it's more abstract. It's taking this whole like post-structuralist notion of we don't know what the physical laws are. We just know that there are, presumably some physical laws dictating the relationships between states and what declarative programs will be true in any given state. But you could think of physical laws as the declarative programs which are true of every state. So, yes.
Cool. Thank you.
Hi. This made me think of temporal logic of action. I don't know if you're familiar.
I'm not, but it sounds like something that I'd like reading about.
It's work by Leslie Lamport, who also invented LaTeX. It's about formal verification. So you define a system with logic, and then you can actually run the system and test all your properties and characteristics of your logic system. So I was wondering if you also do something similar to that, or is it just definitions? Do you have a way to experiment with your formalization?
Yeah, I mean, I do have some experimental results. Oh, it's gone. But those experimental results I published last year, the graph. I mean, initially my planned experiments were with the ARC dataset, but I was programming in Python using loops, and I realized that I was trying to, brute force 30 by 30 by 10 grids, which was ill-conceived. So I just did 8-bit string prediction. And I do plan to scale up more experiments once my thesis is done. I'll go back to the ARC dataset. Is that what you meant?
Yeah.
Sorry.
Any questions for our online presentations? All right, fantastic. Thank you all very much. Thank you, Michael. Thank you, Ken. Thanks, Vincent. Excellent presentations, very informative. It's excellent to see this space opening up. So next, I'd like to welcome to the stage Dr. Alex Arobia. He's going to talk about back propagation of errors, predictive coding, and biomimetic. So Alex Arobia is an assistant professor in computer science and cognitive science, as well as an affiliate professor in psychology at the Rochester Institute of Technology. He also serves as the director of the Neural Adaptive Computing Laboratory and has long argued against backpropagation of errors, the workhorse algorithm behind deep learning. And his body of work advocates for a biomimetic approach to intelligence and computation. His research group investigates questions related to neurobiological credit assignment and develops mathematical models for spiking neuronal dynamics and synaptic plasticity, predictive coding, and active inference. So please welcome Dr. Alex with me.
Mic on.
Hello, and thank you for the introduction. I'm excited to be here and to talk to you about some things about biomimetic intelligence. But first, a minor correction to my title slide, although I didn't format correctly. I'm a little disappointed, but that is saying getting rid of, based on a discussion I had with one of you yesterday. Apparently it was viewed that I was going to say we are doing neo-backpropagation, but I'm essentially saying we want to get rid of. So just so that we were clear about the premise of this talk. So we are obviously here because of AGI and our interest in the subject. But oftentimes in the media, especially from the world of machine learning and machine intelligence research, we essentially are hearing the bells sound that AGI is already upon us, perhaps even in some instances, as our morning keynote speaker said, a few years out. AGI is around the corner. But some of you might wonder, really, is it? And of course, I have here, besides mentioning that the machine learning community has continual monthly breakthroughs every minute saying, yep, we've solved this problem, we've solved that. You probably recognize none other than ChatGPT, which is a generative pre-trained transformer, or just a deep neural network with self-attention weighting. DALL-E, which is also a transformer. Midjourney, which is a transformer tied together with a diffusion network. All of these, of course, are trained with calculus and a tool very well known as backpropagation of errors, which will be part of our talk today. And of course, there's the idea of these overpromises that these generative pre-trained transformers are all we need. As you can see, that was literally one part of the title of one of the first papers that started the trend in deep learning, which is insert phrase is all you need. And of course, we saw Francois show as well this paper, which is part of my subject of criticism. So this is also not new. History tends to repeat itself. And of course, I mentioned someone who is actually an instigator of some of the earliest criticisms far back. As you can see, 1965, Dreyfus and his criticism at the time of good old-fashioned AI, as some of you might know the phrase. And the idea was back then, formal rules and explicit conscious symbolic reasoning was all you need. And a similar set of bells were alarming, essentially telling us that we had AGI around the corner. And any criticism of this view was typically met with hostility and ridicule. Then, of course, a little bit later on, and Dreyfus's comments sort of are the predecessor to giving rise to connectionism and the alternatives to symbols and doing subsymbolic processing. Later on, kernels took all the rage in 1990s. And again, kernel machines were thought to be all that you need. And any criticism, especially deep neural networks trained with backprop, were met with ridicule and hostility. As we can see, my friend Jeff went through tough times. And many times his ideas were laughed at or scoffed. And of course, we can see none other than Francis Crick. You might be familiar with DNA and RNA, and he was one of the earliest critics of even the coming wave of deep learning before it was called deep learning. It was just neural networks or artificial neural networks. So again, you might be wondering, are backprop and deep GPTs all that we really need? And we can already start to poke at the problems, and many of us are aware of them, as it's encouraging to see at this conference many different criticisms addressing their weaknesses. There is this concept that is emerging in the field of machine learning called red AI. And effectively, red AI is saying we have machine intelligence, but when we conduct our experiments, we leave a massive carbon footprint. We are effectively burning holes into our ozone layer to train a very, very large language model. And since we believe bigger is better, that carbon footprint only increases. So even the statistics that I report in the body of work I'm going to briefly talk to you about today is already falling quite behind, as my estimates will be old. They're worse than what I can tell you today. And of course, you need hundreds of technicians to run these multi-GPU systems. And addressing these issues is going to also be important for democratization. So many of us are not going to, and as Francois had mentioned in his talk, these big tech companies and these particular labs are the ones that can just train bigger and bigger models because they have the money to pour into burning the energy required, while many other groups don't have access to these resources. Although there is work, I will point out, trying to compress these models and try to address some of their energy inefficiencies. But this is important. We want the opposite of what I have on the slide. We want green AI, which is another emerging term in the field of machine learning. And at least it's encouraging to see some of that discussion. We also have with generative transformers, generalization issues. And again, this applies to all deep learning and backpropagation-based approaches. And oftentimes when you design your architecture, even though you might be using a pre-built model, if you want to start messing around with how things are designed, you often have to do things to please the training algorithm itself, and instead of focusing on oftentimes the problem-solving mechanisms you want to build into your model. For example, the most important problem is, let's say you want to use a discrete operation. You want to work with spike values, 0 or 1. Or you want to work with integers. This is going to be very difficult, if not near impossible, with a training algorithm that requires the entire system to be fully differentiable or smoothly differentiable everywhere. So already you are constrained in what kinds of models that you can build, let alone anything more interesting in terms of biology. And of course, we have other problems in terms of generalization, such as weak out of distribution generalization, when we are essentially moving far outside our training sample, even though the premise of classical statistical learning was about generalization and avoiding overfitting and dealing with underfitting issues. We essentially are now building huge, massive lookup tables, approximate neural lookup tables trained on the entirety of the internet, aggregating the average human experience. However, this isn't quite generalization, and again, Francois mentioned some issues with a memorization or memory-centric approach to learning. And then, of course, something I like to mention, as my research group has studied over a long period of time, catastrophic forgetting is actually, despite what you might be led to believe, largely still an unsolved problem. It is much, much harder to train a deep neural network or a deep system that can effectively learn multiple tasks in an order and without forgetting old knowledge that it has acquired. There's millions of approaches that are backprop-centric, and many might say continual learning is a solved problem. We can now worry about other things. However, there's a lot of tricks that hide the problem, and so that is something that we still need to be aware of. So what could we turn to once we think about maybe backprop and the fundamental way that we do machine learning and machine intelligence might have issues or might lead to some roadblocks? Doesn't mean that's not useful, but it might not be the pathway towards AGI or general machine intelligence. And again, we actually have some of the lumineers and pioneers of deep learning also helping make those claims, or at least they once did. And so, as you can see, Jeff has been one of the earlier critics as well. And then we see this idea that maybe we need to look to other areas, perhaps more strongly towards neuroscience. A lot of deep learning is loosely inspired by the way that neurons work. As I will briefly show you later, they are gross simplifications of really what neurons do, which might be cheating us of some rich mechanisms that could allow us to tackle these problems that I've told you earlier. And again, there's more. There's this word phrase that came out recently, even though many of us have worked on this topic for a long time, called neuro AI. And again, you might see some names that you recognize as these initiatives start to come forward and argue for a new way to tackle intelligence or machine intelligence specifically. And again, there's more reviews, names you might recognize. And of course, we saw in the last talk a mention of this work, but all of these sort of lead towards this last concept, which, funny enough, I will only be briefly talking about, as it in and of itself could be worth 2 or 3 talks as a topic. So, as also part of the title, I had the phrase biomimetic intelligence. So what do I mean by biomimetic? Obviously, we know that we are mimicking biological or nature or natural entities. And so we want effectively bio-motivated self-organization, adaptivity, something called structural selection, which I will touch on briefly again as well at the end of this talk. Bioplausibility is also not a niche property of interest solely to neuroscientists, which is oftentimes the ridicule that those that work in bioplausible learning face today by reviewers, often saying, backprop's good enough, it's all you need. So why do I care about biorealism or maybe caring about how neural dynamics actually work? And a very, very clean argument and counter-argument to this is energy efficiency. As I just mentioned earlier, if you want the opposite of red AI, we might need to look at how we do our actual fundamental computations. Things like sparsity is something that isn't really a big component of modern-day intelligent systems. We have very dense, real-valued, massive vectors and matrices to represent everything. That doesn't really work well on hardware. Hardware really likes things like 0 or 1. And if we could get closer to that, that might help deal with this problem of carbon footprint. And of course, you might wonder, and those that might dabble in biological-inspired learning or computational neuroscience or cognitive neuroscience, how much detail do I really need? And it is still a pretty difficult question because if we're not interested in just faithfully modeling the system, how much do we need to help us go on the right pathway or a potentially useful pathway for machine intelligence? Well, none other than Albert gave us a great phrase that I think can give you a thought. Everything should be made as simple as possible, but no simpler. And we'll touch a little bit on what the no simpler might mean, but just to give you the punchline, it's effectively what task you want to solve, what types of problems you want to solve, and what mechanisms do you think neuronal dynamics bring to the table. So again, we might dive a little bit here deeper into what's wrong with backprop. Let's just again zoom into the fundamental computing unit we all take maybe for granted in building our deep architecture. So on the bottom of my diagram, under the slashed line, we have your traditional neuronal unit. It's effectively a pointwise approximation of a vast amount of complexity in biology. And you might recognize the weight values. These are scalars that represent our synaptic strengths. In computational neuroscience, these are sometimes called efficacies, just in case you see that word later in the talk. I'll try to keep the jargon to a minimum, but sometimes it slips out. And you multiply essentially a set of incoming signals by these weighted values, sum them up, run them through an F function, which is your nonlinear activation function, and that's it. You put a bunch of these together, you build multiple layers, you have effectively the deep learning network I showed earlier. There might be some other mechanisms, as transformers do have cross-attention mechanisms, but they're effectively just more linear algebra piled in. To the top, above the slash line, we have an actual cartoon depiction of an actual neuronal unit. And just briefly, we're not going to go into the complexity of all the neuroanatomy for this talk, but effectively we have our dendrites, which are the receptors that receive the actual signal from incoming neurons. Then eventually a neuron builds up a membrane potential or a voltage value. It just basically accumulates a signal. And again, this is bioanatomy. And it essentially builds up to a certain threshold and releases what's known as an action potential or a spike. And that transmits along the axon, this electrical signal, and then to the synapses, which are effectively the connections to other neurons. Really, they're actually neurotransmitter synaptic junctions, which we'll briefly touch on in a later slide, and those are received by other neurons. Just even that mechanism in the dendritic trees and the complexity of neurons is nowhere to be found in our deep learning architectures. So maybe if we look deeper at how neurons work and maybe build more faithful models, including how they learn and adapt, there might be some value that we can bring back to machine learning, and I will try to briefly convince you with some results that my group and my collaborators and others in the domain have pulled it together to try to show an alternative to backpropagation. Obviously, these are very different. So backprop, I'm not going to, again, go through the pedagogical tutorial or walkthrough of exactly how backpropagation works, but you might be familiar if we do a left to right type of processing. X is your input. We take our input vector, we transmit it through a chain or pile of linear algebraic transforms. We just do matrix multiplies, run them through our activation function until we reach this output layer where I have this fancy L that represents our cost function, which is a function of our parameters, our inputs, our target outputs. We compute a derivative of that, and that's what that fancy delta symbol really is. It's the first derivative of the loss function with respect to a particular layer, and then we just go backwards. We essentially have to follow the exact same pathway that we took from left to right. Now we have to go right to left. And biology doesn't do that. There's absolutely very little to no evidence of this particular form of coordinated global backpropagation. There is a backpropagating potential, but that's not at all what backpropagation is emulating. However, it is good to remember some of the pioneering work, and I will try to keep that, and you can look up these references if you're interested. That was where one of the repopularization of backpropagation came from. Obviously, Leibniz and Newton invented essentially the first predecessors to this, but I'm not showing those references. So, again, I'm not going to go into every single problem. I recommend reading some of these papers, particularly maybe the survey at the bottom, that goes into excruciating detail as to what are all the problems behind backpropagation-based learning. And again, those are potential areas to innovate on or try to avoid. However, I'm just going to highlight 3 basic ones. These other problems down there, if we're interested, I can talk offline with anyone. But the idea of the weight transport problem, this is really more of a biological memory kind of issue. The idea is that when you are forward passing your data or moving data from the bottom to the top in this case, you can turn it over from left and right. We essentially have a weight matrix that represents all the synapses, and we do a multiply, a matrix multiply to be specific. Well, when we go backwards, we have to reverse pathway our signals. So what you do is you take that matrix and you do a transpose, and then we multiply the derivative signals backwards. However, in biology, there's absolutely no reuse of synapses when we go backwards. It is a nice little efficiency in terms of memory savings, but we're cheating ourselves of biological recurrence and rich temporal dynamics, which is something we will touch on today on predictive coding. And again, that's the my rightmost or your leftmost problem. The middle problem is the forward locking problem. This one I think is more prominent in the sense that when we do a forward pass, any single layer that I have, and I have this it depends on, doesn't exist at all, technically, until the layer below exists. So a neural network, its neurons are null. They don't even have the value of 0. There is no temporal nature to them in most feed-forward networks. I'm not going to touch on recurrent nets. They have their own issues. And until you plug in data, you just have a pile of matrices waiting to do something. And so the first layer doesn't exist until data below exists and you do the matrix multiply. The second layer doesn't exist until the first layer exists, and so on and so forth. So you can't parallelize the layers. You can't use any form of model level parallelism easily. You can hack it. There's deep learning work that tries to do approximations, but you end up resorting to approximations that have high error. The same thing, so that's the inference or the forward pass of our model. Inference just means we are answering a query given input data. The update locking problem is also the learning or the backpropagation version of the same problem. I cannot compute the way to update for the bottommost matrix W1, that's the triangle delta, until I have the derivatives of the cost function, little delta 3 and little delta 2, until I can go all the way back to the bottom, I cannot make an update to those weight synapses, whereas in the brain, everything is inherently local and immediate, or at least time immediate. There is no waiting for a synapse to change its particular strength or efficacy while other neurons learn. Things are very Hebbian-like. You might know that phrase, neurons that fire together, wire together. It's an approximation of what he says, but it's a useful thought to bring to the table. Just another mention, credit assignment is the blame game or the credit game that we play with neurons. When we have a cost function, we like to tell how much a neuron is important for how much it contributes to a cost function. And then, of course, recurrent neural nets, you could say, well, I can make them have a state, and yes, you can, but to train them, you just treat them as one massive deep network. You basically unfold the mathematical recurrence or relation that constructs the recurrent network. And you build a very long network, you stretch it over time, and then you do normal backpropagation, but now you do it across T rather than just across the layers. This is obviously worse and even far more biologically implausible, as the brain doesn't go ahead and copy itself, stitch it together back in time, create a time machine, and then update all the weights simultaneously, and then roll it back up and say, here you are at time T. I'm gonna have to keep doing this every single time step. So backprop through time is even worse, and one of our biggest enemies in biomimetic intelligence. So again, what's the whole point of pointing out these problems? Again, backprop and deep networks can be useful for very specific applications, and obviously they are doing really interesting things. However, the argument from biomimetic intelligence is perhaps we're not working with the right set of building blocks. Backprop is easy and fast to use, and the things that I will talk about briefly today are a little slower in terms of simulation, unless you go to the neuromorphic computing and the actual speed that's afforded by analog hardware. Recurrence is easier to get rid of. Transformers actually, I come from the era of recurrent neural nets. Transformers just do time windows, essentially rolling windows in time and make everything explicit, so that way you can just be one big feed forward encoder decoder, and we don't have to worry about unrolling recurrence relations. However, you're cheating yourself of the ability to capture long-term dependencies in data. It's almost like not solving the problem. It's just, we'll just build a lesser model to approximate time. Point-wise, neurons are easy to use, and there's nothing bad to say about things that are easy to start with. And there are, again, like I said, lots of applications, but there might be insurmountable roadblocks. With the way that we do deep learning today and build transformers, we will obviously not be able to tackle easily the energy inefficiency problem. And again, this also relates to how we do computing, which I will touch on very briefly towards the end, and the other problems. I also like to mention my group works on reinforcement learning. The sparse reward problem is still a holy grail. It is really, really hard to do deep reinforcement learning, and biology sometimes offers some really nice tricks, and there's lots of nice work out there that shows you how to avoid the problems of sparse rewards to a degree. So the message is really, if you take away anything, maybe we haven't tapped into the full value of what real neurons and neuronal systems have to offer. So I'm just going to show you the galaxy of algorithms that are out there. I am not going to spend the time talking about every one. Those will be here forever. I do recommend reading some of the work that is cited. I will make these slides available to everyone as well on my public page, so that way you can look at the work and read it for yourself. So of course we have backprop. I'm not going to unpack these diagrams, but we know already how it works from the discussion earlier. Feedback alignment is just an algorithm that tries to deal with the weight transport problem, use random matrices in place of the forward matrices. Local representation alignment tries to introduce things like errors at every layer, and it's motivated somewhat by biological considerations and helps address a few issues. It can work without derivatives. That's really nice. Target propagation is another mechanism where we take the idea of autoencoders. It actually comes from an older idea called recirculation, where we're just using inputs of encoders and decoders and comparing them a few times or a few time steps, and then computing errors based on that. Again, if none of this makes sense to you, it's okay. It's just to show you that there's a lot out there besides the thing I'm going to talk to you about. We also have things like competition among neurons that can serve as a really nice mechanism. And we have Hebbian learning, as I mentioned earlier. And you can do things like contrastive Hebbian learning. And that one has a pretty long history. In fact, even in cognitive science, Boltzmann machines, you might know that word, have been used quite a bit. And they're very interesting, but we're not going to talk about that. More recently, you might have heard of Jeff's forward-forward algorithm, or maybe the predictive forward-forward algorithm by Arobia and Mali, or the forward-only learning mechanisms of Cohan's group. And these are just algorithms that say we don't want to have feedback loops. We want to learn with only the forward pass. That, too, would be a talk in of itself, but just know that there's work out there if you don't like feedback. But we're going to use feedback today. Okay, so there's a lot of things, and that's only a tiny sample of what's out there. Terry Sajanowski once said to me in one of his talks that there is a galaxy of learning algorithms in his opinion, so I like that phrase. But you can organize these. Before I show you the brief taxonomy, you might recognize again our deep neural network, and that's in the middle. That's our dot and arrow diagram. And of course, to my far right, your far left, are two real synapses, or sorry, real neurons, I should say. And we have a presynaptic neuron. I just want you to be familiar with that phrase. Pre means before the synapse, and post means right after the synapse. And the idea here is that we have a representation of each one as a little circle. And these neurons are connected by dendrites and synaptic junctures. But of course, when we talk about linear transforms in deep learning, you shouldn't call it a presynaptic activation function or a presynaptic vector. It is just a pre-transformation, and we dump it through another nonlinearity, and that's called a post-transformation. That just helps, and if you read the literature, it can help you disambiguate the neuroscience from the deep learning. So okay, we know that the dots are the arrows. Oh, I'm making noise here. And of course, what do we mean by learning? Learning is going to be the idea that we're changing our weight values. That part carries over. We're changing connection strengths. However, we understand that in biology, these are the gaps in between the synapses, or rather the dendrites and the synaptic cleft. And the idea is that neurotransmitters are moving across them. So we're kind of dealing with neurotransmitter chemicals. But that's just to give you a little biology. So again, you can put these into a nice little taxonomy. The model to your far left is essentially breaking down the machine learning pipeline into base components. And you can break it down into your architecture. So what type of model structure do you have? Your cost function. Sensory stream is your data. You have maybe your inference algorithm if you designed one. How do you answer queries from your model? Credit assignment is obviously the subject of the talk. It's our learning process. And optimization is decoupled. So if you know stochastic gradient descent or ADAM, these are just optimizers. They say, give me a change and I will apply it. So we're keeping optimization a little bit separate here for now. That way you can use them if you're using credit assignment. To your far right, inside the circle, is all the possible algorithms. Actually, there's a lot more. These are just a representative set. And you can build a family tree. I'm not going to go into what this tree means because we only need to zoom into one of them. Particularly discrepancy-based. Again, I refer you to work if you would like to see how all the algorithms over the last several decades of research, going back to 1960s and earlier, how they're organized and how these thoughts relate to each other. So we only need to zoom in, so thankfully you don't have to see all the different algorithms. We're going to talk about discrepancy-based, and discrepancy just means mismatches or comparing one thing to another. And we're only going to talk about one algorithm in it called predictive coding, which gives us to the final bit of the title of this talk. So what is predictive coding? Well, predictive coding, and I'm going to give you the crash course, very high level view of it. It's this idea that we have layers of neurons, so you could build a deep neural architecture that's very similar in structure. However, every layer of neurons tries to guess the state of the other layer of neurons. That's kind of the basic premise. So the idea is that the brain itself is a hierarchically or heterarchical. That means it's not necessarily strictly one layer above another. It could have skip connections and recurrence in all weird ways. That essentially is a big generative model. This is the predictive engine hypothesis that comes as early as von Helmholtz, actually. Got to give him credit. And also Immanuel Kant talked about very, very early versions and conceptions of the idea that the brain is one big predictive engine. And we're going to construct a chain of these little predictors to build a predictive coding network. I also like to mention some of the most infamous works that kind of proposed variations of these ideas. And a lot of the work has been in computational neuroscience to just recover certain effects that we observe in real neurons. But you can bring them back into machine intelligence and get some really cool properties, as my lab likes to show and my collaborators and friends. Sparsity is another important part. It's not part of the name, but it is an important component where essentially we want lots of zeros. The more zeros you have, especially in the layers of neurons, the more likely you're going to have efficient compute, because 0 is really good for hardware. We don't need to do the operation when it's 0. We only need to do it if maybe it's 1, and we have a weight of 1. Yeah, this is just me highlighting the diagram. Obviously, the estimator is you. You are a big set of predictive coding circuits. We're not going to put a cognitive architecture right now about it, but obviously you would want to do that. And then you have the world, which is your sensory stream that you are actively trying to predict. I'm also going to keep action out of it, although that is a very important part of biological systems known as active inference, but that's a different subject. And again, I just show you here, you can look at these slides later, there is some neuroanatomical mapping between the model, the little pieces of predictive coding that I'm going to introduce to you today. But we obviously have our generative synapses, which is just basically synapses that connect one layer of neurons to another. Basically, it's what allows them to make a prediction of one layer of activity. We're also going to introduce this other concept that isn't in deep learning, error neurons, which are just little neurons that are specialized, that take a target value and a prediction, and they subtract them. Turns out they are actually the derivatives of local distributional functions that we're not going to have time to go into, but there's really nice work there, and you can do things like precision weighting. And again, I refer you to some work that kind of gives you examples of how these things are derived. But I think it's better to show you a very simple pedagogical example. So let's just build a 3-layer neural network. The very bottom is just a floating neuron. And by the way, these neurons have inherent temporal nature to them. The idea is they are always something. They're either 0 or some real valued number. They could be negative, depends on what kind of circuit you build. For now, it could just be a floating point number. So these are literally just one neuron. And this neuron at the very bottom of the diagram wants to predict the neuron in the middle. So that's neuron 2. And the neuron in the middle's goal is to predict the activity value, or what state the neuron is, at the very, very top. And the diamonds are one single error neuron. And that's pretty much all we need to build your very own predictive coding circuit. So again, step 1, when you're doing a predictive coding circuit, and this is one way to build the model, you generate your hypotheses. So every neuron has a guess what it thinks the other neuron's state will be. So the neuron at the very bottom emits a guess, and that guess goes along that solid arrow with the diamond, and it gets deposited in the orange diamond, which is right now not highlighted for you. So it transmits and deposits this little prediction into there, and then the neuron in the middle deposits its little prediction in the diamond at the very, very top. Notice something, we already have parallelism. We've solved the forward locking problem that I mentioned earlier, because the neuron at the very bottom doesn't depend on the neuron in the middle, and the neuron in the middle doesn't depend on the neuron at the bottom, and so on and so forth. So immediately you've already solved the forward locking problem, which is quite huge. So we have natural layer-wise parallelism, or natural layer-wise neuronal parallelism. So what do you do when those little predictions are deposited inside the diamonds? Well, now I highlight them for you, and we need a target. That's the only last piece we're missing to compute an error. So now we take the state of the neuron that prediction was meant to predict. And for example, since the bottom neuron wanted to guess the state of the middle neuron, all we have to do is take the actual current state of the middle neuron and deposit it in the error neuron itself, and you're good to go. Now you can do like a subtraction, and that's one of the simplest things you could do to build an error mismatch signal. And the same thing for the very top neuron, right? We just transmit its value into that diamond. Now, again, these neurons don't have any data associated with them. What you can do is at the very, very tippy top, and I realized I forgot to put the label, you could set that equal to the data. So let's just pretend you have an image of pixels. And in this case, it's a 1-pixel image, so it's not very interesting. And the idea is that neuron represents the data, and all the other neurons have to figure out what their state should be, so that way they can accurately predict that data point that's clamped to the very top. And obviously, they're not predicting that data point directly, they're predicting each other's activities. So we compute our error, pretty easy. Then after that, we take those errors and we transmit them back, but not along the same forward synapse that we used to make the prediction. We transmit them along a feedback synapse. This is a separate synapse, has its own values. You can simplify it and set it equal to the transpose, but biological models like the works that we do in our group, it's just a separate synapse that will learn itself. And we transmit that back. The error at the very top goes to the neuron's current activity in the middle. And then obviously the error neuron in the middle transmits its value to the neuron at the very bottom. And what they're doing is they are depositing the perturbation into that neural activity. That means they are shifting its value to that way when it makes a prediction in the next time step, it'll be a little more accurate. And this is it. So basically it's like guess and check. All the neurons make their predictions, we compute the errors, and we feed them back. The only other thing you might notice is in the middle neuron, this is actually a really important part, and in neuroscience it's called retrograde signaling, which means we can kind of get a little bit of a backward signal in neural synapses. That diamond transmits its value to the middle neuron, but we take the opposite derivative. So it's just multiplying it by -1. We can talk offline if you're interested in the math behind that. And that's a top-down pressure. So once you do all that, you're good to go. You've now implemented predictive coding's inference algorithm. And we just go back to step 1, and we repeat this as many times as you'd like, or depending on what you want to do in your stimulus window, you do it for t steps. And that's pretty much it. Now you might say, well, wait a minute, how do I'm changing the values of the neurons, which by the way, we don't do anything like that. In deep learning, we don't have any form of short-term plasticity, which is what we just modeled. But how do I modify the synapses? Well, it's really easy. Once you do t steps of this in this particular model, you have your neural activities. Remember, these error neurons are going to change with time, so you already have an error. All you have to do is Hebbian learning. Take the error, the value at the diamond, multiply it with the gray circle at the bottom, whatever its current activity value is, and you have a signal to change your weights. Since I'm hiding most of the math from you, I'm just showing you a pictorial diagram, but obviously you can compute your delta W's. And you can do the same thing for the feedback synapses. They actually have a really fun little form that, the work that I refer to gives you some answers on how to build. So these synaptic adjustments are made dynamically. And notice too, you can calculate everything you need to change every single synapse because all you need is the presynaptic neuron and the postsynaptic error, which is the diamond. So you just multiply those two values and you have simple Hebbian learning, and this works really well. Now, that's it. You guys are all now experts in predictive coding. Congratulations. And this is really nice because there's a mathematical grounding to all of this. It's essentially optimizing an objective known as the variational free energy. I'm not going to get into the free energy principle in much detail in this talk, but that's effectively what predictive coding embodies, and it commits you to certain theories if you're interested. But the idea is that this type of circuitry, since all these neurons are local and they learn with little Hebbian rules and their inference is independent of each other, that means you can also do asynchronous compute, which is also something that's very hard in deep learning. It generalizes to very flexible architectures, and some work that I am highlighting here across my friends and others that have published in the area. You can build brain regions very easily. You can build complex graph networks. And there's some interesting results on actually graph networks with predictive coding from some of the research groups that are out there. What else is a framing bayou? Well, some of those that are more theoretically inclined among you might say, well, but backprop is not too bad. Is there any theoretical relationship with it? Well, if you do a little squinting and some mathematical manipulation, turns out that PC subsumes backprop. Under a case where the errors are actually 0 in every layer except in the output, you can effectively get backpropagation, which means PC is more than backprop. It's kind of like that's a special case, and that work that I have highlighted here points you to all that wonderful theory. And this is a nice little curve trained on MNIST just to show you that actually the generalization is different when you change the magnitude of the error neurons, but we're not going to go into that detail. And you can also replicate the weight updates produced by backprop under some conditions. But let's just show some pretty pictures, because I think that's more fun. You can build for free a generative model. And actually the model that I just walked you through, with a few extra extensions, you can read that work if you're interested, you can build beautiful generative models of digits and Japanese kanji characters, and silhouettes and some of these problems. And it turned out some of this work showed that this was better than variational autoencoders and even generative adversarial networks in some instances, which was really interesting from very, very simple learning principle. And you get all the benefits of, like I said, the layer-wise parallelism. You are not locked. You don't have the weight transport problem. So you get generative models that are really, really good, and they get better. I'll show you some cool pictures later. You'll also see, for example, we also reproduce some very famous classical results. You can work with image patches that are arranged in an anatomical structure, similar to how your eye processes them. My student and I recently showed ourselves for now. This is an upcoming work. You can reproduce classical filters, and they learn little edge detectors from natural images, which are really complicated and way more difficult than MNIST images. So keep tuned for work like that. And of course, there's also work that we showed that these things learn in the bottom layer their own independent filters, which is really nice. They learn these little atomic elements. And the upper layers of the network is like a latent command structure that basically, and I show you with the red things, and again, you can look at the slides to see this more clearly, they correspond to stitching together components, and the upper layers just coordinate what the lower levels do. So they are essentially learning almost like a compositional model, but I want to be careful because compositionality is a very tricky topic. But they learn pseudo compositional structures. And it's really nice because you can actually just take the filters together and multiply them by certain coefficients that are in the neural activities, and you can get fantasies out of the model as well. Like this 0 is not an actual digit that was directly fed into the network. These are a weighted superposition of the bottom layer. And again, the work that I showed earlier shows you how to do that if you want to build your own fun little models. So I just want to end by convincing you of some other things you can do, taking that very simple principle and obviously going further, and there's other biology that we're not going to go into, but I just want to show you that you can do more complex images. For example, we can work with, you get for free a natural image denoiser. So predictive coding isn't trained to denoise like a denoising autoencoder, and we actually showed that you got that property for free, which is really, really interesting in terms of that you didn't have to inject noise at the input, for those that might know what a denoising autoencoder was. So you get image decorruption. It's not perfect. It could probably be improved, but it was very promising. And then another really interesting result from this work was we actually found for free, we got out-of-sample generalization. You could train this network, and I recommend you read that paper. We trained it on CFAR10 and evaluated it on SVHN. Those are pretty different natural image benchmarks. This was able to reconstruct those digits fairly accurately and was actually competitive to autoencoders that were trained directly on it, which is astounding because that's an out-of-sample data set. No relationships at all. So it learns some fundamental generalization in terms of reconstruction, which was really interesting. Also was really interested in seeing what the filters look like. Turned out without doing anything special, it was just essentially generalizing it to a convolutional structure, you got an image pyramid representation, which used to be argued classically what the brain was doing. You learn essentially representations at lower resolutions. So your brain's taking your sensory input and smoothing it and blurring it and doing this multiple layers because the highest level is very abstract and kind of keeps the important information, but we don't need to know all the details. So it was really interesting to see that without any priors or inductive biases put onto this particular model, it got image pyramid-like representations, which was fascinating. These are feature maps, not filters. Oh no. This is not. Okay. Temporal modeling. Time is also a very difficult part. The only thing I want to highlight here is even though I'm showing you this network shown over time, you don't do any unrolling. You don't do anything like backprop through time. It's an online algorithm. You do some other extensions. You can read this work to see how you put recurrence into these. But the idea is that you can do online learning with temporal data for free. You can also do online continual sequence modeling. And we got some really competitive results on things like bouncing MNIST and bouncing fashion MNIST, or bouncing not MNIST, and some really complicated video benchmarks. And we were competitive actually with, for example, long short-term memory, which used to be one of the go-to recurrent networks before transformers kicked them to the curb. So it was really interesting, and if you're interested in learning without backprop through time, I recommend you look into my lab's work on this area. And of course, okay, and then that's just the bonus slide. Uh-oh. Wait, oh, it's going backwards. Sorry. Sorry about that. You can also do graphs. I'm not going to dwell on that for sake of time. I do want to show you one fun little thing, though. In some upcoming work, we're going to show you that we have really nice results on generative modeling with like robotic control. This did not play. Well, there are animations, I promise you. So they are animations, and it shows really complicated generative structures and the fantasy of a robot arm moving, which was really nice. You can also do continual learning. So that catastrophic forgetting problem that I showed you earlier is not so much of a problem when you do a predictive coding-like approach. There is a little bit more to tackling that problem. You have to model the basal ganglia and some information routing work. Some of you familiar with Andrea Stocco's work. This kind of takes that hypothesis and integrates it into predictive coding. And we beat out, those dots are hiding a lot of other baselines. All of those are backprop, and predictive coding blows them out of the water on these benchmarks. And that was really fascinating result. So it was a very promising framework for catastrophic forgetting. And then the last part is dynamic cognitive control. You can build agents with it. And for those of you that are familiar with active inference, predictive coding is a beautiful little circuit that plays perfectly into the active inference framework. I'm not going to tell you what all these things mean, but essentially you can build a little cognitive control architecture with a prior preference, generative transition dynamics, procedural memory, for those that might know what that is, a motor cortex or a motor action model, and you can build a little system that actually works with sparse rewards. And this series of work, also my friend Rajesh had some really promising results dealing with sparse reward control problems. And I don't know if I have a slide. Oh yeah, also some work that appeared in AGI 2022. You can do maze navigation problems really well. You can augment these with little working memories and get little buffers that might remind you of things like an ACTAR, kind of glue the parts together. And you can build some really interesting little cognitive architectures out of these circuits. And we got some really good results. Obviously, we paid homage to Miller's classical work and set our working memory to 7 items, the magic number 7 plus or minus 2, even though there's very different results now. But that worked really well for the problem that we were looking at. And we could solve some we were more effective actually than reinforcement learning baselines. And obviously, CogEngine is a much more general cognitive architecture, largely draws its source inspiration and its aspiration to implement the blueprint of the common model of cognition. It's actually, you could call it a free energy common model of cognition that essentially tries to adhere to the different modules in the common model, which is actually shown at the very, very top left, and then the general principles and how the circuits relate. There's details for other work. I don't want to drag us down for that. There is an animation because the same architecture can tackle one of the real hard problems in RL, which none of my animations are playing. I apologize. Watch them. There's a procedural environment, and the agent moves across different agents, different environments. I don't know why why these don't play. Well, the robot arm was moving, and it learned really effective sparse reward control problems. I promise. Just watch the videos later. I have no clue why they don't play. The last thing I want to end, and I have just enough time to at least whet your appetite. You might say, well, wait a minute. Didn't you say at the very beginning of the talk, neurons communicate in discrete pulses called spikes? And the answer is you can do that in predictive coding. And in fact, predictive coding is a wonderful, beautiful framework for spikes. And we already have work that shows you how to do that. It also turns out that reference in the last slide, there was even early work that talked about how to build probabilistic spiking models from Dana and Rajesh's work, early work. So you might be familiar, basically spiking neurons, they just take impulse trains of values, discrete values, they build up voltage up to a certain threshold, and once they cross a threshold, they fire. And then what happens once you fire, neurons have to rest, they get tired, so we hyperpolarize them or move them away from the threshold and maybe force them to be silent for a little while to model the fatigue that neurons have. And you get extremely efficient and sparse codes. The idea is that there's only like maybe 8% of your massive vectors are ones and the rest are 0, which is perfect for neuromorphic chips. So you can get its ultimate energy efficiency, as our work and the neuromorphic community has shown. But you can build your predictive coding circuit. Essentially looks pretty much what I taught you. There's only one more concept called a trace, and we're not going to go into it, but it's just keeping a real valued chemical concentration approximation of spikes. And if you do that, you can pretty much just do what I taught you earlier, which is you build a predictive coding circuit, but you're working with pulses now. So everything is 0 or 1. but you model the electrical potential, the voltage potential, and other things inside these little neurons. But that's what those equations show you. And I was going to walk you through it, but I think for sake of time, I want to move towards the end. There is math. We could also do continual learning. You get that for free because these things are extremely sparse. And for those that might know sparse distributed codes, you get a nice anti-forgetting kind of mechanism. So to end this talk, we just saw how predictive coding can smoke a lot of deep learning on some very challenging problems. There's still a lot of work to be done. It's not a solved problem. I don't want to claim that predictive coding is all you need, but it's certainly a tool that we should consider using going in the future. The only reason, and we're not going to unpack this slide, all I just want to mention is that that free energy that I told you that predictive coding optimizes actually comes from a much more important framework that gives us a chance to, even what our last speaker address the problem of what we call mortal computation and the idea of embodiment and enactivism, which is kind of basically building agents that now have to maintain their Markov blanket. And that's just essentially a boundary that separates all those little neural components that I've taught you from an external environment. And so everything is essentially a process of conserving your own boundary. I just recommend you read that work. There will be other talks about this topic, but you can essentially use predictive coding as an important tool to build a mortal computer. And we developed something called 5E cognitive theory. For those that know what 4E is, we added an extra E because there's some other types of cognition that come from base biology that we thought was important to put in. I'm not going to talk about any of these. Well, actually, I do want to mention one. I do think it's important that predictive coding and the results that this body of work has accumulated over the last decade doesn't depend on just building big monolithic predictive coding circuits, just like we're doing with deep learning architectures and transformers. We instill a cognitive architecture prior, is my name for it. And our favorite prior was the common model of cognition, but there are other architectures that you could use to sort of construct how these circuits relate to each other. That also fits from the free energy principle and mortal computation, because nature has a lot of simplifications. Basically, it makes these approximations to say, for example, what and where in your brain has different neural structures that are separate from each other. So there's a factorization that's very natural, and it makes the optimization problem really easy. So we should learn a little bit about what evolution installed in us, inductive biases, and kind of build that into our models. And cognitive architectures is a very long and well-studied area. So that might be a useful area. We talk about different types of memory, and some of those references I have earlier show you how to combine auto-associative memory and hypervector-like memory with these predictive coding circuits to do some really nice things. The other thing I just want to mention is if you want to do neuromorphic computing or something that is thermodynamically efficient, so I said earlier that we have red AI, transformers take about 5 times the carbon emission of a lifetime of a car, and that's actually an old estimate at this point, I've realized. They're even far worse. Your brain only uses a few watts of energy, and it does beautiful, complex things. We've heard so many talks about the wonderful things that humans can do and how we would like to emulate that in our own systems. And the way to get to that energy efficiency so that we can focus on building that complexity is going to be looking to biology, perhaps, to give us a chance to build efficient circuits. So we get sparsity, synchronicity, parallelism, all the things that I've shown you very quickly in this talk. It's going to be also useful for neurorobotics. And don't forget what Albert told us. We have our guiding principle, make everything as simple as possible, but no simpler, because the idea is that we do need some mechanisms from biology. We don't necessarily need them all. And I'm not going to talk about that. This is the future. If you don't want to do feedback, you can do contrastive biological learning, but that's another talk. Last thing I want to end on, I promise this is the end. I'm a little over my predicted time. What if you want to build your own predictive coding circuits and engage yourself into research in biological learning? Our lab has wonderful tools that are efficiently implemented for you. They're meant to support computational neuroscience, cognitive neuroscience work, and machine intelligence. And they are written in JAX, and they are heavily optimized for GPUs, GPUs and CPUs. We also have ports for Intel's Lava too. Loihi 2 Lava framework. So if you wanted some emulation of your spiking neural nets or your spiking predictive coding that could run on chips, this is a really great place to look. And we have long support for this. This has existed for many, many years. And we also welcome community contributions. I like to highlight the NGC Museum. It's just a museum that's meant to reproduce all the works in history. Obviously, that's a quite ambitious goal, but if you use NGC Learn and build your own model, whether it's predictive coding or maybe our spiking plasticity models, and you use it in your own work, we'd love to hear about it. And if you wrote it in NGC Learn, we'd like to feature it so that way others will know of your work, can run your model, reproduce your results, and add a little bit more rigor to machine intelligence, because reproducibility is one of its biggest weaknesses. And then the last thing I should mention is I can't say that this is a one-man army. I have a small army of wonderful students. For some reason, that picture didn't show up, but I promise there's another one. His name's Will. I don't know why what happened. The conversion process messed it up. I have many wonderful collaborators too that makes this work possible. Some of the names you might recognize. And we do a lot of really fun things. So keep an eye out for the NAC lab if you're interested in what is the future or an alternative pathway to our backprop-based deep learning way of doing things. So with that, I wrap up. Maybe a question.
Thank you so much. That was so fascinating. We have time for a couple questions, if there's any from the audience. Aha, right over here.
Thank you for a fantastic lecture. Comprehensive, utterly fantastic. I saw your second to last slide in your collaborator list. You had verses there. I have a question. Given this is an AGI conference, I remember a couple of months ago, there's this huge ad in the New York, or letter in the New York Times saying, we've discovered AGI using predictive coding, essentially. So you're here. How did they do it? I was trying to think. I was banging my head saying, how did they do it? Please tell us. Yeah.
Well, I should be very careful because I don't speak for verses. I am just an independent researcher at RIT. I just work with my friend Carl and Tomaso. So I will comment on one thing. I don't believe that they use predictive coding. They're using a certain implementation of active inference, but I don't want to speak for that now. I have to be very careful politically about what I say for verses. So the answer is I'm not entirely sure, but I do know it's not the framework that I was showing. Okay. It's not predictive coding. I can tell you that. Sure.
Okay. Thank you, and thank you for a fantastic lecture.
Yeah, thank you very much.
We have a question online I'll ask. Robert said there are hypotheses about chronic pain that use predictive coding as an explanatory model for why pain can persist when tissue damage has gone. Do you know if there are computational insights into it?
Well, I mean, there is a long history of using predictive coding for modeling all kinds of phenomena in terms of, I see hands waving, I'm not sure.
Are you still mic'd?
I don't know, I haven't done anything. Maybe it got knocked. Don't know. Can you hear me? I just try to speak louder so that way I can.
Well, there's a stream that can't hear the speak
Right.
louder.
Will that
You can use this, yeah.
I'll just speak into the mic. So there is already a lot of good work, even modeling things like, for example, schizophrenia and other mental phenomenon. And there's a lot of long history in neuropsychiatry and computational psychiatry of modeling things. I don't want to speak to that as my lab does not focus on modeling those things, but I think predictive coding, I can't speak specifically to modeling chronic pain. I will have to look into that work. However, what's really interesting about predictive coding, and I've talked to this with some of my students, is that you could do some really interesting things to manipulate the dynamics of how these neurons move through time, since predictive coding is inherently temporal, as I tried to convince you in this talk. And you can do things to create degenerate cases, behaviors that you would not expect the neural dynamics to follow. An easy one, and again, it could maybe perhaps relate to the chronic pain, is you know that we make a prediction and we take data and we compare that mismatched signal and we transmit it back into the network. Well, in some instances, you can also remove that target signal. And basically, when you're over-predicting, you are hallucinating, and you can create confabulations from the model, and that can be useful in certain applications in computational psychiatry. So these models can be very useful for modeling that phenomenon. Although I do want to comment, you probably want to add a little bit more biological detail than the simplifications that I made here. So I don't think this predictive coding circuit probably could explain every single thing that you can model in actual biology, but with a few little extra touches, I know that there's a good work in, and I recommend looking at computational psychiatry and its applications of predictive coding.
Thank you very much. Any more?
One question, Alex. So, and I sort of know the answer, but I'm curious to dig in, or have you dig in a little more. So, one reason I've thought predictive coding could be interesting for learning neural nets is not just that it could be a more scalable way of learning once it's more advanced, because it's asynchronous and more parallelizable and so forth, but also it seemed like perhaps it could learn more transparent semantic representations than we're getting with, for example, transformer neural networks. And if you had a more sort of simple and transparent semantic representation inside the network, that would help with a number of things, including reflective self-understanding of the neural network and analysis of that neural network by other neural nets or by symbolic systems, right? Thus perhaps easing neural symbolic integration. But I wonder if you could share some of your intuition as to why predictive coding might lead to sort of less tangled up and more transparent internal knowledge representation.
So that's a really good question, Ben. And I think while there isn't a good amount of work at the moment on getting those exact semantic representations that you seek, the nice thing about the predictive coding framework, which funny enough, it wasn't highlighted in what I taught you. Those are kind of like the plasticity in inference dynamics. But since these neural states, the layers of neurons are inherently temporal, and they sort of have values inherent to them all the time, you can actually introduce something called priors and actually place, for example, certain distributions, and you can also place constraints on what you want those vector representations to be. For example, this might not be terribly useful for the semantic representations you spoke for, but you can place sparsity priors. So if you want to, for example, say, I can only have so many neurons fire at any one time step, you can actually naturally and easily encode distributions or recurrent synaptic matrices that have certain interpretations. Actually, in one of the papers, the Nature paper that I was showing you earlier, we placed a very specific masking matrix that would actually enforce columns of neurons to only be active, and they would compete with each other. So basically, there was like a little competitive pattern. And so these can get you very sparse representations, which could, for example, be argued to be a little bit useful for disentanglement. There's some interesting thoughts that our group has had about maybe perhaps introducing a disentanglement prior. I think, for example, classical work that has existed for a long time, maybe some of you are familiar with independent components analysis, I think introduced some interesting ideas about how to construct factors that are separate from one another, that aren't entangled, they are disentangled. It solves the cocktail party problem. And you could naturally integrate that into the predictive coding framework, whether you place it at every layer of neurons. You could also just place it on some layers, like for example, at the very, very top of this generative model. If you want it to sort of construct something that looks like a symbolic vector, you place a particular prior. And
Right, so part of the network can be as tangled as it needs to be.
Yeah.
And then the other part is pressured by the prior to sort of disentangle that other part. Yeah, that seems very promising direction.
And what's really nice about what you just said too is if you, let's say, place a prior at the very top, you can actually write out what the generative model is too. I didn't go into detail, but there's actually a generative model underlying this, and you can write out its probability chain and talk about what distributions you use if you use a distributional type of constraint. So you can even write that down.
Yeah, so at a high level, what we see is there's an explicit connection between probabilistic modeling and neural learning. much more so than is the case with traditional back propagation-based training. So if you go back to something like Google's Edward framework from a number of years ago, where they were trying to make a probabilistic programming-based wrapper for neural net learning, that never actually worked very well. One would conjecture something like that could perhaps work better with predictive code-based learning under the hood for the neural part.
I agree.
Excellent. Any other questions? Right here. Fantastic. Thank you. Last question.
You actually answered one of my other questions about the relationship between this and presumably category theory and semantics. But the other one I had was you mentioned several times work with neuromorphic chips and how they play in. Has has there actually been neuromorphic chips built around PCs?
Not that I'm entirely aware of. I mean, the work that I showed you would be a neuromorphic friendly architecture. So there is plenty, there's actually a growing body of work on spiking PC, where you're building spiking nets, which would naturally fit to the neuromorphic chip. As to what has been built actual on a neuromorph, like let's say Loihi 2, I am not entirely sure there's much. There might be something I'm not aware of, but it's not a very prominent area of development at the moment.
Thank you. Very cool.
Thank you.
All right. Thank you very much for making us all experts on predictive coding for initiates. Thank you. All right, just a couple last items to announce, and we'll finish the day off with the poster session next door. Again, Rachel Sinclair couldn't be here today. She was unable to attend the conference this year, unfortunately, at the last minute. So instead, we'll have a poster session next door. All the poster presenters will be presenting their posters. We've got a couple demos over there. We're really excited to share that with everybody this year. Then tonight at 7 o'clock at the Burke Museum, everybody's invited to the Desdemona's Dream concert and reception for the AGI conference. There will be drinks. There will be finger food, but not dinner. So if you need dinner, eat before you go. And you'll get to see Ben on keyboards, Diane Krause on saxophone, Desdemona on vocals. And it should be a very fun night. We start tomorrow at 9 a.m. with Gary Marcus, so it should be a fantastic morning tomorrow, and we look forward to seeing everybody next door for the poster session. Tonight at the performance at the Burke Museum, right down the way here, very much within walking distance, and tomorrow morning. Thank you very much.